Thank you. Those who have watched this movie, please visit our planetarium and also ISRO bus. And so in 80 students wait ಮಾಡ್ತಾ ಇದ್ದಾರೆ ಹೊರಗಡೆ. So next batch is waiting for the talk. You please go and see the planetarium and also ISRO bus. Okay. And outdoor science park. And also go and have the tea. Tea and then planetarium. Okay. Teachers can attend this session, biology session.
Sir, PPT. ಕರೆಕ್ಟ್ ಆಗಿದೆ ಡೌನ್ ಆಗಿಬಿಟ್ಟಿದೆ ನೋಡಿ ಈಗ 3D ಗ್ಲಾಸಿಂದ ಏನಾರು ಅಂತ ಇದೆಯಾ ಸರ್ ನೋಡಿ ಇದು ಸ್ಪೀಕರ್ ನೋಡಿ ಸ್ಪೀಕರ್ ನೋಡಿ ಹಿಂಗೆ ಹಾಂ ನೋಡಿ ಚೇಂಜ್ ಮಾಡಿ ಚೇಂಜ್ ಮಾಡಿದ್ದೀವಿ ನೋಡಿ ಈಗ ಸ್ಪೀಕರ್ ಕೊಡಿ HDMI ಸ್ಪೀಕರ್ ಕೊಡಿ ಗೊತ್ತಲ್ಲ ರಿಮೋಟ್ ಇರುತ್ತೆ
Students, good afternoon. Planetarium nodadra? Then Space on Wheel? Chanagita? Now we have a talk by my guru, Dr. Balkrishna Adiga sir. He was the principal of Vijaya College. He has more than 45 years of experience in the field of teaching. Sir will be delivering a talk on biology, how to write biology, rather how to solve biology paper. He will be talking, and what are the opportunities in the field of biology also sir will be speaking about. With this, I request my guru to come out to the stage and speak. Over to you, sir.
Good afternoon, everybody. ಎಲ್ಲರಿಗೂ ಮಧ್ಯಾಹ್ನದ ಶುಭಾಶಯ. ಇವತ್ತು ನಿಮ್ಮನ್ನೆಲ್ಲ ಉದ್ದೇಶಿಸಿ ಜೀವಶಾಸ್ತ್ರ ಬಯಾಲಜಿಗೆ ಸಂಬಂಧಪಟ್ಟ ಹಾಗೆ ಕೆಲವು ಮಾಹಿತಿಯನ್ನು ಹಂಚಿಕೊಳ್ಳೋದಕ್ಕೆ ನನಗೆ ನಾನು 71ನೇ ಇಸ್ವಿಯಿಂದ ಬಯಾಲಜಿ ಪಾಠ ಮಾಡ್ತಾ ಇದ್ದೀನಿ. 50 ವರ್ಷದ ಮೇಲಾಯಿತು. ಬಯಾಲಜಿ ಅಂದರೆ ಏನು ಅಂತ ನಿಮಗೆ ಗೊತ್ತಿದೆ. ಬಯಾಲಜಿ ಈಸ್ ದಿ ಸ್ಟಡಿ ಆಫ್ ಲೈಫ್. ಜೀವಿಗಳ ಅಧ್ಯಯನಕ್ಕೆ ಜೀವಶಾಸ್ತ್ರ ಅಂತ ಕರಿತೀವಿ. ಜೀವಿಗಳು ಅಂದರೆ ಅವು ಸೂಕ್ಷ್ಮ ಜೀವಿಗಳಾಗ್ಬೋದು, ಮೈಕ್ರೋ ಆರ್ಗ್ಯಾನಿಸಮ್ಸ್ ಆಗ್ಬೋದು, ಪ್ಲಾಂಟ್ಸ್ ಆಗ್ಬೋದು, ಸಸ್ಯಗಳಾಗ್ಬೋದು, ಅಥವಾ ಆನಿಮಲ್ಸ್ ಆಗ್ಬೋದು. ಬಯಾಲಜಿ ಇಸ್ ದಿ ಸ್ಟಡಿ ಆಫ್ ಲೈಫ್ ಅನ್ನೋದಕ್ಕಿಂತ ನಾನು ಅಂದ್ಕೊಳ್ಳೋದು ಬಯಾಲಜಿ ಈಸ್ ಎ ಬ್ರಾಂಚ್ ಆಫ್ ಸೈನ್ಸ್ ವಿಚ್ ಹ್ಯಾಸ್ ಲೈಫ್ ಅಂತ. ಫಿಸಿಕ್ಸ್ ಜೀವ ಇಲ್ಲದ ವಸ್ತುಗಳ ಅಧ್ಯಯನಕ್ಕೆ ಸಂಬಂಧಪಟ್ಟಿದೆ. ಕೆಮಿಸ್ಟ್ರಿ ಕೂಡ ಜೀವ ಇಲ್ಲದ ವಸ್ತುಗಳ ಅಧ್ಯಯನಕ್ಕೆ ಸಂಬಂಧಪಟ್ಟಿದೆ. ಆದರೆ ಬಯಾಲಜಿ ಮಾತ್ರ ಜೀವ ಇರುವಂಥ ವಸ್ತುಗಳ ಅಧ್ಯಯನಕ್ಕೆ ಸಂಬಂಧಪಟ್ಟಿದೆ. ಅಂದರೆ ವಿಜ್ಞಾನದ ಶಾಖೆಗಳಲ್ಲಿ, ಅಮಾಂಗ್ ದಿ ಬ್ರಾಂಚಸ್ ಆಫ್ ಸೈನ್ಸ್, ವಿಜ್ಞಾನದ ಶಾಖೆಗಳಲ್ಲಿ ಜೀವಂತವಾಗಿರುವಂಥ ಶಾಖೆ ಯಾವುದು ಅಂದರೆ ಅದು ಬಯಾಲಜಿ. ಬಯಾಲಜಿಯ ಕೆಲವು ವಿಶೇಷಗಳ ಬಗ್ಗೆ ನಾನು ನಿಮಗೆ ಹೇಳಬೇಕು. ನೀವೆಲ್ಲರೂ ಹೈಸ್ಕೂಲ್ ವಿದ್ಯಾರ್ಥಿಗಳಲ್ವಾ? ಓಕೆ. ನಿಮಗೆ ಗೊತ್ತಿದೆ, ಫಿಸಿಕ್ಸ್ನಲ್ಲಿ ನೀವು ಅನೇಕ ಸಮಸ್ಯೆಗಳನ್ನು ಬಿಡಿಸ್ತೀರ. ಸಾಲ್ವಿಂಗ್ ಸಮ್ ಪ್ರಾಬ್ಲಮ್ಸ್, ಆಪ್ಟಿಕ್ಸಿಗೆ ಸಂಬಂಧಪಟ್ಟಿದ್ದಿರ್ಬೋದು, ಮ್ಯಾಗ್ನೆಟಿಸಮ್ಗೆ ಸಂಬಂಧಪಟ್ಟಿದ್ದಿರ್ಬೋದು, ಕೆಲವು ಸಮಸ್ಯೆಗಳನ್ನು ಬಿಡಿಸ್ತೀರ. ಕೆಮಿಸ್ಟ್ರಿನಲ್ಲೂ ಕೂಡ ದೇರ್ ಆರ್ ಪ್ರಾಬ್ಲಮ್ಸ್. ಈಕ್ವಲೆಂಟ್ ವೆಯ್ಟ್ ಕಂಡುಹಿಡಿಯೋದು, ನಾರ್ಮ್ಯಾಲಿಟಿ ಕಂಡುಹಿಡಿಯೋದು ಇತ್ಯಾದಿ. ಬಯಾಲಜಿನಲ್ಲಿ ಎಲ್ಲಾದರೂ ಪ್ರಾಬ್ಲಮ್ಸ್ ಇದೆ ಅಂತ ಕೇಳಿದ್ದೀರಾ ನೀವು? ಬಯಾಲಜಿ ಇಸ್ ಎ ಸಬ್ಜೆಕ್ಟ್ ವಿಚ್ ಡಸ್ ನಾಟ್ ಹ್ಯಾವ್ ಎನಿ ಪ್ರಾಬ್ಲಮ್ಸ್. ಸಮಸ್ಯೆಗಳೇ ಇಲ್ಲದಂಥ ಒಂದು ಸಬ್ಜೆಕ್ಟ್ ಯಾವುದಾದ್ರೂ ಇದೆ ಅಂದರೆ ಅದು ಬಯಾಲಜಿ. ಆದರೆ ಏನಾಗ್ಬಿಟ್ಟಿದೆ, ಸುಮಾರು ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಬಯಾಲಜಿನೇ ಒಂದು ಸಮಸ್ಯೆ ಆಗ್ಬಿಟ್ಟಿದೆ. ಬಯಾಲಜಿ ಅಂದರೆ ಬಯಾಲಜಿ ಆಗಿದೆ. ಭಯ ಪ್ರೆಸಾಲಜಿ. ಯಾಕೆ ಹಿಂಗಾಗಿದೆ ಅಂದರೆ, ಬಹುಶಃ ನನ್ನ ಅನುಭವದಲ್ಲಿ ನಾನು ಹೇಳೋದಾದರೆ ಅದಕ್ಕೆ 2 ಕಾರಣ ಇರ್ಬೋದು ಅಂತ ನಾನು ಅನ್ಕೋತೀನಿ. ಇದನ್ನ ಯಾಕೆ ಹೇಳ್ತಾ ಇದ್ದೀನಿ ಅಂದರೆ, ನಾನೀಗ ಹೇಳುವಂಥ 2 ಕಾರಣದ ಬಗ್ಗೆ ಗಮನವಿಟ್ಟು ಕೇಳಿಸ್ಕೊಳ್ಳಿ. ಇವೆರಡಕ್ಕೆ ನೀವು ಹೆಚ್ಚಿನ ಗಮನ ಕೊಟ್ಟರೆ ಬಯಾಲಜಿನ ನೀವು ತುಂಬ ಸುಲಭ ಮಾಡ್ಕೋಬೋದು. ಎರಡು ಕಾರಣ ಇರ್ಬೋದು ಅಂತ ನನಗನ್ಸುತ್ತೆ. ಒಂದು, ಬಯಾಲಜಿನಲ್ಲಿ ಚಿತ್ರಗಳು ಜಾಸ್ತಿ. ಬಯಾಲಜಿ ಈಸ್ ಫುಲ್ ಆಫ್ ಡಯಾಗ್ರಾಮ್ಸ್. ಹೌದಾ? ಫುಲ್ ಆಫ್ ಡಯಾಗ್ರಾಮ್ಸ್. ಆ ಡಯಾಗ್ರಾಮ್ ಬರೆಯೋದು ಅಂದರೆ ಕೆಲವರಿಗೆ ಬೇಜಾರು, ಆಲಸ್ಯ. ಅದು ಒಂದು ಕಾರಣ ಇರ್ಬೋದು ಅಂತ. ಎರಡನೇ ಕಾರಣ ಏನು? ಬಯಾಲಜಿನಲ್ಲಿ ಟೆಕ್ನಿಕಲ್ ಟರ್ಮ್ಸ್ ಜಾಸ್ತಿ, ತುಂಬ ಟೆಕ್ನಿಕಲ್ ಟರ್ಮ್ಸ್. ನೀವು ಗಮನಿಸಿದ್ರೆ ಈ ಟೆಕ್ನಿಕಲ್ ಟರ್ಮ್ಸ್ ಎಲ್ಲ ಎಲ್ಲಿಂದ ತಗೊಂಡಿದ್ದಾರೆ? ಲ್ಯಾಟಿನಿಂದ ತಗೊಂಡಿದ್ದಾರೆ ಅಥವಾ ಗ್ರೀಕಿಂದ ತಗೊಂಡಿದ್ದಾರೆ. ಸಾಮಾನ್ಯವಾಗಿ ನಮಗೇನು ಅರ್ಥ ಆಗಲ್ವೋ ಅದನ್ನು ನಾವು ಗ್ರೀಕ್ ಅಂಡ್ ಲ್ಯಾಟಿನ್ ಅಂತ ಕರಿತೀವಿ. ಆದರೆ ನನಗನ್ಸೋದು ಟೀಚರಾಗಿ, ಒಬ್ಬ ಬಯಾಲಜಿ ಟೀಚರಾಗಿ ನನಗನ್ಸೋದು, ಈ ಗ್ರೀಕ್ ಅಂಡ್ ಲ್ಯಾಟಿನ್ ಪದಗಳನ್ನು ನಾವು ಸರಿಯಾಗಿ ಅರ್ಥ ಮಾಡಿಕೊಂಡ್ರೆ ಬಯಾಲಜಿ ತುಂಬ ಸುಲಭವಾಗುತ್ತೆ ಅಂತ. ತುಂಬ ಸುಲಭವಾಗುತ್ತೆ. ನೀವು ನೋಡಿ, ಕೆಲವು ಸರಳವಾದ ಉದಾಹರಣೆಗಳನ್ನು ಕೊಡ್ತೀನಿ. ಈ ಕೆಲವು ಪದಗಳನ್ನು ನೀವು ಕೇಳಿದ್ದೀರಾ. ಪ್ರೋಟೋಝೋವಾ ಅನ್ನೋ ಪದ ಕೇಳಿದ್ದೀರಾ. ಅದು ಲ್ಯಾಟಿನ್ನಿಂದ ಬಂದಿರುವಂಥ ಪದ. ಪ್ರೋ ಅಂದರೆ ಯಾವಾಗಲೂ ಬಿಗಿನಿಂಗ್ ಅಂತ, ಸ್ಟಾರ್ಟಿಂಗ್ ಅಂತ. ಪ್ರೋಟೋಝೋವಾ ಅಂದರೆ ಅನಿಮಲ್ಸ್. ಜುವಾಲಜಿ ಬಂದಿರೋದು ಝೋವಾದಿಂದನೇ ಬಂದಿರೋದು. ಸೊ ಪ್ರೋಟೋಝೋವಾ ಅಂದರೆ ಏನು? ಭೂಮಿಯ ಮೇಲೆ ಪ್ರಾರಂಭದಲ್ಲಿ ಕಾಣಿಸಿದ ಪ್ರಾಣಿಗಳು ಯಾವುದು? ಅವು ಪ್ರೋಟೋಝೋವಾ. ಯಾವುದು? ಅಮೀಬಾ, ಪ್ಯಾರಮೀಷಿಯಂ, ಯುಗ್ಲಿನ ಮುಂತಾದ ಜೀವಿಗಳು. ಹೌದಾ? ಇನ್ನೊಂದು ಪದ ಕೇಳಿದ್ದೀರಾ ನೀವು, ಪ್ರೋಫೇಸ್ ಅಂತ ಒಂದು ಪದ ಕೇಳಿದ್ದೀರಾ. ಮೈಟಾಸಿಸ್ನಲ್ಲಿ ಸೆಲ್ ಡಿವಿಷನ್ನಲ್ಲಿ ಬರುತ್ತೆ. ಪ್ರೋಫೇಸ್ ಅಂತ ಯಾಕೆ ಕರಿತೀವಿ? ಪ್ರೋ ಅಂದರೆ ಪ್ರಾರಂಭ, ಮತ್ತು ಫೇಸ್ ಅಂದರೆ ಹಂತ. ಸೊ ಮೈಟಾಸಿಸ್ ಸೆಲ್ ಡಿವಿಷನ್ನಲ್ಲಿ ಪ್ರಾರಂಭದ ಹಂತಕ್ಕೆ ಪ್ರೋಫೇಸ್ ಅಂತ ಕರಿತೀವಿ. ಅದರ ಮುಂದಿನ ಹಂತಕ್ಕೆ ಮೆಟಾ ಫೇಸ್ ಅಂತ ಕರಿತೀವಿ. ಮೆಟಾ ಅಂದರೆ ನಂತರ. ಅದರ ನೆಕ್ಸ್ಟು ಅನಾಫೇಸ್ ಅಂತ ಕರಿತೀವಿ, ಇನ್ನೂ ಮುಂದೆ ಅಂತ. ಅನಾಫೇಸ್ ಅಂದರೆ ಕೊನೆಯಲ್ಲಿ ಟಿಲೋಫೇಸ್. ಟಿಲೋ ಅಂದರೆ ಎಂಡ್, ಕೊನೆಯ ಹಂತ. ಅಂದರೆ ಯಾವುದೇ ಲ್ಯಾಟಿನ್ ಅಥವಾ ಗ್ರೀಕ್ ಪದವನ್ನು ನೀವು ಅರ್ಥ ಮಾಡಿಕೊಂಡ್ರೆ ಬಯಾಲಜಿನಲ್ಲಿ ಎಲ್ಲವೂ ಕೂಡ ತುಂಬ ಸುಲಭ ಅನಿಸುತ್ತೆ. ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕಾದ್ರೆ ನೀವೇನು ಮಾಡಬೇಕು? ಆ ಪದವನ್ನು ಒಡಿಬೇಕು. ಯು ಹ್ಯಾವ್ ಟು ಸ್ಪ್ಲಿಟ್ ದಟ್ ಲ್ಯಾಟಿನ್ ಆರ್ ಗ್ರೀಕ್ ವರ್ಡ್ ಆ್ಯಂಡ್ ಫೈಂಡ್ ಔಟ್ ವಾಟ್ ಈಸ್ ಇಟ್ಸ್ ಮೀನಿಂಗ್ ಅಂತ. ನೀವೆಲ್ಲ ಬೈನಾಮಿಯಲ್ ನಾಮಿನ್ಕ್ಲೇಚರ್ ಬಗ್ಗೆ ಕೇಳಿದ್ದೀರಾ. ಪ್ರತಿಯೊಂದು ಪ್ರಾಣಿಗೆ ಅಥವಾ ಪ್ರತಿಯೊಂದು ಸಸ್ಯಕ್ಕೆ ಅಥವಾ ಪ್ರತಿಯೊಂದು ಸೂಕ್ಷ್ಮ ಜೀವಿಗೆ ಒಂದು ವೈಜ್ಞಾನಿಕ ಹೆಸರನ್ನು ಕೊಡ್ತಾರೆ. ಎ ಸೈಂಟಿಫಿಕ್ ನೇಮ್ ಈಸ್ ಗಿವನ್. ದಟ್ ಸೈಂಟಿಫಿಕ್ ನೇಮ್ ಕನ್ಸಿಸ್ಟ್ಸ್ ಆಫ್ 2 words ಅಲ್ವಾ? 2 ಪದ ಇರುತ್ತೆ. ದಿ ಫಸ್ಟ್ ವರ್ಡ್ ಈಸ್ ದಿ ನೇಮ್ ಆಫ್ ದಿ ಜೀನಸ್. ಅದು ಯಾವ ಜಾತಿಗೆ ಸೇರಿದ ಜೀವಿ ಅನ್ನೋದನ್ನು ಇಂಡಿಕೇಟ್ ಮಾಡೋದು ಫಸ್ಟ್ ನೇಮ್. ದಿ ಸೆಕೆಂಡ್ ನೇಮ್ ಈಸ್ ದಿ ನೇಮ್ ಆಫ್ ದಿ ಸ್ಪೀಶೀಸ್. ಅದು ಯಾವ ಪ್ರಭೇದಕ್ಕೆ ಸೇರಿದೆ ಅನ್ನೋದನ್ನು ಹೇಳೋದು ಸೆಕೆಂಡ್ ನೇಮ್. ಸೊ ಎವ್ರಿ ಸೈಂಟಿಫಿಕ್ ನೇಮ್ ಹ್ಯಾಸ್ 2 words. ದಿ ಫಸ್ಟ್ ನೇಮ್ ಈಸ್ ದಿ ನೇಮ್ ಆಫ್ ದಿ ಜೀನಸ್, ಜಾತಿ. ಸೆಕೆಂಡ್ ನೇಮ್ ಈಸ್ ದಿ ನೇಮ್ ಆಫ್ ದಿ ಸ್ಪೀಶೀಸ್, ಪ್ರಭೇದ. ಒಂದು ಜಾತಿಯಲ್ಲಿ ಅನೇಕ ಪ್ರಭೇದಗಳಿರ್ಬೋದು, 100,000 ಸಾವಿರಾರು ಪ್ರಭೇದಗಳಿರ್ಬೋದು, ಅಥವಾ ಕೇವಲ ಒಂದೇ ಪ್ರಭೇದ ಇರ್ಬೋದು. ಆ 2 ಹೆಸರನ್ನು ಸೇರಿಸಿ ವೈಜ್ಞಾನಿಕ ಹೆಸರನ್ನು ಕೊಡ್ತಾರೆ. ಉದಾಹರಣೆಗೆ ಮ್ಯಾಂಜಿಫೆರಾ ಇಂಡಿಕಾ ಅನ್ನೋದು ಮಾವಿನ ಮರದ ವೈಜ್ಞಾನಿಕ ಹೆಸರು. ಮಾವಿನ ಮರದ ವೈಜ್ಞಾನಿಕ ಹೆಸರು ಮ್ಯಾಂಜಿಫೆರಾ ಇಂಡಿಕಾ. ಮ್ಯಾಂಜಿಫೆರಾ ಜಾತಿಯ ಹೆಸರು, ಇಂಡಿಕಾ ಪ್ರಭೇದದ ಹೆಸರು. ಈ ಮ್ಯಾಂಜಿಫೆರಾ ಪದ ತಗೊಳ್ಳಿ, ಅದರಲ್ಲಿ 2 ಲ್ಯಾಟಿನ್ ಪದ ಇದೆ. ಮ್ಯಾಂಜಿ ಅಂದರೆ ಸ್ವೀಟ್ ಅಂತ, ಫೆರಾ ಅಂದರೆ ಹ್ಯಾವಿಂಗ್ ಅಂತ. ಅಂದರೆ ಅದರ ಅರ್ಥ ಏನು? ಮ್ಯಾಂಜಿಫೆರಾ ಅಂದರೆ ಫ್ರೂಟ್ ಹ್ಯಾವಿಂಗ್ ಸ್ವೀಟ್ನೆಸ್ ಅಂತ. ಸಿಹಿಯಾದ ಹಣ್ಣು ಯಾವುದು? ಮಾವಿನ ಹಣ್ಣು. ಇಂಡಿಕಾ ಅನ್ನೋ ಹೆಸರು ಎಲ್ಲಿಂದ ಬಂತು? ಇಟ್ ಈಸ್ ಗ್ರೋನ್ ಓನ್ಲಿ ಇನ್ ಇಂಡಿಯಾ. ಸೊ ಇಂಡಿಕಾ ಅನ್ನೋ ಹೆಸರು ಬಂತು. ಇದೇ ಥರ ನೀವು ಯಾವುದೇ ವೈಜ್ಞಾನಿಕ ಹೆಸರನ್ನು ತಗೊಳ್ಳಿ, ಬೈನಾಮಿಯಲ್ ನಾಮಿನ್ಕ್ಲೇಚರ್ ಅಂತ ಕರಿತೀವಿ ಅದಕ್ಕೆ. ಆ ವೈಜ್ಞಾನಿಕ ಹೆಸರಿಗೆ ಒಂದು ಹಿನ್ನೆಲೆ ಇದೆ. ಅದು ಆ ಜೀವಿಗೆ ಸಂಬಂಧಪಟ್ಟ ಒಂದು 2-3 ಲಕ್ಷಣಗಳನ್ನು ನಮಗೆ ಹೇಳುತ್ತೆ. ಹ್ಯೂಮನ್ ಸ್ಪೀಶೀಸ್ ತಗೊಳ್ಳಿ. ಹ್ಯೂಮನ್ ಸ್ಪೀಶೀಸನ್ನು ಏನಂತ ಕರಿತೀವಿ ನಾವು? ಹೋಮೋ ಸೆಪಿಯನ್ಸ್ ಅಂತ. ಹೋಮೋ ಅಂದ್ರೇನು? ಲ್ಯಾಟಿನ್ನಲ್ಲಿ ಹೋಮೋ ಅಂದರೆ 2 ಅರ್ಥ ಇದೆ. ಒಂದು ಸಿಮಿಲರ್ ಅಂತ, ಎರಡನೇದು ನೇರವಾಗಿ ನಿಲ್ಲೋದು ಅಂತ. ಹೋಮೋ ಅಂದರೆ ನೇರವಾಗಿ ನಿಲ್ಲುವಂಥ ಪ್ರಾಣಿ ಅಂತ. ಎಲ್ಲ ಪ್ರಾಣಿಗಳನ್ನು ನೋಡಿ, ನಮ್ಮ ಥರ ಸಂಪೂರ್ಣ ನೇರವಾಗಿ ನಿಲ್ಲುವಂಥ ಪ್ರಾಣಿ ಯಾವುದಾದ್ರೂ ಇದೆಯಾ? ಇಲ್ಲ. ಸೊ ಹೋಮೋ ಅಂದರೆ ನೇರವಾಗಿ ನಿಲ್ಲುವಂಥ ಪ್ರಾಣಿ. ಸೆಪಿಯನ್ಸ್ ಅಂದ್ರೇನು? ಸೆಪಿಯನ್ಸ್ ಅಂದರೆ ಲ್ಯಾಟಿನಲ್ಲಿ ನೋಯಿಂಗ್ ಎವ್ರಿಥಿಂಗ್ ಅಂತ, ಅಂದರೆ ಅತಿ ಬುದ್ಧಿವಂತ ಪ್ರಾಣಿ ಅಂತ. ಮನುಷ್ಯ ತನಗೆ ತಾನೇ ಕೊಟ್ಟುಕೊಂಡ ಹೆಸರದು, ನಾನು ಅತಿ ಬುದ್ಧಿವಂತ ಪ್ರಾಣಿ ಅಂತ. ಹೋಮೋ ಸೆಪಿಯನ್ಸ್. ಇನ್ನೊಂದು ಉದಾಹರಣೆ ನೋಡಿ, ರಾನಾ ಹೆಕ್ಸಾಡಕ್ಟೈಲ ಅಂತ. ಕಪ್ಪೆಯ ವೈಜ್ಞಾನಿಕ ಹೆಸರು ರಾನಾ ಹೆಕ್ಸಾಡಕ್ಟೈಲ. ರಾನಾ ಅಂದರೆ ಹಾಪಿಂಗ್ ಅಂತ, ಕುಪ್ಪಳಿಸೋದು. ಕಪ್ಪೆಗಳು ಕುಪ್ಪಳಿಸೋದು ಗೊತ್ತಿದೆ ನಿಮಗೆ. ಅದ್ರ ಮೂಲಕ, ಆ ಒಂದು ಲಕ್ಷಣದ ಮೂಲಕ ಬಂದಿರೋ ಹೆಸರು ರಾನಾ ಅಂತ. ಹೆಕ್ಸಾ ಅಂದರೆ 6, ಹೆಕ್ಸಗನ್ ಅಂತ ಕೇಳಿದ್ದೀರ ನೀವು. ಹೆಕ್ಸಾ ಅಂದರೆ 6. ಡ್ಯಾಕ್ಟೈಲ ಅಂದರೆ ಡಿಜಿಟ್ಸ್, ಫಿಂಗರ್ಸ್. ಅದಕ್ಕೆ ಕಾಲಿನಲ್ಲಿ 6 ಬೆರಳಿದೆ ಆ ಪ್ರಭೇದಕ್ಕೆ. ಸೊ 6 ಬೆರಳಿರುವ, ಕಾಲಿನಲ್ಲಿ 6 ಬೆರಳಿರುವ ಕುಪ್ಪಳಿಸುವ ಪ್ರಾಣಿ ಯಾವುದು? ಕಪ್ಪೆ, ರಾನಾ ಹೆಕ್ಸಾಡಕ್ಟೈಲ. ಹೀಗೆ ಯಾವುದೇ ವೈಜ್ಞಾನಿಕ ಹೆಸರನ್ನು ತಗೊಂಡು ನೀವು ವಿಶ್ಲೇಷಣೆ ಮಾಡಿದ್ರೆ, ಆ ವೈಜ್ಞಾನಿಕ ಹೆಸರಿನಲ್ಲಿ 2-3 ಸಂಬಂಧಪಟ್ಟ ಲಕ್ಷಣಗಳಿರೋದು ನಮಗೆ ಗೊತ್ತಾಗುತ್ತೆ. ಅಂದರೆ ಹಿಂದಿನವರು ಲ್ಯಾಟಿನ್ನಲ್ಲೇ ಅಥವಾ ಗ್ರೀಕ್ನಲ್ಲೇ ಯಾಕೆ ಹೆಸರು ಕೊಡ್ತಾ ಇದ್ರು? ನಮ್ಮ ತಲೆ ತಿನ್ನೋದಕ್ಕ ಅಲ್ಲ. ಆವಾಗ ಇಂಗ್ಲೀಷ್ ಇರಲಿಲ್ಲ. ಇಂಗ್ಲೀಷ್ ಬಂದಿದ್ದೆಲ್ಲ ಒಂದು 200-300 ವರ್ಷದಿಂದ ಈಚೆಗೆ. ವೈಜ್ಞಾನಿಕ ಹೆಸರು ಕೊಡುವ ಪದ್ಧತಿ 300 ವರ್ಷಕ್ಕಿಂತ ಹಿಂದೆ ಇತ್ತು. ಆವಾಗ ಪ್ರಪಂಚದಲ್ಲಿ 3 ಭಾಷೆ ತುಂಬ ಪರಿಚಯವಾದಂಥ ಭಾಷೆ ಯಾವುದು? ಒಂದು ಗ್ರೀಕು, ಒಂದು ಲ್ಯಾಟಿನ್ನು, ಇನ್ನೊಂದು ಸಂಸ್ಕೃತ. ಓಲ್ಡೆಸ್ಟ್ ಲ್ಯಾಂಗ್ವೇಜಸ್. ಹಾಗಾಗಿ ಆಗಿನ ವಿಜ್ಞಾನಿಗಳು, ಕರೋಲಸ್ ಲಿನೇಯಸ್ ಮುಂತಾದವರು ಈ ಪದ್ಧತಿಯನ್ನು ಪ್ರಾರಂಭ ಮಾಡಿದಾಗ ಅವರು ವೈಜ್ಞಾನಿಕ ಹೆಸರಿಗೆ ಹುಡುಕಿದ್ದು ಲ್ಯಾಟಿನ್ ಮತ್ತು ಗ್ರೀಕ್ನಿಂದ ಪದಗಳನ್ನು. ಇದನ್ನು ನಾವು ಅರ್ಥ ಮಾಡಿಕೊಂಡ್ರೆ ಸುಲಭವಾಗಿ ಬಯಾಲಜಿನ ಕಲಿಬೋದು. ಅದಕ್ಕೆ ನಾನು ಹೇಳೋದೇನು ನಿಮಗೆ, ನೀವು ಬಯಾಲಜಿ ಪಾಠ ಕಲಿಯುವಾಗ ಯಾವುದೇ ಅಧ್ಯಾಯದಲ್ಲಿ ಈ ಥರ ಟೆಕ್ನಿಕಲ್ ವರ್ಡ್ಸ್ ಯಾವುದು ಬರುತ್ತೆ, ವೈಜ್ಞಾನಿಕ ಪದಗಳು ಯಾವುದು ಬರುತ್ತೆ, ತಾಂತ್ರಿಕ ಪದಗಳು ಯಾವುದು ಬರುತ್ತೆ, ನಿಮ್ಮ ನೋಟ್ಬುಕ್ಕಲ್ಲಿ ಕೊನೆಯ ಪೇಜ್ನಲ್ಲಿ, ಕೊನೆಯ 2-3 ಪೇಜ್ನಲ್ಲಿ ಈ ಟೆಕ್ನಿಕಲ್ ಪದಗಳನ್ನು ಪಟ್ಟಿ ಮಾಡ್ಕೋತಾ ಹೋಗಿ. ಚಾಪ್ಟರ್ 1ನಲ್ಲಿ ಎಷ್ಟು ಟೆಕ್ನಿಕಲ್ ಪದ ಬಂತು, ಚಾಪ್ಟರ್ 2ನಲ್ಲಿ ಎಷ್ಟು ಬಂತು ಮಾಡ್ಕೋತಾ ಹೋಗಿ. ಎಲ್ಲ ಪುಸ್ತಕದ ಅಂಗಡಿನಲ್ಲಿ ಸಿಗುತ್ತೆ. ಡಿಕ್ಷನರಿ ಆಫ್ ಬಯಾಲಜಿ ಅಂತ ಒಂದು ಪುಸ್ತಕ ಸಿಗುತ್ತೆ. ಡಿಕ್ಷನರಿ ಆಫ್ ಬಯಾಲಜಿ ಅಂತ. ಬಯಾಲಜಿಗೆ ಒಂದು ಡಿಕ್ಷನರಿ ಇದೆ. ಆ ಡಿಕ್ಷನರಿ ಆಫ್ ಬಯಾಲಜಿ ಪುಸ್ತಕ ತಗೊಳ್ಳಿ. ನೀವು ಪಟ್ಟಿ ಮಾಡ್ಕೊಂಡಿರೋ ಪದಗಳಿಗೆ ಅರ್ಥ ಏನು ಅಂತ ಹುಡುಕಿ ಅದರಲ್ಲಿ ಪಕ್ಕದಲ್ಲಿ ಬರ್ಕೊಳ್ಳಿ. ಆ ಪದಗಳಿಗೆ ಅರ್ಥ ಬರ್ಕೊಳ್ಳಿ. ಆವಾಗ ನಿಮ್ಮ ಪಠ್ಯ ಪುಸ್ತಕದಲ್ಲಿ ಬಯಾಲಜಿಯ ಅಧ್ಯಾಯಗಳಲ್ಲಿ ಇರುವಂಥ ಎಲ್ಲ ಟೆಕ್ನಿಕಲ್ ಪದಗಳಿಗೆ ನಿಮ್ಮದೇ ಆದಂಥ ಒಂದು ಡಿಕ್ಷನರಿ ಸಿಕ್ಕಿದೆ. ನಿಮ್ಮದೇ ಆದಂಥ ಒಂದು ಡಿಕ್ಷನರಿನ ನೀವು ಮಾಡ್ಕೊಂಡಿದ್ದೀರಾ. ನೀವು ಅಧ್ಯಯನ ಮಾಡುವಾಗ ಈ ಡಿಕ್ಷನರಿ ನಿಮಗೆ ತುಂಬ ಸುಲಭ ಆಗುತ್ತೆ. ಇದನ್ನು ಮಾಡಿದ್ರೆ ಬಯಾಲಜಿನ ನೀವು ತುಂಬ ಇಷ್ಟಪಡೋದಕ್ಕೆ ಶುರು ಮಾಡ್ತೀರಾ. ಆಮೇಲೆ ನೀವೇ ಹುಡುಕ್ತೀರಾ. ಒಂದು ಮನೆಯಲ್ಲಿ ಒಂದು ಜಿರಳೆ ಕಾಣಿಸಿದ್ರೆ ಇದ್ರ ಸೈಂಟಿಫಿಕ್ ನೇಮ್ ಏನಿರ್ಬೋದು, ಇದಕ್ಕೆ ಆ ಸೈಂಟಿಫಿಕ್ ನೇಮ್ ಯಾಕೆ ಬಂತು? ಕುತೂಹಲ. ಎಲ್ಲಿ ಕುತೂಹಲ ಇದೆಯೋ ಅಲ್ಲಿ ವಿಜ್ಞಾನ ಬೆಳೆಯುತ್ತೆ. ಸೊ ಇದನ್ನು ಮಾಡಿ ನೋಡಿ, ಖಂಡಿತವಾಗೂ ನಿಮಗೆ ಬಯಾಲಜಿ ಸುಲಭ ಆಗುತ್ತೆ. ಇನ್ನೊಂದು ಚಿತ್ರಗಳು, ಅದೇನು ಮಾಡೋದಕ್ಕೆ ಸಾಧ್ಯವಿಲ್ಲ. ಬಯಾಲಜಿನಲ್ಲಿ ಚಿತ್ರ ಕಲೀಲೇಬೇಕು ನೀವು. ಕಲೀಲೇಬೇಕು. ಎಲ್ಲ ಪಠ್ಯಪುಸ್ತಕದಲ್ಲಿರೋ ಎಲ್ಲ ಚಿತ್ರಗಳನ್ನು ಕಲೀರಿ ಅಂತ ಯಾರು ಹೇಳಲ್ಲ ನಿಮಗೆ. ಪರೀಕ್ಷೆಗೆ ಇಂತಿಷ್ಟು ಚಿತ್ರಗಳು ಅಂತ ನಿಗದಿಪಡಿಸಿರ್ತಾರೆ. ಇಷ್ಟು ಚಿತ್ರಗಳನ್ನು ನೀವು ನೋಡ್ಕೋಬೇಕು ಅಂತ. ಅದಷ್ಟು ಚಿತ್ರಗಳನ್ನು ಚೆನ್ನಾಗಿ ಪ್ರಾಕ್ಟೀಸ್ ಮಾಡಿ. ನೀವು ಓದೋ ಕೋಣೆಯಲ್ಲಿ ಶಾರುಖ್ ಖಾನ್ದೋ ಇನ್ಯಾರದ್ದೋ ಫೋಟೋಗಳು ಹಾಕ್ಕೊಳ್ಳೋದ್ರ ಬದಲು ನಿಮ್ಮ ಬಯಾಲಜಿ ಚಿತ್ರಗಳನ್ನು ಬರೆದು ತಗಲಾಕ್ಕೊಡಿ. ನೋಡಿ ಇದರ ಪರಿಣಾಮ ಹೆಂಗಾಗುತ್ತೆ ಅಂತ. ದಿನ ಮಲಗಕ್ಕೆ ಮುಂಚೆ ಬೆಳಿಗ್ಗೆ ಎದ್ದ ಮೇಲೆ ಆ ಬಯಾಲಜಿ ಚಿತ್ರಗಳನ್ನು ನೋಡಿ. ನೀವು ತಗಲಾಕಿರೋ ಒಂದು 10-12 ಚಿತ್ರಗಳನ್ನು ಬರೆದು ತಗಲಾಕಿರ್ತೀರ. ಒಂದು A4 ಶೀಟ್ನಲ್ಲಿ ದೊಡ್ಡದಾಗಿ ಬರೀರಿ. ಪಾರ್ಟ್ಸ್ ಎಲ್ಲ ಲೇಬಲ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಪಾರ್ಟ್ಸ್ ಎಲ್ಲ ಅದನ್ನು ಚೆನ್ನಾಗಿ ಲೇಬಲ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಅದನ್ನು ನೀಟಾಗಿ ಗೋಡೆಗೆ ತಗಲಾಕಿ. ದಿನ ನೋಡಿ. ಇದನ್ನು ಮಾಡೋಕ್ಕೆ ಶುರು ಮಾಡಿದ್ರೆ ನಿಮಗೆ ಆ ಚಿತ್ರ ನಿಮ್ಮ ತಲೆಯಿಂದ ಹೋಗೋದೇ ಇಲ್ಲ. ಎಷ್ಟರ ಮಟ್ಟಿಗೆ ಅದು ನಿಮ್ಮ ಮೆದುಳಿನಲ್ಲಿ ಪ್ರಿಂಟ್ ಆಗೋಗ್ಬಿಟ್ಟಿರುತ್ತೆ ಅಂದರೆ, ಪರೀಕ್ಷೆಯಲ್ಲಿ ಆ ಚಿತ್ರ ಕೇಳಿದ್ರೆ ಸುಲಭವಾಗಿ ಖುಷಿಯಿಂದ ಆ ಚಿತ್ರ ಬರೀತೀರ. ಅದರ ಭಾಗಗಳನ್ನು ಗುರುತಿಸ್ತೀರ. ಸರಿಯಾಗಿ ಚಿತ್ರ ಬರೆದು ಭಾಗಗಳನ್ನು ಗುರುತಿಸಿದ್ರೆ ಪೂರ್ತಿ ಅಂಕ ಬರುತ್ತೆ, ನಿಮಗೆ ಗೊತ್ತಿದೆ. ಹೌದಾ? ಸೊ ಬಯಾಲಜಿನಲ್ಲಿರೋ 2 ಸಮಸ್ಯೆಗಳು, ಒಂದು ಚಿತ್ರ ಬರೆಯೋದು, ಎರಡನೇದು ತಾಂತ್ರಿಕ ಪದಗಳನ್ನು ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳೋದು. ಇವೆರಡು ಸಮಸ್ಯೆಗಳಿಗೆ ಸುಲಭವಾದಂಥ ಪರಿಹಾರವನ್ನು ನಾನಿವತ್ತು ಸೂಚಿಸಿದ್ದೀನಿ. ಇದನ್ನು ಗಮನದಲ್ಲಿಟ್ಕೊಂಡು ನೀವು ಪಾಲಿಸಿದರೆ, ನಾನು ಆಗಲೇ ಹೇಳಿದಾಗೆ ಬಯಾಲಜಿನ ಇನ್ನು ಮುಂದೆ ನೀವು ತುಂಬ ಇಷ್ಟಪಡೋದಕ್ಕೆ ಶುರು ಮಾಡ್ತೀರ. ಯಾಕೆ ಬಯಾಲಜಿನ ಇಷ್ಟಪಡಬೇಕು? ಯಾಕೆ ಇಷ್ಟಪಡಬೇಕು ಅಂದರೆ, ಒಂದು, ನಮಗೆ ಸುತ್ತಮುತ್ತ ಇರುವಂಥ ಜೀವಿಗಳನ್ನು ಪರಿಚಯ ಮಾಡಿಸುತ್ತೆ ಬಯಾಲಜಿ. ಇಟ್ ಹೆಲ್ಪ್ಸ್ us to understand all living organisms in and around our environment. ಇದು ಬಹಳ ಮುಖ್ಯ. ಎರಡನೇದು, it helps us to understand the relationship between these variety of living organisms. ವಿವಿಧ ಸಸ್ಯಗಳ, ವಿವಿಧ ಪ್ರಾಣಿಗಳ, ವಿವಿಧ ಸೂಕ್ಷ್ಮ ಜೀವಿಗಳ ನಡುವೆ ಇರುವ ಸೂಕ್ಷ್ಮ ಸಂಬಂಧವನ್ನು ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳೋದಕ್ಕೆ ನಮಗೆ ಸಹಾಯ ಮಾಡುತ್ತೆ. ನಿಮಗೆ ಬಯಾಲಜಿಯಲ್ಲಿ ಕಾಡುವಷ್ಟು ಕುತೂಹಲದ ಪ್ರಶ್ನೆಗಳು ಬಹುಶಃ ಬೇರೆ ಯಾವ ಸಬ್ಜೆಕ್ಟ್ನಲ್ಲೂ ಬರೋದಿಲ್ಲ. ವಿಜ್ಞಾನ ಕಲಿಬೇಕಾದ್ರೆ ನಿಮಗೆ ನಿಮ್ಮ ಮನಸ್ಸಿನಲ್ಲಿ ಏನು, ಯಾಕೆ, ಎಲ್ಲಿ, ಹೇಗೆ, ಈ ಥರದ ಪ್ರಶ್ನೆಗಳು ನಿಮ್ಮ ಮನಸ್ಸಿನಲ್ಲಿ ಹುಟ್ಟಬೇಕು. ಅದು ಹುಟ್ಟಿದಾಗಲೇ ನಿಮಗೆ ಅದನ್ನು ಹೆಚ್ಚು ಹೆಚ್ಚು ಅರ್ಥ ಮಾಡಿಕೊಳ್ಳುವಂಥ ಒಂದು ಪ್ರವೃತ್ತಿ ಪ್ರಾರಂಭ ಆಗುತ್ತೆ. ಹಾಗಾಗಿ ಈಗ ಉದಾಹರಣೆಗೆ ಸಸ್ಯಗಳನ್ನು ತಗೊಳ್ಳಿ. ಸಸ್ಯಗಳಷ್ಟು ಪರೋಪಕಾರಿ ಜೀವಿಗಳು ಬೇರೆ ಯಾವುದೂ ಇಲ್ಲ. ಒಂದು ಸಸ್ಯ ತನಗೋಸ್ಕರ ಬದುಕೋದಿಲ್ಲ, ಅದು ಬದುಕೋದೇ ಇತರ ಜೀವಿಗಳಿಗೆ. ಎಷ್ಟು ಅನುಕೂಲಗಳಿದೆ ಒಂದು ಸಸ್ಯದಿಂದ ನಿಮಗೆ ಗೊತ್ತಿದೆ. ಸಸ್ಯಗಳು ಕಾರ್ಬನ್ ಡೈಆಕ್ಸೈಡನ್ನು ಹೀರಿಕೊಂಡು, ಕಾರ್ಬನ್ ಡೈಆಕ್ಸೈಡ್ ಅನ್ನೋದು ಒಂದು ವಿಷಯುಕ್ತವಾದಂಥ ಅನಿಲ. ನಾವು ಆಕ್ಸಿಜನ್ನ ಒಳಗಡೆ ತಗೊಳ್ತೀವಿ, ಕಾರ್ಬನ್ ಡೈಆಕ್ಸೈಡನ್ನು ಹೊರಗಡೆ ಹಾಕ್ತೀವಿ. ಯಾಕೆ ಆಕ್ಸಿಜನನ್ನು ಒಳಗಡೆ ತಗೋತೀವಿ? ಉಸಿರಾಟಕ್ಕೆ ಬೇಕದು, ನಮಗೆ ಶಕ್ತಿ ಕೊಡೋದಕ್ಕೆ ಆಕ್ಸಿಜನ್ ಬೇಕು. ಕಾರ್ಬನ್ ಡೈಆಕ್ಸೈಡ್ನ ಹೊರಗಡೆ ಹಾಕ್ತೀವಿ. ಯಾಕೆ ಹೊರಗಡೆ ಹಾಕಬೇಕು? ಅದು ಒಳಗಡೆ ಇದ್ದರೆ ವಿಷಯುಕ್ತವಾಗುತ್ತೆ, ಅದಕ್ಕೆ ಅದನ್ನು ನಾವು ಹೊರಗಡೆ ಹಾಕಬೇಕು. ಇದಕ್ಕೆ ನಾವು ಉಸಿರಾಟ ಅಂತ ಕರಿತೀವಿ. ಆಕ್ಸಿಜನ್ನ ಒಳಗೆ ತಗೊಳ್ಳೋದು, ಕಾರ್ಬನ್ ಡೈಆಕ್ಸೈಡ್ನ ಹೊರಗೆ ತಗೊಳ್ಳೋದು. ಸಸ್ಯಗಳು ಈ ಕೆಲಸ ಮಾಡ್ತವೆ, ಅವು ಉಸಿರಾಡ್ತವೆ. ಅದಕ್ಕಿಂತ ಹೆಚ್ಚಾಗಿ ಸಸ್ಯಗಳು ಕಾರ್ಬನ್ ಡೈಆಕ್ಸೈಡನ್ನು ಒಳಗಡೆ ತಗೊಂಡು ಆಕ್ಸಿಜನನ್ನು ಹೊರಗಡೆ ಬರ್ತವೆ. ಎಲ್ಲಾದರೂ ಕೇಳಿದ್ದೀರಾ ವಿಷಯುಕ್ತವಾದ ವಸ್ತುವನ್ನು ದೇಹಕ್ಕೆ ತೆಗೆದುಕೊಂಡು ಅದನ್ನು ಉಪಯುಕ್ತ ವಸ್ತುವಾಗಿ ಪರಿವರ್ತಿಸಿ ಹೊರಗಡೆ ಹಾಕುವಂಥ ಒಂದು ಪ್ರಕ್ರಿಯೆ ಸಸ್ಯಗಳಲ್ಲಿ ಮಾತ್ರ ಇರೋದು. ಅವು ಏನು ಆಕ್ಸಿಜನ್ ಹೊರಗಡೆ ಬಿಟ್ಟಿದ್ದಾವೆ ಅದನ್ನು ನಾವೆಲ್ಲರೂ ಉಸಿರಾಡ್ತಾ ಇದ್ದೀವಿ. ಅಷ್ಟೇ ಅಲ್ಲ, ಸಸ್ಯಗಳು ಬಹುತೇಕ ಪ್ರಾಣಿಗಳಿಗೆ, ಮನುಷ್ಯರಿಗೆ ಸಸ್ಯಗಳು ಆಹಾರ ಒದಗಿಸ್ತವೆ. ಸೊ ಆಕ್ಸಿಜನ್ ಒದಗಿಸ್ತವೆ, ಆಹಾರ ಒದಗಿಸ್ತವೆ. ಔಷಧೀಯ ಸಸ್ಯಗಳ ಬಗ್ಗೆ ನೀವು ಕೇಳಿದಿರಿ. ಎಷ್ಟೊಂದು ಸಸ್ಯಗಳಿಂದ ನಾವು ಔಷಧಿ ಪಡಿತೀವಿ. ನಾವೆಲ್ಲರೂ ಮನೆ ಹತ್ರ ಒಂದು ತುಳಸಿ ಗಿಡನ ಸಾಕ್ತೀವಿ. ಪರಂಪರೆಯಿಂದ ಬಂದಿದೆ ಪದ್ಧತಿ ಇದು. ಮನೆ ಮುಂದೆ ಒಂದು ತುಳಸಿ ಗಿಡ ಇರಬೇಕು ಅಂತ. ಯಾಕೆ ಅಂತ ನಿಮ್ಮ ತಾಯಿ ಅಥವಾ ನಿಮ್ಮ ಅಜ್ಜಿ ಇದ್ರೆ ಕೇಳಿ ನೋಡಿ. ತುಳಸಿ ಗಿಡ ತುಂಬ ಒಳ್ಳೆಯದು, ಅದಕ್ಕೆ ದೇವರ ಸಮಾನವಾದ ಪಟ್ಟವನ್ನು ಕೊಡ್ತೀವಿ ನಾವು. ಅದಕ್ಕಿಂತ ಮುಖ್ಯವಾಗಿ ನಾವು ತಿಳ್ಕೋಬೇಕಾದೇನು, ತುಳಸಿ ಗಿಡಕ್ಕೆ ಸೊಳ್ಳೆ ಮತ್ತಿತರ ಹಾನಿಕಾರಕ ಕೀಟಗಳನ್ನು ದೂರ ಇಡುವಂಥ ಸಾಮರ್ಥ್ಯ ಇದೆ. ಸೊ ಮನೆಯ ಮುಂದೆ ಒಂದು ತುಳಸಿ ಗಿಡ ಇದ್ದರೆ ಸೊಳ್ಳೆಗಳ ಕಾಟ ಸಾಕಷ್ಟು ಕಡಿಮೆ ಆಗುತ್ತೆ. ಅದೊಂದೇ ಅಲ್ಲ, ತುಳಸಿ ಗಿಡಕ್ಕೆ ಸುಮಾರು 30 ಔಷಧೀಯ ವಸ್ತುಗಳನ್ನು ಒಳಗೊಂಡಿದೆ. ಅದು ವಿಶೇಷವಾಗಿ ಉಸಿರಾಟಕ್ಕೆ ಸಂಬಂಧಪಟ್ಟಂಥ ಸಮಸ್ಯೆಗಳನ್ನು ದೂರ ಮಾಡೋದಕ್ಕೆ ಯಾವುದೇ ಆಯುರ್ವೇದಿಕ್ ಕಾಫ್ ಸಿರಪ್ ತಗೊಳ್ಳಿ ನೀವು, ಅದರಲ್ಲಿ ತುಳಸಿ ಇದ್ದೇ ಇರುತ್ತೆ. ಡೈಜೆಷನ್, ಜೀರ್ಣಕ್ಕೆ ತುಳಸಿ ಒಳ್ಳೆಯದು. ಅಂದರೆ ಹಿಂದಿನವರಿಗೆ ಹೆಚ್ಚಿನ ವೈಜ್ಞಾನಿಕ ಚಿಂತನೆ ಇಲ್ಲದೇ ಇದ್ದರೂ ಕೂಡ ಉಪಯುಕ್ತತೆಯನ್ನು ಅವರು ಕಂಡುಕೊಂಡಿದ್ದರು. ಅದಕ್ಕೋಸ್ಕರ ಒಂದು ಗೌರವಯುತ ಸ್ಥಾನವನ್ನು ಕೊಟ್ಟರು. ಅದರಲ್ಲಿ ಏನೇನು ಪ್ರಯೋಜನ ಇದೆ ಅಂತ ಹೇಳೋದಕ್ಕಿಂತ ಹೆಚ್ಚಾಗಿ ದೇವರ ರೀತಿಯಲ್ಲಿ ಅದನ್ನು ಪೂಜಿಸಿದ್ರು. ಸಂಪ್ರದಾಯ ಬೆಳ್ಕೊಂಡು ಬಂತು. ಇವತ್ತು ವಿಜ್ಞಾನ ನಮಗೇನು ಹೇಳ್ತಾ ಇದೆ, ತುಳಸಿ ಗಿಡದಲ್ಲಿ ಎಷ್ಟು ಪ್ರಯೋಜನ ಇದೆ ಅಂತ ಗೊತ್ತಾಗಿದೆ. ಅಶ್ವತ್ಥ ಮರದಲ್ಲಿ ಅದು ಒಂದು ದಿನಕ್ಕೆ ಎಷ್ಟು ಕಾರ್ಬನ್ ಡೈಆಕ್ಸೈಡನ್ನು ತೆಗೆದುಕೊಳ್ಳುತ್ತೋ ಅದರ 2ರಷ್ಟು ಆಕ್ಸಿಜನನ್ನು ಹೊರಗಡೆ ಹಾಕುತ್ತೆ. 2 times ದಿ ಕ್ವಾಂಟಿಟಿ ಆಫ್ ಕಾರ್ಬನ್ ಡೈಆಕ್ಸೈಡ್. ಅದಕ್ಕೋಸ್ಕರ ನೋಡಿ, ಹಿಂದಿನಿಂದಲೂ ಕೂಡ ನಮ್ಮ ಸಂಪ್ರದಾಯದಲ್ಲಿ ನಾವೊಂದು ಹಳ್ಳಿಯ ಒಳಗಡೆ ಪ್ರವೇಶ ಮಾಡ್ತಾ ಇದ್ದ ಹಾಗೆ ಮೊದಲು ನಾವು ನೋಡ್ತಾ ಇದ್ದಿದ್ದು ಅಲ್ಲೊಂದು ಅರಳಿಕಟ್ಟೆ, ಅಶ್ವತ್ಥ ಕಟ್ಟೆ, ಅಲ್ಲಿ ಕಲ್ಲು ಬೆಂಚುಗಳು, ಹತ್ತಿರದಲ್ಲೊಂದು ದೇವಸ್ಥಾನ. ಎಂಥ ವಾತಾವರಣ ನೋಡಿ. ಯಾಕೆ ಅರಳಿಕಟ್ಟೆ? ಅಲ್ಲಿ ಕೂತ್ಕೊಂಡು ಪ್ರಯಾಣ ಮಾಡಿ ಬಂದಾಗ ನಿಮಗೆ ಸುಸ್ತಾದರೆ ಅಲ್ಲಿ ಕೂತ್ಕೊಂಡು ಉಸಿರಾಡಿದ್ರೆ ನಿಮಗೆ ಆಕ್ಸಿಜನ್ ಜಾಸ್ತಿ ಸಿಗುತ್ತೆ, ಮನಸ್ಸಿಗೆ ನೆಮ್ಮದಿ ಸಿಗುತ್ತೆ. ಹತ್ತಿರದಲ್ಲಿ ದೇವಸ್ಥಾನ ಇರೋದ್ರಿಂದ ಒಂದು ದೈವಿಕ ವಾತಾವರಣ ಸಿಗುತ್ತೆ. ಇವನ್ನೆಲ್ಲ ಸುಮ್ಮನೆ ನಾವು ಹಿಂದಿನವರು ಯೋಚನೆ ಮಾಡಲಿಲ್ಲ. ಎಲ್ಲದರಲ್ಲೂ ಕೂಡ ಪ್ರಯೋಜನ ಇದೆ ಅನ್ನೋದನ್ನು ಕಂಡುಕೊಂಡಿದ್ದರು ಅವರು. ಹಾಗಾಗಿ ಸಸ್ಯಗಳು ಅತ್ಯಂತ ಪರೋಪಕಾರಿ ಜೀವಿಗಳು. ಪ್ರಾಣಿಗಳನ್ನು ತಗೊಳ್ಳಿ, ಬಹಳಷ್ಟು ಇವತ್ತಿನ ವಿಜ್ಞಾನ ಏನು ಕಂಡುಕೊಂಡಿದೆ ಅದಕ್ಕೆಲ್ಲ ಪ್ರಾಣಿಗಳೇ ಮೂಲ ಕಾರಣ. ಮನುಷ್ಯ ನೀರಿನಲ್ಲಿ ಈಜೋದನ್ನು ಕಲಿತಿದ್ದೇ ಮೀನುಗಳನ್ನು ನೋಡ್ಬಿಟ್ಟು. ಸಬ್ಮೆರೀನ್ ಮುಂತಾದ ನೀರಿನಲ್ಲಿ ಓಡಾಡುವಂಥ ವಾಹನಗಳಿದೆಯಲ್ಲ, ಅವುಗಳು ಕೆಲಸ ಮಾಡೋದ್ರ ಆಧಾರ ಯಾವುದು? ಅದಕ್ಕೆ ಹೈಡ್ರೋಡೈನಮಿಕ್ಸ್ ಅಂತ ಕರಿತೀವಿ ನಾವು ಫಿಸಿಕ್ಸ್ನಲ್ಲಿ. ಆ ಹೈಡ್ರೋಡೈನಮಿಕ್ಸನ್ನು ನಾವು ಎಲ್ಲಿ ನೋಡ್ತೀವಿ? ಮೀನುಗಳಲ್ಲಿ ನೋಡ್ತೀವಿ. ಏರೋಪ್ಲೇನ್ ಮೇಲ್ ಹಾರುತ್ತಲ್ಲ, ಅದರ ಹಿಂದಿನ ತಂತ್ರಜ್ಞಾನ ನಮಗೆ ಎಲ್ಲಿಂದ ಬಂದಿದೆ? ಹಕ್ಕಿಗಳಿಂದ ಬಂದಿದೆ. ರಾಡಾರ್ ತಂತ್ರಜ್ಞಾನ ಎಲ್ಲಿಂದ ಬಂದಿದೆ? ಬಾವಲಿಗಳು ಅಂತ ಕೇಳಿದಿರ ನೀವು? ರಾತ್ರಿ ಹೊತ್ತು ತುಂಬ ಚಟುವಟಿಕೆಯಿಂದ ಇರುವಂಥ ಪ್ರಾಣಿಗಳು ಹಗಲೊತ್ತು ತುಂಬ ನಿದ್ರೆ ಮಾಡ್ತಾ ಇರ್ತವೆ. ಆ ಬಾವಲಿಗಳಲ್ಲಿ ಒಂದು ವಿಶಿಷ್ಟವಾದಂಥ ಸಾಮರ್ಥ್ಯ ಇದೆ. ರಾತ್ರಿ ಅವು ಹಾರಕ್ಕೆ ಹೊರಟಾಗ ಶಬ್ದಗಳನ್ನು ಉತ್ಪತ್ತಿ ಮಾಡ್ತವೆ, ವಿಶಿಷ್ಟವಾದ ಶಬ್ದಗಳನ್ನು. ನಮಗೆ ಕೇಳಿಸಲ್ಲ, ನಮ್ಮ ಕಿವಿ ಕೇಳಿಸಲ್ಲ. ನಮ್ಮ ಕಿವಿ ಕೇಳಿಸಲ್ಲ. ಆ ವಿಶಿಷ್ಟವಾದ ಶಬ್ದ ಎದುರುಗಡೆ ಯಾವುದಾದ್ರೂ ಒಂದು ತಡೆಗೆ ಹೊಡೆದ್ರೆ ಅವಕ್ಕೆ ಪ್ರತಿಧ್ವನಿ ಬರುತ್ತೆ. ಆ ಪ್ರತಿಧ್ವನಿ ಬಂದರೆ ಅಲ್ಲೇನೋ ತಡೆ ಇದೆ ಅಂಥೇಳಿ ಅವು ಮಾರ್ಗ ಬದಲಾಯಿಸ್ತವೆ. ಇದೇ ತಂತ್ರಜ್ಞಾನವನ್ನು ಅಳವಡಿಸಿ ನಾವು ಇವತ್ತು ರಾಡಾರ್ನ ಕಂಡುಕೊಂಡಿದ್ದೀವಿ. ನೀವು ಇರುವೆಗಳು ನೋಡಿದ್ದೀರಾ, ಜೇನುನೊಣ ನೋಡಿದ್ದೀರಾ, ಅವುಗಳಲ್ಲೆಲ್ಲ ಸಮಾಜ ಜೀವನ ಅಂತ ನೋಡ್ತೀವಿ, ಸೋಷಿಯಲ್ ಲೈಫ್ ಅಂತ ನೋಡ್ತೀವಿ. ಸಾವಿರಾರು ಜೀವಿಗಳು ಒಟ್ಟಿಗೆ ಜೀವನ ನಡೆಸ್ತವೆ. ಒಂದು ಇರುವೆ ಗೂಡಿನಲ್ಲಿ ಸುಮಾರು 50,000ದಿಂದ 80,000 ಇರುವೆಗಳು ಒಟ್ಟಿಗೆ ಇರ್ತವೆ. ಅದರಲ್ಲಿ ರಾಣಿ ಇರುವೆ ಇದೆ, ರಾಜ ಇರುವೆ ಇದೆ, ಕೆಲಸಗಾರ ಇರುವೆ ಇದೆ, ಸೈನಿಕ ಇರುವೆ ಇದೆ. ಅಂದರೆ 4 ಬಗೆಯ ಇರುವೆಗಳಿರ್ತವೆ. ರಾಜ ಮತ್ತು ರಾಣಿ ಇರುವೆಗಳಿಗೆ ಅಥವಾ ರಾಜ ಮತ್ತು ರಾಣಿ ದುಂಬಿಗಳಿಗೆ ಸಂತಾನೋತ್ಪತ್ತಿ ಮಾಡೋದೊಂದೇ ಕೆಲಸ. ಈ ಸೈನಿಕ ಇರುವೆಗಳಿಗೆ ಮತ್ತು ಕೆಲಸಗಾರ ಇರುವೆಗಳಿಗೆ ರಕ್ಷಣೆ, ಆಹಾರ ಹುಡ್ಕೊಂಬರೋದು ಇತ್ಯಾದಿ ಕೆಲಸ. ಒಟ್ಟಿಗೆ ಇರ್ತವೆ, ಎಷ್ಟು ಚೆನ್ನಾಗಿ ಜೀವನ ನಡೆಸ್ತವೆ, ಸಮಾಜ ಜೀವನ ನಡೆಸ್ತವೆ. ನಾವು ಅವುಗಳಿಂದ ಕಲಿಬೇಕಾದ್ದು ಬೇಕಾದಷ್ಟಿದೆ. ಹೀಗೆ ಸಸ್ಯಗಳ ಉದಾಹರಣೆ, ಪ್ರಾಣಿಗಳ ಉದಾಹರಣೆ ತಗೊಂಡ್ರೆ ನಮಗೆ ಸಾಕಷ್ಟು ಮಾಹಿತಿ ಸಿಗುತ್ತೆ, ಸಾಕಷ್ಟು ಮಾರ್ಗದರ್ಶನ ಸಿಗುತ್ತೆ. ಅದಕ್ಕೋಸ್ಕರನಾದರೂ ನಾವು ಬಯಾಲಜಿನ ಓದಲೇಬೇಕಾಗುತ್ತೆ. ಇನ್ನೊಂದು ಬಹಳ ಮುಖ್ಯವಾದಂಥ ಕಾಂಟ್ರಿಬ್ಯೂಷನ್ ಬಯಾಲಜಿದು ಅಂತಂದರೆ, ನೀವು ಬೇರೆ ಸಬ್ಜೆಕ್ಟ್ಗಳಿಗೆ ಹೋಲಿಸಿದರೆ, ವಿಜ್ಞಾನದ ಇತರ ಶಾಖೆಗಳಿಗೆ ಹೋಲಿಸಿದರೆ, ಬಯಾಲಜಿನಲ್ಲಿ ಬೇರೆ ಸಬ್ಜೆಕ್ಟ್ಗಳಿರುವಷ್ಟು ಬೇರೆ ಸಬ್ಜೆಕ್ಟ್ನಲ್ಲಿ ಬಯಾಲಜಿ ಇಲ್ಲ. ಬಯಾಲಜಿ incorporates several aspects from different branches of science. ಬಯಾಲಜಿನಲ್ಲಿ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಇದೆ, ಗೊತ್ತಾ ನಿಮಗೆ? ಬಯಾಲಜಿನಲ್ಲಿ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಇದೆ. ಆಮೇಲೆ ಬಯಾಲಜಿಯಲ್ಲಿರೋ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ನಲ್ಲಿ ಒಂದು ವಿಶೇಷ ಇದೆ. ಅಕಾರ್ಡಿಂಗ್ ಟು ದಿ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಆಫ್ ಬಯಾಲಜಿ, ಮಲ್ಟಿಪ್ಲಿಕೇಶನ್ ಆ್ಯಂಡ್ ಡಿವಿಷನ್ ಆರ್ ಒನ್ ಆ್ಯಂಡ್ ದಿ ಸೇಮ್. ಸಾಧ್ಯನಾ ಇದು? ಸಾಧ್ಯನಾ? ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ನಲ್ಲಿ ನೀವೇನು ಹೇಳ್ತೀರಾ, ಮಲ್ಟಿಪ್ಲಿಕೇಶನ್ನೇ ಬೇರೆ, ಡಿವಿಷನ್ನೇ ಬೇರೆ ಅಂತೀವಿ. ಬಯಾಲಜಿನಲ್ಲಿ ಎಕ್ಸಾಂಪಲ್ ನೋಡಿ, ಒಂದು ಎಕ್ಸಾಂಪಲ್ ಕೊಡ್ತೀನಿ. ಅಮೀಬಾ ತಗೊಳ್ಳಿ. ಅಮೀಬಾ, ಒಂದು ಅಮೀಬಾ ಇದ್ದಿದ್ದು ಸ್ವಲ್ಪ ಹೊತ್ತಾದಮೇಲೆ 2 ಅಮೀಬಾ ಆಗುತ್ತೆ. ಅದು ಸಂತಾನೋತ್ಪತ್ತಿ ಮಾಡುವ ವಿಧಾನ. ಅದನ್ನು ಹೇಳುವಾಗ ನಾವೇನು ಹೇಳ್ತೀವಿ? ಅಮೀಬಾ ಮಲ್ಟಿಪ್ಲೈಸ್ ಇಂಟು 2. ಹೌದಾ? ಹೇಳ್ತೀವಲ್ವ? ಹಾಗೆಯೇ ಅಮೀಬಾ ಡಿವೈಡ್ಸ್ ಇಂಟು 2 ಅಂತೀವಿ. ಸೊ ಇನ್ ಬಯಾಲಜಿ, ಡಿವಿಷನ್ ಆ್ಯಂಡ್ ಮಲ್ಟಿಪ್ಲಿಕೇಶನ್ ಆರ್ ದಿ ಸೇಮ್. ಇನ್ನೊಂದು ನಿಮಗೆ ತುಂಬ ಇಂಟ್ರೆಸ್ಟಿಂಗು ಬಯಾಲಜಿನಲ್ಲಿ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಇರೋದಕ್ಕೆ, ಎತ್ತರವಾಗಿ ಬೆಳೆದಿರೋ ಮರಗಳಿರೋ ಕಡೆ ಹೋಗಿ ಅದರ ಪಕ್ಕದಲ್ಲಿ ಯಾವುದಾದ್ರೂ ಒಂದು ಅಪಾರ್ಟ್ಮೆಂಟ್ ಇದ್ದರೆ, ಆ ಮರದ ಎತ್ತರಕ್ಕಿಂತ ಮೇಲ್ಗಡೆ ಇರೋ ಒಂದು ಫ್ಲೋರ್ನಿಂದ ಕೆಳಗಡೆ ಮರಗಳನ್ನು ಬಗ್ಗಿ ನೋಡಿ, ಮಾಡಿ ನೋಡಿ, ಇದನ್ನು ಬಗ್ಗಿ ನೋಡಿ. ಏನು ನೋಡ್ತೀರಾ? ಆ ಮರಗಳ ಶಾಖೆಗಳು ಕಾಣುತ್ತೆ ನಿಮಗೆ, ಬ್ರಾಂಚಸ್ ಆಫ್ ದಿ ಟ್ರೀ ಕಾಣುತ್ತೆ. ನೀವು ಗಮನಿಸಿ ನೋಡಿ, ಆ ಶಾಖೆಗಳನ್ನು ನೋಡಿದಾಗ ನಿಮಗೆ ಆಶ್ಚರ್ಯ ಆಗುತ್ತೆ. ಅವುಗಳೆಲ್ಲ ಒಂದು ಸರಿಯಾದ ಒಂದು ಆರ್ಡರ್ನಲ್ಲಿ ಅರೇಂಜ್ ಆಗಿರೋದು ಕಾಣಿಸುತ್ತೆ. ಅಂದರೆ ಶಾಖೆಗಳು ಒಡೆದಿರೋದಿದೆಯಲ್ಲ, ಅವುಗಳಲ್ಲಿ ನೀವು ಒಂದು ಸೌಂದರ್ಯನ ಗಮನಿಸ್ತೀರ. ನೀವು ಅದನ್ನು ಒಂದು ಶಾಖೆಗೂ ಇನ್ನೊಂದು ಶಾಖೆಗೂ, ಒಂದು ಬ್ರ್ಯಾಂಚ್ಗೂ ಇನ್ನೊಂದು ಬ್ರ್ಯಾಂಚ್ಗೂ ಮಧ್ಯೆ ಆ್ಯಂಗಲ್ ಇದೆಯಲ್ಲ, ಕೋನ, ಈ ಮಧ್ಯೆ ಆ್ಯಂಗಲನ್ನು ನೀವು ಅಳೆದರೆ ಅದು ಸರಿಯಾಗಿ 137 ಡಿಗ್ರಿ ಇರುತ್ತೆ, 137 ಡಿಗ್ರೀಸ್. ಯಾವುದೇ ಮರ, ಯಾವುದೇ ಬ್ರಾಂಚ್, ದಿ ಆ್ಯಂಗಲ್ ಬಿಟ್ವೀನ್ ಬ್ರಾಂಚಸ್ ವಿಲ್ ಬಿ 137. ಇದಕ್ಕೆ ಗೋಲ್ಡನ್ ಆ್ಯಂಗಲ್ ಅಂತ ಕರೀತಾರೆ. ಸುವರ್ಣ ಕೋನ ಅಂತ ಕರೀತಾರೆ, ಗೋಲ್ಡನ್ ಆ್ಯಂಗಲ್ ಅಂತ. ಇದು ಯಾಕೆ ಅಂದರೆ ಆ ಆ್ಯಂಗಲ್ ಅಷ್ಟಿದ್ದರೆ ಈ ಬ್ರಾಂಚ್ ಮೇಲೂ ಕೂಡ ಸೂರ್ಯನ ಬೆಳಕು ಬೀಳುತ್ತೆ, ಈ ಬ್ರಾಂಚ್ ಮೇಲೂ ಕೂಡ ಸರಿಯಾಗಿ ಸೂರ್ಯನ ಬೆಳಕು ಬೀಳುತ್ತೆ. ಈ ಆ್ಯಂಗಲ್ ಸ್ವಲ್ಪ ಹೆಚ್ಚು ಕಮ್ಮಿ ಆದರೂ ಕೂಡ ಕೆಲವು ಬ್ರಾಂಚಸ್ಗೆ ಸನ್ಲೈಟ್ ಬೀಳೋದಿಲ್ಲ. ಸನ್ಲೈಟ್ ಬೀಳದೆ ಹೋದರೆ ಅವಕ್ಕೆ ದ್ಯುತಿ ಸಂಶ್ಲೇಷಣೆ, ಫೋಟೋಸಿಂಥಸಿಸ್ ಮಾಡೋದಕ್ಕೆ ಸಾಧ್ಯವಾಗೋದಿಲ್ಲ, ಆಹಾರ ಉತ್ಪತ್ತಿ ಮಾಡೋದಕ್ಕೆ ಸಾಧ್ಯವಾಗೋದಿಲ್ಲ. ಅಂದರೆ ನಮಗಿಂತ ಚೆನ್ನಾಗಿ ಮ್ಯಾಥಮೆಟಿಕ್ಸನ್ನು ಯಾರು ಅರ್ಥ ಮಾಡ್ಕೊಂಡಿರೋದು? ಪ್ಲಾಂಟ್ಸ್. ದೇ ಹ್ಯಾವ್ ಅಂಡರ್ಸ್ಟುಡ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಬೆಟರ್ ದ್ಯಾನ್ ಅಸ್. ನಮ್ಮದೇ ಹ್ಯೂಮನ್ ಬಾಡಿ ಎಕ್ಸಾಂಪಲ್ ತಗೊಳ್ಳಿ. ನಮ್ಮ ಹ್ಯೂಮನ್ ಬಾಡಿನಲ್ಲಿ ಎಷ್ಟೊಂದು, ಈಗ ನಾ ಹೇಳಿದ್ನಲ್ಲ ಈ ಗೋಲ್ಡನ್ ಆ್ಯಂಗಲ್, ಅದಕ್ಕೆ ಸಂಬಂಧಪಟ್ಟ ಹಾಗೆ ಇನ್ನೊಂದು ಕಾನ್ಸೆಪ್ಟ್ ಇದೆ, ಅದನ್ನು ಗೋಲ್ಡನ್ ರೂಲ್ ಅಂತ ಕರಿತೀವಿ. ಈಗ ಈ ಕೈ ತಗೊಳ್ಳಿ, ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ, ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ, ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಎಷ್ಟು ಉದ್ದ ಇದೆ, ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಎಷ್ಟು ಉದ್ದ ಇದೆ ಅಂತ ಅಳೆದ್ಬಿಟ್ಟು ಮನೆಗೆ ಹೋದ್ಮೇಲೆ ಮಾಡಿ ನೋಡಿ. ಅಳೆದ್ಬಿಟ್ಟು ಅವೆರಡರ ರೇಷಿಯೋ ಎಷ್ಟಿದೆ ಅಂತ ಕಂಡುಹಿಡಿ. ದಿ ರೇಷಿಯೋ ಆಫ್ ದಿಸ್ ಆ್ಯಂಡ್ ದಿಸ್ ಇಟ್ ವಿಲ್ ಬಿ ನಾನು ಹೇಳ್ತೀನಿ ಕೇಳಿ, 1.61. ಅದನ್ನು ಗೋಲ್ಡನ್ ರೇಷಿಯೋ ಅಂತ ಕರಿತೀವಿ. ನಿಮ್ಮ ಮುಖ ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ, ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ರೇಷಿಯೋ ತಗೊಳ್ಳಿ, 1.61 ಇರುತ್ತೆ. ಕಾಲು ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ, ಅಲ್ಲಿಂದ ಕೆಳಗಡೆ ರೇಷಿಯೋ ತಗೊಳ್ಳಿ, 1.61 ಇರುತ್ತೆ. ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ, ಇಲ್ಲಿಂದ ಕಿವಿವರೆಗೆ ರೇಷಿಯೋ ತಗೊಳ್ಳಿ, 1.61 ಇರುತ್ತೆ. ಅಂದರೆ ಹ್ಯೂಮನ್ ಬಾಡಿನಲ್ಲಿ ಬೇರೆ ಬೇರೆ ಅಂಗಗಳು, ಅವುಗಳ ಮೆಷರ್ಮೆಂಟ್ ಏನಿದೆ ಅದರಲ್ಲೂ ಕೂಡ ಒಂದು ಗೋಲ್ಡನ್ ರೇಷಿಯೋ ಇದೆ, ಸುವರ್ಣ ಅನುಪಾತ ಅಂತ ಕರಿತೀವಿ. ಹಾಗೆ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ನಲ್ಲಿ ಎಷ್ಟೊಂದು, ಐ ಮೀನ್ ಬಯಾಲಜಿನಲ್ಲಿ ಎಷ್ಟೊಂದು ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಕಾನ್ಸೆಪ್ಟ್ ಬರುತ್ತೆ. ಬಯಾಲಜಿನಲ್ಲಿ ಫಿಸಿಕ್ಸ್ ಇಲ್ವಾ? ಫೋಟೋಸಿಂಥಸಿಸ್ ತಗೊಳ್ಳಿ, ದ್ಯುತಿ ಸಂಶ್ಲೇಷಣೆ ಆಗುವಾಗ ಕ್ಲೋರೋಫಿಲ್ನಲ್ಲಿ ಎನರ್ಜಿ, ಸೋಲಾರ್ ಎನರ್ಜಿ ಇಸ್ ಕನ್ವರ್ಟೆಡ್ ಇಂಟು ಕೆಮಿಕಲ್ ಎನರ್ಜಿ ಅಂತೀವಿ. ನೀವೆಲ್ಲ ಥರ್ಮೋಡೈನಮಿಕ್ಸ್ ಬಗ್ಗೆ ಕೇಳಿದ್ದೀರಾ. ಎನರ್ಜಿ ಕ್ಯಾನ್ ಬಿ ಕನ್ವರ್ಟೆಡ್ ಫ್ರಮ್ ಒನ್ ಫಾರ್ಮ್ ಇಂಟು ಅನದರ್ ಫಾರ್ಮ್. ಸೊ ಸೋಲಾರ್ ಎನರ್ಜಿ ಇಸ್ ಕನ್ವರ್ಟೆಡ್ ಇಂಟು ಕೆಮಿಕಲ್ ಎನರ್ಜಿ is converted into food energy. So physics ilva, biology nalli physics ide. Chemistry ilva, ಎಷ್ಟು ಕೆಮಿಸ್ಟ್ರಿ ಇದೆ. ವಾಟ್ ಈಸ್ ಡೈಜೆಷನ್? ಡೈಜೆಷನ್ ಅಂದ್ರೇನು? ಆಹಾರ ಜೀರ್ಣವಾಗೋದು ಅಂದ್ರೇನು? ಇಟ್ ಇಸ್ ಎನ್ ಎಂಜೈಮ್ಯಾಟಿಕ್ ಪ್ರಾಸೆಸ್. ಆಹಾರದಲ್ಲಿರುವಂಥ ಸಕ್ಕರೆ ಅಂತ ಹೇಳಿಬಿಟ್ಟು ನನ್ನ ಮಾತನ್ನು ಮುಗಿಸ್ತೀನಿ.
ಡಾಕ್ಟರ್ ಬಾಲಕೃಷ್ಣ ಅಡಿಗ ಸರ್ ನಮ್ಮ ಟೀಚರು. ನನಗೆ ನಮ್ಮ ಡಿಗ್ರಿ ಆ್ಯಂಡ್ ಪಿ ಯು ಕ್ಲಾಸ್ನಲ್ಲಿ ಕೂತ್ಕೊಂಡಾಯಿತು, ಮರ್ತೋಗಿದ್ದೆಲ್ಲ ಮತ್ತೆ ಜ್ಞಾಪಕಕ್ಕೆ ಬಂತು. ಇನ್ಫ್ಯಾಕ್ಟ್ ಸರ್ ಇನ್ಸ್ಪಿರೇಷನಿಂದನೇ ಐ ಬಿಕೇಮ್ ಎ ಫಿಶರೀಸ್ ಸೈಂಟಿಸ್ಟ್. ಸೊ ಆಪ್ಷನ್ಸ್ ಆರ್ ಮೆನಿ. ಸರ್ ಹೇಳ್ದಂಗೆ PCMB ತಗೊಂಡ್ರೆ ಆಪ್ಷನ್ಸ್ ಆರ್ ಮೆನಿ. PCMC ಅಥವಾ PCMCE ತಗೊಂಡ್ರೆ ಆಪ್ಷನ್ಸ್ ಆರ್ ಲಿಮಿಟೆಡ್. ಇನ್ಫ್ಯಾಕ್ಟ್ ಸರ್ ಹೇಳ್ದಂಗೆ ತಮಗೆಲ್ಲ ವೆಂಕಿ ರಾಮಕೃಷ್ಣನ್ ಬಗ್ಗೆ ಗೊತ್ತಲ್ವಾ? ವೆಂಕಟರಾಮಕೃಷ್ಣನ್ ನೊಬೆಲ್ ಲಾರೆಟ್ 2009 ನೊಬೆಲ್ ಪ್ರೈಸ್ ಬಂತು. ಇನ್ಫ್ಯಾಕ್ಟ್ ಅವರು PhD ಮಾಡಿದ್ದು ಫಿಸಿಕ್ಸಲ್ಲಿ. ಫಿಸಿಕ್ಸ್ PhD ಮಾಡಿದ ಮೇಲೆ ಅವ್ರಿಗೆ ಫಿಸಿಕ್ಸ್ ಈಸ್ ಬೋರಿಂಗ್ ಅನ್ನಿಸ್ತಂತೆ. ಯಾಕೆಂದರೆ ತುಂಬ ಕೆಲಸ ಆಗೋಗ್ಬಿಟ್ಟಿದೆ, ಫಿಸಿಕ್ಸ್ ನಲ್ಲಿ ಮಾಡೋಕ್ಕೇನೂ ಇಲ್ಲ, ಐ ವಾಂಟ್ ಟು ಸ್ಟಡಿ ಬಯಾಲಜಿ ಅಂದ್ಬಿಟ್ಟು PhD ಆದಮೇಲೆ 2 ವರ್ಷ ಮಾಲಿಕ್ಯುಲರ್ ಬಯಾಲಜಿ ಬಗ್ಗೆ ಸ್ಟಡಿ ಮಾಡಿ ಆನಂತರ ಏನು ಕಂಡುಹಿಡಿದ್ರು? ಸ್ಟ್ರಕ್ಚರ್ ಆ್ಯಂಡ್ ಫಂಕ್ಷನ್ಸ್ ಆಫ್ ರೈಬೋಸೋಮ್ ಬಗ್ಗೆ ವರ್ಕ್ ಮಾಡಿ ನೊಬೆಲ್ ಪ್ರೈಸ್ ಬಂತು. ಆ ರೀತಿ ತಮಗೆ ಡಾಕ್ಟರ್ ವಿಜಯ ರಾಘವನ್ ಬಗ್ಗೆ ಕೆಲವರು ತಿಳ್ಕೊಂಡಿದ್ದೀರಿ ಅನಿಸುತ್ತೆ. ಸೈಂಟಿಫಿಕ್ ಅಡ್ವೈಸರ್ ಟು ಪ್ರೈಮ್ ಮಿನಿಸ್ಟರ್ ಆಗಿದ್ದರು. ಇನ್ಫ್ಯಾಕ್ಟ್ ಅವರು ಕೆಮಿಕಲ್ ಎಂಜಿನಿಯರ್ ಬೇಸಿಕಲಿ, ಆಮೇಲೆ ಬಯೋಟೆಕ್ನಾಲಜಿ ಮಾಡಿ ಉನ್ನತ ಅಧ್ಯಯನ ಮಾಡಿದ್ರು. ಅದೇ ರೀತಿ ಇನ್ನೊಬ್ಬರು ಏಟ್ರಿಲಿ ಒಬ್ರು ಇದ್ದಾರೆ, ಏಟ್ರಿ ಅಂತ ಸಂಸ್ಥೆ ಇದೆಯಲ್ಲ ಇಲ್ಲಿ, ಅವರು ಎಲೆಕ್ಟ್ರಿಕಲ್ ಇಂಜಿನಿಯರ್. ಬೇಸಿಕಲಿ ಎಲೆಕ್ಟ್ರಿಕಲ್ ಇಂಜಿನಿಯರಿಂಗ್ ಮುಗಿಸಿದ ಮೇಲೆ ಅವ್ರಿಗೆ ಬಯಾಲಜಿ ಮೇಲೆ ಇಂಟ್ರೆಸ್ಟ್ ಬಂತಂತೆ. ಸೊ ಈ ಬಿಕೇಮ್ ಎನ್ ಎಕಾಲಜಿಸ್ಟ್, ಫೇಮಸ್ ಎಕಾಲಜಿಸ್ಟ್ ನಾವು. ಸೊ ಆಪ್ಷನ್ಸ್ ಆರ್ ಮೆನಿ. ಎಲ್ಲ ಸಬ್ಜೆಕ್ಟ್ ಬಗ್ಗೆನೂ ಇಂಟ್ರೆಸ್ಟ್ ಇಲ್ಲಿ. ಬಯಾಲಜಿ ಒಂದೇ ಅಲ್ಲ, ಫಿಸಿಕ್ಸ್, ಕೆಮಿಸ್ಟ್ರಿ, ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಬಗ್ಗೆನೂ ನಿಮಗೆ ಆಸಕ್ತಿ ಇಟ್ಕೊಂಡಿರಿ. ಮುಂದೆ ತಮಗೆ ಫಿಸಿಕ್ಸ್ ಮಾಡಿ ಬೋರ್ ಅನಿಸಿದ್ರೆ ಯು ಕ್ಯಾನ್ ಜಂಪ್ ಟು ಬಯಾಲಜಿ ಆರ್ ಟು ಕೆಮಿಸ್ಟ್ರಿ. ಓಕೆ. ಸೊ ನಮ್ಮ ಗುರುಗಳಿಗೆ ನಿಮ್ಮೆಲ್ಲರ ಪರವಾಗಿ ತುಂಬ ಹೃದಯದ ಧನ್ಯವಾದಗಳು. ಈಗ ವಿ ಹ್ಯಾವ್ ವಿತ್ ಅಸ್ ಡಾಕ್ಟರ್ ಪ್ರಸಾದ್ ಸರ್, ಹೂ ಈಸ್ ಎನ್ ರಾಕೆಟ್ ಸೈಂಟಿಸ್ಟ್. ಅಬ್ದುಲ್ ಕಲಾಂ ಬಗ್ಗೆ ಕೇಳಿದ್ದೀರಾ? APJ ಏನಾಗಿದ್ದರು? ಎಸ್, ಅವ್ರ ಜೊತೆ ಕೆಲಸ ಮಾಡಿದ್ದಾರೆ ಸರ್. ಒಂದು ಜೋರಾದ ಚಪ್ಪಾಳೆ ಕೊಡಿ. ಸರ್ಗೆ ನಮ್ಮ VSS ಅಂತ ಒಂದು ಆರ್ಗನೈಸೇಷನ್ ಇದೆ, ಇಸ್ರೋ ಆರ್ಗನೈಸೇಷನ್ನು. ಅಲ್ಲಿ ತುಂಬ ವರ್ಷಗಳ ಕಾಲ ಕೆಲಸ ಮಾಡಿ ಈಗ ನಿವೃತ್ತರಾಗಿದ್ದಾರೆ. ಈಗ ಸೈನ್ಸ್ ಕಮ್ಯುನಿಕೇಷನ್ ಅಂದರೆ ಹುಡುಗರಿಗೆ ರಾಕೆಟ್ ಸೈನ್ಸ್ ಬಗ್ಗೆ, ರಾಕೆಟ್ಸ್ ಯು ಬಿ ಸ್ಪೀಕಿಂಗ್ ಆನ್ ವಾಟ್ ಸರ್? ಸ್ಪೇಸ್ ಸೈನ್ಸ್, ಬಾಹ್ಯಾಕಾಶ. ನಿನ್ನೆ ಹೇಳ್ತಾ ಇದ್ದೆ ಪ್ರೊಫೆಸರ್ ಯು ಆರ್ ರಾವ್, ಡಾಕ್ಟರ್ SK ಶಿವಕುಮಾರ್ ಅವರಿಬ್ಬರು ಸ್ಪೇಸ್ ಸೈನ್ಸಲ್ಲಿ ದಿಗ್ಗಜರು. ಅವ್ರ ಜೊತೆ ಕೆಲಸ ಮಾಡಿದಂಥ ವಿಜ್ಞಾನಿ ಅವರು ಬಂದಿದ್ದಾರೆ. ನಿಮ್ಮೆಲ್ಲರ ಪರವಾಗಿ ಅವ್ರಿಗೆ ಸ್ವಾಗತ ಕೋರ್ತೀನಿ. ಹಾಗೆ ಅವರ ಕಿರು ಪರಿಚಯವನ್ನು ನಮ್ಮ ಕಲೀಗ್ ಉಮೇಶ್ ಅವರು ಮಾಡಿಕೊಡ್ತಾರೆ.
Very good afternoon. It's my immense pleasure to introduce great scientist and engineer C.D. Prasad sir. Currently, sir is advisor and committee member of Gravity Science Foundation, Mysuru, and sir has a vast experience of 33 years in the Department of Space for onboard rocket for PSLV, GSLV, and ASLV. He headed and configuration control of electrical integration and checkout systems for PSLV and GSLV. He is qualified as an internal auditor for ISO 9000 standards. His specific achievement is a core member for antenna test facility. He established a configuration control concept towards electrical integration of checkout systems for launch vehicles. Sir has finished his BE in electronics, and he has published many reputed journal papers in the national and international papers. With this brief introduction, I once again welcome you on behalf of KSTA, on behalf of all the teachers and students here, sir. Welcome you, sir. The floor is yours. Thank you, sir.
Hello, can you hear me? Before I start, I just want to know from you whether you are comfortable if I present in English or you want in Kannada. If somebody wants in Kannada, please raise your hand. Okay, we'll make it a mixture. Kannada and working language. Almost for last 65 to 70 years, our country has made progress on space science, especially towards the peaceful application of the space. That 65 years of development, I had to make it in 60 minutes is very difficult. Anyway, let me make an attempt to convince you all how we have done what we have done for so many years. When I told about peaceful application, I am talking about how the space can be used for the public, for the society. not for military application. Of course, there are certain things which are common that can go for military application also. ನೀವೆಲ್ಲ ಕೇಳಿದ್ದೀರಾ ಸ್ಯಾಟಲೈಟ್. ಸ್ಯಾಟಲೈಟ್ನ ಉಪಯೋಗ ಏನು? ಪ್ರತಿಯೊಂದು ಹೆಜ್ಜೆನಲ್ಲೂ ಕೂಡ ಟುಡೇ ವಿ ಆರ್ ಡಿಪೆಂಡಿಂಗ್ ಆನ್ ಸ್ಯಾಟಲೈಟ್. ಫಿಶಿಂಗ್, ಮೀನುಗಾರಿಕೆಗೆ ಸ್ಯಾಟಲೈಟ್ ಬೇಕಾ? ಎಸ್. ಅರ್ಲಿಯರ್ the fishermen they used to go to the deep sea with some seasonal, ಈ ಸೀಸನಲ್ಲಿ ಇಂಥ ಕಡೆ ಜಾಸ್ತಿ ಮೀನು ಸಿಕ್ಕುತ್ತೆ ಅಂದ್ಕೊಂಡು ಉದ್ದೇಶದಿಂದ ಒಂದು ವಿತ್ ಸಮ್ ಅಸಂಪ್ಷನ್ ಅವ್ರು ಹೋಗ್ತಾಯಿದ್ರು. ಒಂದೊಂದು ಸಾರಿ ಸರಿಯಾಗಿ ಕರೆಕ್ಟ್ ಸಿಗ್ತಾಯಿತ್ತು, ಒಂದೊಂದು ಸಾರಿ ಇಲ್ಲ. ಆ ಸೀಸನ್ನಲ್ಲಿ ಪಾಪ ಮೀನು ಸಿಗದೇ ಇದ್ದರೆ ಹೋಲ್ ದೇರ್ ಫ್ಯಾಮಿಲಿ ಎವ್ರಿಬಡಿ ವಿಲ್ ಸ್ಟಾರ್ವ್. ದಟ್ ಇಸ್ ದ ಸಿನಾರಿಯೋ ಲಾಂಗ್ ಎಗೋ. ಈಗ ನಾವು ಸ್ಯಾಟಲೈಟ್ ಮುಖಾಂತರ ಎಲ್ಲಿ ಫಿಶ್ ಇದೆ ಅಂತ ನಾವು ನೋಡಿ ಆ ಬಸ್ತರಿಗೆ ನಾವು ಥ್ರೂ ಅವರ್ ಫಿಶರಿ ಡಿಪಾರ್ಟ್ಮೆಂಟ್ ನಾವು ಹೇಳ್ಕೊಡ್ತೀವಿ. ವೇರ್ ದೇರ್ ಇಸ್ ಮೋರ್ ಫಿಶ್ ಗೋ ದೇರ್, ಡೋಂಟ್ ಗೋ ದೇರ್ ಅದು ನಾವು ಹೇಳ್ತೀವಿ. ಸೊ ವಿ ಹೆಲ್ಪ್ ದಿ ಫಿಶಿಂಗ್ ಇಂಡಸ್ಟ್ರಿ. ATM ನಿಮಗೆಲ್ಲ ಗೊತ್ತು, ಬ್ಯಾಂಕಿಂಗ್ ಸರ್ವಿಸ್. ಯು ಕ್ಯಾನ್ ಡ್ರಾ ಯುವರ್ ಮನಿ ಫ್ರಮ್ ಎನಿವೇರ್. ಹೌ ದ ಬ್ಯಾಂಕಿಂಗ್ ಸರ್ವಿಸ್? ಥ್ರೂ ದ ಸ್ಯಾಟಲೈಟ್. ಕ್ರಿಕೆಟ್ ಮ್ಯಾಚ್ ಆಸ್ಟ್ರೇಲಿಯಲ್ಲಿ ಆಗ್ತಾ ಇರುತ್ತೆ, ಆರಾಮಾಗಿ ಕೂತ್ಕೊಂಡು ನಾವು ಇಲ್ಲಿ ನೋಡ್ತೀವಿ. ಹೌ ಇಸ್ ದಟ್? ಥ್ರೂ ದ ಸ್ಯಾಟಲೈಟ್. ಯು ನೇಮ್ ಇಟ್. ಐ ನೀಡ್ ನಾಟ್ ಟಾಕ್ ಅಬೌಟ್ ಮಿಲಿಟರಿ or military application satellite, how it is useful. You all know it. You name it, in any step you take, whether it is communication, whether you are in living room or bathroom, you can talk to your uncle whether he is in New Zealand or New York. How is that? Through the satellite. So I think that's enough. I need not waste time on that. So today satellite is an important tool for every application. 10 ದಿವಸಕ್ಕೆ ಮುಂಚೆನೇ ನಾವು ಹೇಳ್ತೀವಿ ಚಂಡಮಾರುತ ಎಲ್ಲಿದೆ, ಯಾವ ಕಡೆ ಬರ್ತಾ ಇದೆ. ಸೊ ದ ಕನ್ಸರ್ನ್ ಗವರ್ಮೆಂಟ್ ಕ್ಯಾನ್ ಟೇಕ್ ನೆಸೆಸರಿ ಆ್ಯಕ್ಷನ್ ಟು ಸಿ ದಟ್ ಡಿಸಾಸ್ಟರ್ ಶುಡ್ ನಾಟ್ ಟೇಕ್ ಪ್ಲೇಸ್. ಸೊ ಫಾರ್ ವೆದರ್ ರಿಪೋರ್ಟ್, ಫಾರ್ ಎವ್ರಿ ಸ್ಟೆಪ್ ಟುಡೇ ವಿ ನೀಡ್ ಸ್ಯಾಟಲೈಟ್. I think that's enough. Now you know satellite is an important tool. Now how the satellite is there? It will not just go there. So to put that satellite there, extraordinary technology is required. So many things are involved. First and foremost, what is required is a vehicle to carry this passenger. The passenger is the satellite. That passenger has to be taken to a required orbit. It has to be placed there. So we require a vehicle. That we call SLV, Satellite Launch Vehicle. That's how the beginning. Now you see how difficult it is to make a rocket. There are so many things. From now on I will keep on telling difficult, everything is difficult. Now first and foremost is rocket. Rocket, especially since you are all 8th standard and above, you all know long ago, or might be recently, you have studied above the earth there are different layers are there. You remember that? Stratosphere, troposphere, you remember all that? So different layers are there. That's almost up to around 120 kilometers above the earth. This 120 kilometers is the most difficult region for the rocket. Why? For a moment you imagine all these layers were not there. If those layers were not there, what would have happened? On this earth, ಯಾವ ಜೀವಿನೂ ಇರ್ತಾ ಇರಲಿಲ್ಲ. Because the sun releases all sorts of rays, ultraviolet rays, gamma rays, X-rays, all those things would have come and killed everybody. But it has to come through these layers. So they get filtered there. Those energies are stored there. The filtered one, beautiful sunlight, we are living happily here. But now once the rocket has to go, it has to pierce these layers and go. So the friction, the temperature developed on the rocket body will be almost 1500 degrees centigrade. 30 degrees we want AC here. Now imagine 1500 what will happen. You have heard of Kalpana Chawla? What happened to her? During their Apollo mission, after their objective was over, they were asked to come back. When they have to come back, they have to come through these layers. Unfortunately, there is a quality issue. The capsule where these astronauts will be seated, they called heat shield. Unfortunately, we do not know the actual reason, but what is told is there is a quality issue. So there are some minor cracks were there. So the 1500 degrees entered the capsule and all the 7 astronauts, including Kalpana Chawla, were burnt. You know that. So for our rocket, first and foremost is metallurgy. Some of you students, you may become a scientist of metallurgy. The most no, all are important. No, I am telling you. I keep on telling you that. So one is that. Next one. I am not going to talk about big science. Simple what you have studied. I throw a stone like that. What happened to the stone? Why it falls down? When I put the rocket, it starts pulling down. Like our political issue now, you know. One man want to go up, 10 people want to pull him down. Now when the rocket put up, it starts pulling down. No, it should not come down. It has to keep on going up and up and up. So it requires certain energy. Such an energy is required that should make sure, in spite of gravity pulling it down, it should not come down. It has to keep on going up and up and up. What is that called as? Escape velocity. Escape velocity, almost 11.2 kilometers per second. Such a energy is required. Then only it will go up. Otherwise, it will come down. So, what sort of energy is required? So, we require chemical energy. But there are so many research going on. We may go for nuclear power in the future or electrical, that's all. It's a different story. But as on now, we are experts in chemical. What we are using? Certain chemical. What's that chemical? You all know, Deepavali time, you make the rocket, you make the pataka. What the pataka does? A paper barrel. And on the bottom side, with a clay or something, it is stuffed there. It is plugged. And on the top, inside the paper barrel, chemical is there, explosive. And then there is a batti, wick. A batti is there. That is also tightly held. Once you light that batti, that wick, it goes inside. And that chemical, nothing happens. It keeps on burning. Then there is a very huge pressure is built inside. But that paper barrel cannot hold that pressure. So it will burst. So pataka dam, you are all happy, 10 rupees gone. Happy. Pataka over. Whereas in my rocket, it should not happen. So what we do, on the top end, we, on, somebody is there? No. On the top end, we call head end of the rocket, there we seal it, blocked. And at the bottom side, we put a nozzle. Nozzle design is very difficult. I will come to that later. Okay, let me complete that nozzle itself. You are all familiar to your garden. You are using a long hose. One side it is connected to the tap there, and then you try to put water. You cannot go further up. So what you do, you put your finger there, and you try to control that. Is it not? How the water? So it means that nozzle is the one controlling, that finger is the one controlling how far the water should go. But the pressure is same. So how you should do? Here also, that chemical, once it is ignited in the rocket, the pressure start building up. Huge pressure start building up. As I told you the material, it should withstand that, not a paper like pataka. Here it has to withstand that pressure. That pressure has to come out. For that what we do a nozzle. So this is the throat level, and then there is a wider one. So here we try to reduce the pressure. That pressure has to come at certain, I don't want to go more detail about that. Once it starts coming out, it gets a push, upward push, because the pressure is going to coming down. If you make it very narrow, it will burst. If you make it wide, pressure will not be there. So it is a very difficult situation. So the nozzle design of a rocket is a very tough. So now you know metallurgy I told, now there is a chemical energy I told, and there are, like that there are innumerable I don't want to go more in depth because we have got only 1 hour. Let us say rocket is ready. Once the rocket is ready, it will carry this satellite. Now we will come to the satellite. Now the satellite design, that is another difficult story. Who is the end user? Whether for communication or for weather report or for military application. So what sort of electronics has to be incorporated in the satellite? ಅದು ಮಾಡಬೇಕಾಗ್ತದೆ. ಯಾವ ಥರ ಕ್ಯಾಮ್ರಾ ಇರಬೇಕು, ಯಾವ ಥರ ಸೆನ್ಸರ್ಗಳಿರಬೇಕು, ಆಲ್ ದೋಸ್ ಥಿಂಗ್ಸ್ ವಿ ಹ್ಯಾವ್ ಟು ಟೇಕ್ ಕೇರ್. ಈಗ ನಾವು ಒಂದು ಸ್ಯಾಟಲೈಟ್ ನಾವು ಹೇಳಿದ್ರೆ ಆ ಸ್ಯಾಟಲೈಟ್ನಲ್ಲಿ ಆಲ್ಮೋಸ್ಟ್ ಅರೌಂಡ್ 50% ಆಫ್ ದಿ ಸ್ಯಾಟಲೈಟ್ ದಟ್ ಗೋಸ್ ಫಾರ್ ಹೌಸ್ ಕೀಪಿಂಗ್. ಹೌಸ್ ಕೀಪಿಂಗ್ ಅಂದರೆ ಬೇಕಾದ್ದೇ ಅದು ಇರಲೇಬೇಕಾದಷ್ಟು ಸ್ಟ್ರಕ್ಚರ್ ಬೇಕು ಅದನ್ನು ಇಡೋದಕ್ಕೆ, ಅದ್ರ ತೂಕ ಆಗೇ ಆಗುತ್ತೆ. ಸೊ ಆ ಎಲೆಕ್ಟ್ರಾನಿಕ್ಸ್ ಸೊ ಅದಕ್ಕೋಸ್ಕರ ದೆರ್ ಇಸ್ ಎ 50% ಓನ್ಲಿ ಅವೈಲಬಲ್ ಫಾರ್ ಯುವರ್ ವೇರಿಯಸ್ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ಸ್. ಬಾಕಿ 50% ಅದು ಹೌಸ್ ಕೀಪಿಂಗ್. ಏನು ಹೌಸ್ ಕೀಪಿಂಗ್ ಅಂದರೆ ಇನ್ನೊಂದೇನು, ನಾವು ಗ್ರೌಂಡಿಂದ ಕಮಾಂಡ್ ಕೊಡ್ತೀವಿ ಆ ಸ್ಯಾಟಲೈಟ್ಗೆ, ಅಲ್ಲಿಗೆ ದೇರ್ ಶುಡ್ ಬಿ ಎನ್ ಆ್ಯಂಟನಾ ಟ್ರಾನ್ಸ್ಮಿಟರ್ ಫ್ರಮ್ ಹಿಯರ್ ಆ್ಯಂಡ್ ದೇರ್ ಶುಡ್ ಬಿ ರಿಸೀವರ್ ದೇರ್. ಅಲ್ಲಿಗೆ ವಿ ಕಾಲ್ ಇಟ್ ಆಸ್ ಎ ಅಪ್ವರ್ಡ್ ಲಿಂಕ್. ಇಲ್ಲಿಂದ ನಾವು ಅಪ್ವರ್ಡ್ ಸಿಗ್ನಲ್ ಕಳಿಸ್ತೀವಿ. ಆ ಕೆಲಸ ಅದು ಮಾಡ್ತೂ ಇಲ್ಲ ಅನ್ನೋದು ದಟ್ ಹ್ಯಾಸ್ ಟು ಸೆಂಡ್ ದಿ ಸಿಗ್ನಲ್ ಬ್ಯಾಕ್ ಟು ಅಸ್ ಹಿಯರ್. ಸೊ ದಟ್ ಇಸ್ ಅ ಡೌನ್ವರ್ಡ್ ಲಿಂಕ್. ಸೊ ವಿ ಹ್ಯಾವ್ ಎ ಅಪ್ವರ್ಡ್ ಲಿಂಕ್ ಆ್ಯಂಡ್ ದರ್ ಇಸ್ ಅ ಡೌನ್ವರ್ಡ್ ಲಿಂಕ್. ನಿಮ್ಗೆ ಆಶ್ಚರ್ಯ ಆಗ್ಬೋದು, ಈಗಲೇ ಹೇಳ್ತಾ ಇದ್ದೀನಿ ನಾನು, ಮುಂದಕ್ಕೆ ಟಚ್ ಮಾಡ್ತೀನೋ ಹೇಳೋ ಗೊತ್ತಿಲ್ಲ, ಟೈಮ್ ಇಲ್ಲ. ನಾವು ಮಂಗಳಯಾನ್ ಮಾಡೋದು, ಮಂಗಳ ಲೋಕಕ್ಕೆ ಕೂಡ ನಾವು ಒಂದು ಸ್ಯಾಟಲೈಟ್ ಕಳಿಸೋದು. ನಿಮಗೆಲ್ಲ ಸ್ಪೀಡ್ ಆಫ್ ಲೈಟ್ ಗೊತ್ತು, ಸ್ಪೀಡ್ ಆಫ್ ಲೈಟ್ ಗೊತ್ತಲ್ಲ, ಆ ಸ್ಪೀಡ್ ಆಫ್ ಲೈಟ್ 1,86,000 miles per second ಅದರಲ್ಲಿ ನಾವು ಮಾಡಿದ್ರು ಕೂಡ ನಾವು ಒಂದು ಸಿಗ್ನಲ್ ಕಳಿಸಿದ್ರೆ ಅದು ಮಂಗಳ ಲೋಕಕ್ಕೆ ಹೋಗಿ ಸ್ಯಾಟಲೈಟ್ಗೆ ತಾಕಿ ಆ ಸ್ಯಾಟಲೈಟ್ ತಾಕಬೇಕಾದ್ರೆ ಇಟ್ ಟೇಕ್ಸ್ ನಿಯರ್ಲಿ 6 minutes. ಅಷ್ಟು ಸ್ಪೀಡಲ್ಲಿ ನಮ್ಮ ಲೈಟ್ ಸ್ಪೀಡಲ್ಲಿ ಸಿಗ್ನಲ್ ಕಳಿಸೋದು ಕೂಡ ಇಟ್ ಟೇಕ್ಸ್ 6 minutes ಟು. ಸೊ ಯು ಸಿ ಹೌ ಫಾರ್ ಇಟ್ ಈಸ್. ಆ ಕೆಲಸ ಮಾಡ್ತೂ ಇಲ್ಲ ಅಂತ ಹೇಳಿ ವಾಪಸ್ ಕಳ್ಸೋಕ್ಕೆ ಸಿಗ್ನಲ್ ಇಲ್ ಟೇಕ್ ಅಂಡರ್ 6 minutes. ನಾವಲ್ಲಿ ಕಮಾಂಡ್ ಕೊಟ್ಟರೆ 12 ನಿಮಿಷ ತನಕ ಏನಾಯಿತು ಅಂತ ಗೊತ್ತಿಲ್ಲ. ಸೊ ವಿ ಹ್ಯಾವ್ ಟು ಅಸ್ಯೂಮ್ ವಾಟ್ ಹಸ್ ಹ್ಯಾಪನ್ ದೇರ್. ಸೊ ಕ್ಯಾನ್ ಯು ಇಮ್ಯಾಜಿನ್ ಹೌ ಡಿಫಿಕಲ್ಟ್ ಇಟ್ ಈಸ್? ಐ ವಿಲ್ ಕಮ್ ಟು ದಟ್ ಲೇಟರ್. ಸೊ ಕಮಿಂಗ್ ಬ್ಯಾಕ್ ಟು ದಿ ಸ್ಯಾಟಲೈಟ್ ಡಿಸೈನ್, ಅದರಲ್ಲಿ ಸ್ಟ್ರಕ್ಚರ್ ಹೊರಟೋಯ್ತು. ಮಿಲ್ಟ್ರಿ ಬೇಕಾದ್ದು ದೇ ವಾಂಟ್ ಟು ಸಿ, ನೀವಿಬ್ಬರು ಹುಡುಗಿಯರು ಸೈಕಲಲ್ಲಿ ಹೋಗ್ತಾ ಇದ್ದರೆ ಅವರ್ ಇಸ್ರೋ ಸೈಂಟಿಸ್ಟ್ ಹ್ಯಾವ್ ಮೇಡ್ ದಿ ಕ್ಯಾಮರಾ ಆಫ್ ಸಚ್ ಎ ನೇಚರ್, ಇಫ್ 2 girls are riding a cycle, not your photo, we can tell the color of your bindi, we can tell you from 300 kilometers. From 300 kilometers we can tell you the color of your bindi. That is the type of resolution camera what we have. So that sort of a thing is required. So all those things ಹಾಕಿ ನಾವು ಸ್ಯಾಟಲೈಟಲ್ಲಿ ಮಾಡಿದ್ರೆ ಅದಕ್ಕೆ ಎಷ್ಟು ಕರೆಂಟ್ ಬೇಕು ಇದೆಲ್ಲ ಓಡಿಸೋಕ್ಕೆ. ಸೊ ವಿ ಹ್ಯಾವ್ ಟು ಪ್ರಿಪೇರ್ ಎ ಸೋಲಾರ್ ಪ್ಯಾನಲ್. ಸೂರ್ಯನಿಂದ ಕಾಂತಿ ತೊಗೊಂಡು ಅದು ಕನ್ವರ್ಟ್ ದಿ ಸೋಲಾರ್ ಎನರ್ಜಿ ಟು ಎಲೆಕ್ಟ್ರಿಕಲ್ ಎನರ್ಜಿ, ಅದನ್ನು ಸ್ಟೋರ್ ಮಾಡೋದಕ್ಕೆ ಬ್ಯಾಟ್ರಿಗಳಾಗಬೇಕು. ಅದೆಲ್ಲ ಮಾಡೋದಕ್ಕೆ 50% ಗೋಸ್ ಟುವರ್ಡ್ಸ್ ದಿ ಹೌಸ್ ಕೀಪಿಂಗ್, 50% ವಾಟ್ ಎವರ್ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಯು ವಾಂಟ್ ಟು ಡೂ, ಅಷ್ಟೆಲ್ಲ ಆಗುತ್ತೆ. ಅದೆಲ್ಲ ಮಾಡಿದ್ಮೇಲಿಂದ ಅದು ಕಂಟ್ರೋಲ್ ಮಾಡಬೇಕಾಗತ್ತೆ. ಆ ಸ್ಯಾಟಲೈಟ್ ಇವಾಗ ನಾವೊಂದು ಟ್ರೈನ್ ಇಲ್ಲಿಂದ ಮೈಸೂರಿಗೆ ಹೋಗಬೇಕು ಅಂತಂದರೆ ಅದು ಶ್ರೀರಂಗಪಟ್ಟಣದಲ್ಲಿ ನಿಂತ್ಕೊಂಡ್ರೆ ಆಗಲ್ಲ, ಅದು ಮೈಸೂರು ತನಕ ಹೋಗಬೇಕು. ಅಲ್ಲಿಗೆ ನಾವು ಬಾಕಿ ಇಟ್ಟಿದ್ದೇನೆಲ್ಲ ನಾವು ಗ್ರೌಂಡಿಂದ ಕಮಾಂಡ್ ಕೊಟ್ಟು ಅದನ್ನು ತಳ್ಳಿ 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 ಆ ಡೆಸ್ಟಿನೇಷನ್ ತನಕ ಹೋಗೋ ಮಾಡಬೇಕು. ಅಲ್ಲಿಗೆ ದೇರ್ ಆರ್ ಸರ್ಟನ್ ಕಂಟ್ರೋಲ್ ಸಿಸ್ಟಮ್ಸ್ ಆರ್ ರಿಕ್ವೈರ್ಡ್. ಗ್ರೌಂಡಿಂದ ಕೊಟ್ಟಿದ್ರೆ ಅದು ಒಬೇ ಮಾಡಬೇಕು. ಸೊ ದಟ್ ಸಾರ್ಟ್ ಆಫ್ ಇಟ್. ಅದಕ್ಕೆ ನಾವು ಥ್ರಸ್ಟರ್ಸ್ ಅಂತ ಹೇಳ್ತೀವಿ. ಆ ಥ್ರಸ್ಟರ್ಸನ್ನು ವಿಲ್ ಹ್ಯಾವ್ ಇನ್ ದಿ ಸ್ಯಾಟಲೈಟ್. ನಾವಿಲ್ಲ ಗ್ರೌಂಡ್ ಕೊಟ್ಟರೆ, ಯಾಕೆಂದರೆ ಅಲ್ಲಿ ದೇರ್ ಇಸ್ ನೋ ಗ್ರಾವಿಟಿ, ದೇರ್ ಇಸ್ ನೋ ಮಚ್ ಪ್ರಾಬ್ಲಮ್. ಈವನ್ ಫಾರ್ ಎ ನ್ಯಾನೋ ಸೆಕೆಂಡ್ ಒಂದು ರಾಕೆಟ್ ಫೈರ್ ಮಾಡಿದ್ರೆ ಇಟ್ ಗೋ 700 kilometers. ಪುಸ್ ಫೈರ್ ಮಾಡಿದ್ರೆ ಸಾಕು, ಇಟ್ ವಿಲ್ ಗೋ. ಸೊ ಅದನ್ನು ಮ್ಯಾನಿಪ್ಯುಲೇಟ್ ಮಾಡಿ ಎಕ್ಸಾಕ್ಟ್ಲಿ ಎಲ್ಲಿಗೆ ಬೇಕು, ಯಾವ ಜಾಗಕ್ಕೆ ಬೇಕು ತೊಗೊಂಡೋಗಿ ಯು ಕ್ಯಾನ್ ಪಾರ್ಕ್ ಇಟ್. ಪಾರ್ಕ್ ಆಗೋದ್ಮೇಲೆ ಕೆಲಸ ಮುಗಿಲಿಲ್ಲ. ಅರ್ತ್ ಈಸ್ ನಾಟ್ ಸ್ಟೇಷನರಿ, ಅರ್ತ್ ಈಸ್ ಗೋಯಿಂಗ್ ಅರೌಂಡ್ ಸ್ಪಿನ್ನಿಂಗ್. ನೋ ಸ್ಯಾಟಲೈಟ್ ಆಲ್ಸೋ ಶುಡ್ ಒಬೇ. ಇಲ್ಲಿ ನಾವು ವಿ ಹ್ಯಾವ್, ಫಾರ್ ಯುವರ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡಿಂಗ್, two types of satellite we will talk about. One, though, we talk about remote sensing satellite. Remote sensing ಅಂತಂದರೆ ಮೋಸ್ಟ್ಲಿ ವಿ ಯೂಸ್ ಫಾರ್ ಆಲ್ ಅವರ್ ಮಿಲಿಟ್ರಿ ಅಪ್ಲಿಕೇಶನು, ಅದು ಇದು ಬೇಕಾದಷ್ಟು ನಾನು ನಿಮ್ಗೆ ಹೇಳಿದ್ನಲ್ಲ, ಅಗ್ರಿಕಲ್ಚರ್ಗಿರ್ಬೋದು, ಫಿಶ್, ಅದಕ್ಕೆಲ್ಲ ಆಗ್ಬೋದು. ಇನ್ನೊಂದು ಕಮ್ಯುನಿಕೇಷನ್ ಸ್ಯಾಟಲೈಟ್. ಅದಕ್ಕೇನು ಮಾಡಬೇಕು ನಾವು, ಇಟ್ಸ್ ಎ ಡಿಫ್ರೆಂಟ್ ಟೈಪ್. Now first we'll talk about remote sensing satellite. ಈ ರಿಮೋಟ್ ಸೆನ್ಸಿಂಗ್ ಸ್ಯಾಟಲೈಟ್ನಲ್ಲಿ ಕೂಡ ಎರಡು ಥರದ್ದು ಮಾಡ್ತೀವಿ. ಒಂದು ಪೋಲಾರ್, ಅದು ಇಫ್ ಯು ಟೇಕ್ ದಿ ಅರ್ತ್ ಹಿಯರ್, ನಾರ್ತ್ ಪೋಲ್, ಸೌತ್ ಪೋಲ್, ವಿ ಪುಟ್ ದಿ ಸ್ಯಾಟಲೈಟ್ ಸೇ ಅಬೌಟ್ 300 kilometers above the earth, that will be orbiting from pole to pole. Pole to pole ಸುತ್ತುತ್ತಾ ಇರುತ್ತೆ. But the ಭೂಮಿ also is spinning. Here we take the advantage of that. ಏನು ಅಡ್ವಾಂಟೇಜು? ನಮ್ಮಲ್ಲಿ ಕಿಟಕಿ ಯಾಕಮ್ಮ ಇರುತ್ತೆ? Why do we have windows? Yeah, she is quite right. ವಿಂಡೋಸ್ ಯಾತಕ್ಕಿದೆ? ಫಾರ್ ವೆಂಟಿಲೇಷನ್ ಪರ್ಪಸ್, ಬೆಳಕು ಗಾಳಿ ಬರಲಿ ಅಂತ ಅಲ್ವಾ? ಎವ್ರಿಬಡಿ ಥಿಂಕ್ ಸೊ. ಬಟ್ ಸಮ್ ಪೀಪಲ್ ದೇ ಥಿಂಕ್ ಕಿಟಕಿ ಇರೋದು ಪಕ್ಕದ ಮನೇಲಿ ಏನಾಗ್ತಾ ಇದೆಯೋ ಅದು ನೋಡೋದಕ್ಕೆ ಅಂತಾರೆ. ಆ ಕೆಲಸನೂ ಮಾಡ್ಬೋದಲ್ವಾ? ಯಾಕೆ ಅದನ್ನು ಹೇಳ್ತೀನಿ ಅಂತಂದರೆ, ದಿ ಸ್ಯಾಟಲೈಟ್ ಆರ್ಬಿಟಿಂಗ್ ಫ್ರಮ್ ಪೋಲ್ ಟು ಪೋಲ್, ಬಟ್ ದಿ ಅರ್ತ್ ಇಸ್ ಸ್ಪಿನ್ನಿಂಗ್. ಒಂದನೇ ಆರ್ಬಿಟ್ ನಮ್ಮ ಇಂಡಿಯಾ ಮೇಲಿದ್ರೆ, ನೆಕ್ಸ್ಟ್ ಆರ್ಬಿಟ್ ಕ್ಯಾನ್ ಬಿ ಲಂಕಾ, ನೆಕ್ಸ್ಟ್ ಆರ್ಬಿಟ್ ಕ್ಯಾನ್ ಬಿ ಆಫ್ರಿಕಾ. ಆ ದೇಶದಲ್ಲಿ ಏನಾಗ್ತಾಯಿದೆ ನಾವು ನೋಡ್ಬೋದು. ಅಲ್ಲಿ ಏನೇನಾಗ್ತಾಯಿದೆ ವಿ ಕ್ಯಾನ್, ಪಾಕಿಸ್ತಾನದಲ್ಲಿ ಏನಾಗ್ತಾಯಿದೆ, ಲಂಕಾದಲ್ಲಿ ಏನಾಗ್ತಾಯಿದೆ, ವಿ ಕ್ಯಾನ್ ಸಿ ಆಲ್ ದಟ್. ಸೊ ದಿಸ್ ಈಸ್ ರಿಮೋಟ್ ಸೆನ್ಸಿಂಗ್. ರಿಮೋಟ್ಲಿ ವಿ ಕ್ಯಾನ್ ಸೆನ್ಸ್ ಆಲ್ ದೀಸ್ ಥಿಂಗ್ಸ್ ಆರ್ ಹ್ಯಾಪನಿಂಗ್. ನೌ ಕಮ್ ದಿ ಕಮ್ಯುನಿಕೇಷನ್ ಸ್ಯಾಟಲೈಟ್. ಸೊ ವಿ ಪುಟ್ ದಿ ಸ್ಯಾಟಲೈಟ್, ಇದು ಇಂಡಿಯಾದಲ್ಲಿ ಸಪೋಸ್ ಯು ಟೇಕ್ ಇಟ್ ದಿಸ್ ಇಂಡಿಯಾ ಗ್ಲೋಬ್, ಇಂಡಿಯಾದಲ್ಲಿ let us take Nagpur at the center. You put the satellite 36,000 kilometers away. Since the earth is spinning, the satellite also all the time in synchronization to this point of the earth. So the geosynchronous. Geo ಅಂದರೆ ಅರ್ಥ ಗೊತ್ತಾಯ್ತಲ್ಲ, ಸಿಂಕ್ರೊನೈಸ್. ಸೊ ಅಲ್ಲಿ ವಿ ಯೂಸ್ ಫಾರ್ ಕಮ್ಯುನಿಕೇಷನ್ ಸ್ಯಾಟಲೈಟ್. ಅದಕ್ಕೆ ಸೊ ಅಲ್ಲಿ ಅರ್ಥ ಆಯ್ತಲ್ಲ, ನಿಮಗೆ ಸಿಂಪಲ್ ಆಗಿ ಹೇಳಿದ್ದೀನಿ. ಕಮ್ಯುನಿಕೇಷನ್ ಸ್ಯಾಟಲೈಟ್ ಅದೇ ರಿಮೋಟ್ ಸೆನ್ಸಿಂಗ್ ಆ ಥರದ್ದೇನು. ಅಲ್ಲಿಗೆ ರಾಕೆಟ್ ಹೇಳಾಯಿತು, ಎಲ್ಲ ಎಷ್ಟು ಕಷ್ಟ, ಸ್ಯಾಟಲೈಟ್ ಹೇಳಾಯಿತು. ಥರ್ಡ್ ಒನ್ ಮೋಸ್ಟ್ ಆಲ್ ಆರ್ ಡಿಫಿಕಲ್ಟ್. ಥರ್ಡ್ ಒನ್ ಏನು? ಟ್ರ್ಯಾಕಿಂಗ್. ರಾಕೆಟ್ ಹತ್ತೋಣ ಬಿಟ್ಬಿಡ್ತು, ರಾಕೆಟ್ ಕೆಲಸ ಮುಗಿದೋಯ್ತು. ಸ್ಯಾಟಲೈಟ್ ಪಾಪ ಆಗ್ತಾನೆ ಹುಟ್ಟಿದ ಒಂದು ಮಗು ಥರ, ಅದೇನು ಮಾಡಬೇಕು ಅಂತ ಗೊತ್ತಿಲ್ಲ. ಆಲ್ ದೋಸ್ ಥಿಂಗ್ಸ್ ಹ್ಯಾಸ್ ಟು ಬಿ ಡನ್ ಫ್ರಮ್ ದ ಗ್ರೌಂಡ್ ಇಯರ್. ಹ್ಯಾವ್ ಟು ಟ್ರ್ಯಾಕ್ ಇಟ್. ಒಂದು ಸ್ಯಾಟಲೈಟ್ ಒಂದು 10 ವರ್ಷ 8 ವರ್ಷ ಜೀವ ಇರ್ಬೋದು. ಆ 8 ವರ್ಷ 10 ವರ್ಷ ಕಂಟಿನ್ಯೂಸ್ ಆಗಿ ಅದನ್ನು ಟ್ರ್ಯಾಕ್ ಮಾಡ್ತಾ ಇರಬೇಕು. ಅದು ಎಲ್ಲಿದೆ, ಯಾವ ದಿಕ್ಕಿನಲ್ಲಿದೆ, ಅದೇನಾದರೂ ಮಿಸ್ ಆಗೋಯ್ತು ಅಂದರೆ ಗಾನ್, ಫಿನಿಶ್. Thousands of crores of rupees what we have spent will go in the space. So continuously this has to be monitored. ತಿಳಿತಲ್ಲ? So these are the, because I am running short of time, because I want to show you video also, I want to cut short. So anyway, I just want to make it very, very fast. I am sorry for the want of time, I am helpless. Now you all know we did, okay, let me touch up a little bit. Why it started, how it started, by whom it started. It's all started by Dr. Vikram Sarabhai. Dr. Vikram Sarabhai actually born into a very, very rich family. Sarabhai Chemical, Sarabhai Textile, so many things they had. But Vikram, his fascination was different. He was more towards the physics, especially astrophysics, cosmic rays. He was more interested in that. He wanted to study the mysteries of the space. He was more fascinated with that. With that ambition, he opened an institute at Ahmedabad called Physical Research Laboratory. He was the man who brought up that institute. But just bringing up students were not enough. He wanted to do something more. He was there in the States also. There also he learned many international scientists, astrophysicists. They were studying the so many things related to upper atmosphere and whatnot. But they were having some problem there. What is the problem? Say around 40 kilometers above the earth, there is a layer called E layer, electrojet. So electron movement will be there. That is the one it helps for earlier days, for communication. They used to send radio signals from the ground towards up, sky waves, and they used to get reflected. So this area we are getting radio communication. But these layers were not ಯೂನಿಫಾರ್ಮ್ ಆ್ಯಂಡ್ ಕಂಟಿನ್ಯೂಸ್. ಅಲ್ಲಲ್ಲೇ ಪ್ಯಾಚಸ್ಸು ಅಲ್ಲಲ್ಲೇ ಹೋಗ್ತಾಯಿತ್ತು. ಅದಕ್ಕೆ ಒಂದು ಸಾರಿ ಸಿಗ್ನಲ್ ಫೇಡ್ ಆಗಿಬಿಡೋದು, ಒಂದು ಸಾರಿ ಸ್ಟ್ರಾಂಗ್ ಸಿಗ್ನಲ್, ಒಂದು ಸಾರಿ ವೀಕ್ ಸಿಗ್ನಲ್, ಅದೆಲ್ಲ ಆಗ್ತಾಯಿತ್ತು. ಸೊ ದೇ ವಾಂಟೆಡ್ ಟು ಸ್ಟಡಿ ಯಾತಕ್ಕೆ ಈ ಥರ ಆಗುತ್ತೆ ಅಂತ ಇಂಟರ್ನ್ಯಾಷನಲ್ ಸೈಂಟಿಸ್ಟ್. ಅದು ಹೇಗೆ ಸ್ಟಡಿ ಮಾಡಬೇಕು? ದೇ ವಾಂಟೆಡ್ ಟು ಸೆಂಡ್ ಸಮ್ ಸ್ಮಾಲ್ ರಾಕೆಟ್ಸ್ ಗೋ ಅಪ್ ಟು 40 kilometers. ಅದರ ಇನ್ಸ್ಟ್ರುಮೆಂಟೇಷನ್ ಇಟ್ಟಿರ್ತಾರೆ, ಅದರಲ್ಲಿ ಬರೋ ಡೇಟಾ ಅನಲೈಸ್ ಮಾಡ್ತಾರೆ ಆ ಥರ. ಬಟ್ ಅದರಲ್ಲಿ ಪ್ರಾಬ್ಲಮ್ ಅವ್ರಿಗೆ. ಮಾಡಿದಾಗ ಅನ್ಫಾರ್ಚುನೇಟ್ಲಿ ಆ ಎಲೆಕ್ಟ್ರೋಜೆಟ್ ಅನ್ನೋದು ಈಗ ಪ್ಯಾಚಸ್ಸು ಬ್ಲ್ಯಾಂಕ್ ಏರಿಯಾ ಆದರೆ ರಾಕೆಟ್ ಹೊರಟೋಗುತ್ತೆ, ಅಲ್ಲಿ ಸಿಗ್ನಲೇ ಬರೋಲ್ಲ. ಇದು ವೇಸ್ಟ್. ಏನು ಮಾಡಬೇಕು ಅಂತ ತಲೆ ಕೆಡಿಸ್ಕೊಂಡ್ರು. ದೆನ್ ದೇ ಕೇಮ್ ಟು ಎನ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡಿಂಗ್, ಇದು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಈಕ್ವೇಟರ್, ಅಲ್ಲಿ ನಾವು ಸ್ಟಡಿ ಮಾಡಿದ್ರೆ ಸಿಗ್ನಲ್ಸ್ ಸ್ಟ್ರಾಂಗ್ ಆಗಿರುತ್ತೆ, ಅಲ್ಲಿ ಪ್ಯಾಚಸ್ ಜಾಸ್ತಿ ಇರೋದಿಲ್ಲ. ದೇ ವಾಂಟೆಡ್ ಟು ದೇ ಕೇಮ್ ಟು ಎನ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡಿಂಗ್. ಅಲ್ಲೂ ಪ್ರಾಬ್ಲಮ್. ಈಗ ಮ್ಯಾಗ್ನೆಟಿಕ್ ನೋ ಡೌಟ್ ಎಲ್ಲ ಸುತ್ತಾ ಇದೆ, ಆದರೆ ನಾವು ಉಡಾವಣೆ ಮಾಡಿದಿರೋ ಒಂದು ರಾಕೆಟ್ 40 ಕಿಲೋಮೀಟ್ರ್ ಹೋಗಿ ಅದ್ರ ಕೆಲಸ ಮುಗಿದ ಮೇಲೆ ಇಟ್ ವಿಲ್ ಫಾಲ್ ದ ಸ್ಪೆಂಟ್ ಸ್ಟೇಜ್. ದಟ್ ಮೇ ಫಾಲ್ ಇನ್ ಎ ವಿಲೇಜ್ ಆರ್ ಎ ಟೌನ್, ದೇರ್ ಬಿ ಡಿಸಾಸ್ಟರ್. ಅಯ್ಯೋ ರಾಮ, ಅದು ಇನ್ನೂ ಕಷ್ಟ ಆಗಿದೆ, ಅದು ಬೇಡ. ವಿ ಮಸ್ಟ್ ಹ್ಯಾವ್ ಎ ಪ್ಲೇಸ್ ವೇರ್ ದೇರ್ ಇಸ್ ಸಿ, ಸಮುದ್ರ ಇರಬೇಕು, ಮ್ಯಾಗ್ನೆಟಿಕ್ ಈಕ್ವೇಟರ್ ಇರಬೇಕು. ರಾಕೆಟ್ ಮಾಡಿದ್ರೆ ಅದು ಸಮುದ್ರದಲ್ಲಿ ಬೀಳಬೇಕು, ಅಂಥ ಜಾಗ ಆಗಬೇಕು. ಪ್ರಪಂಚದಲ್ಲಿ ಎಲ್ಲ ಕಡೆಯೂ ಹುಡುಕಾಡ್ತಾಯಿದ್ರು. ಸಾರಾಭಾಯ್ ವಾಸ್ ನೋಯಿಂಗ್ ಕೇರಳದ ರಾಜಧಾನಿಯಾದ ತಿರುವನಂತಪುರದಲ್ಲಿಂದ 8 ಕಿಲೋಮೀಟರ್ ದೂರದಲ್ಲಿ ತುಂಬಾ ಅಂತ ಒಂದು ಹಳ್ಳಿ, ಇಟ್ಸ್ ಎ ಫಿಷರ್ಮೆನ್, ಅದು ಬೆಸ್ಟ್ ಇರೋ ಜಾಗ. ದ್ಯಾಟ್ ಪ್ಲೇಸ್ ವಾಸ್ ಬ್ಯೂಟಿಫುಲ್. ಸೊ ಹಿ ಸಜೆಸ್ಟೆಡ್ ಟು ಇಂಟರ್ನ್ಯಾಷನಲ್ ಸೈಂಟಿಸ್ಟ್, ನೀವು ಟ್ರಿವಾಂಡ್ರಮ್ ಬನ್ನಿ, ಮ್ಯಾಗ್ನೆಟಿಕ್ ಈಕ್ವೇಟರ್ ಇಸ್ ದೇರ್, ಅರೇಬಿಯನ್ ಸಿ ಇಸ್ ದೇರ್, ಯು ಕ್ಯಾನ್ ಕಂಡಕ್ಟ್ ಆಲ್ ಯುವರ್ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ಸ್. ದೇ ವರ್ ಆಲ್ ರೆಡಿ. ಅವರ್ ಕಂಟ್ರಿ is a God's gifted country. Such a facility is not available anywhere in the world. When Sarabhai mentioned this, international scientists started coming. Sarabhai ಏನೋ ಹೇಳಿಬಿಟ್ರು, ಆದರೆ ಸರ್ಕಾರದ ಸಪೋರ್ಟ್ ಏನೂ ಇರಲಿಲ್ಲ, ಸರ್ಕಾರಕ್ಕೆ ಗೊತ್ತಿಲ್ಲ ಅವ್ರು ಏನು ಮಾಡ್ತಾರೆ ಅಂದ್ಬಿಟ್ಟು. Sarabhai approached the Kerala chief minister at that time, Mr. Namboodiripad, a communist chief minister. I'll tell you why a communist. Though he understood, though he appreciated Sarabhai, but he had a problem. Being a communist chief minister, around 400 fisher families, Bestru, Baduru, Christians, all those things, the people had to be evacuated. Adu, for a communist chief minister, it was no go. He said, I'm sorry. But Sarabhai did not leave. He approached the Bishop of Kerala. What cannot be done scientifically, he thought he can do spiritually. So he approached Bishop, explained ಮಾಡಿದ್ರು, ಈ ಥರ ಇದೆ ಅಂದ್ಬಿಟ್ಟು. He said, okay, I will come to Tumba. It's a small village. ಯಾವಾಗ ಮೆಸೇಜ್ ಹೋಯಿತೋ, ಆ ಕಂಪ್ಲೀಟ್ ತುಂಬಾದ ಕ್ರಿಶ್ಚಿಯನ್ಸ್ ಎಲ್ಲ, ದೇ ವರ್ ಟೇಕನ್ ಬೈ ಸರ್ಪ್ರೈಸ್. ಬಿಷಪ್ ಈಸ್ ಕಮಿಂಗ್ ಟು ಅವರ್ ಪ್ಲೇಸ್. ಇದಕ್ಕೆ ಸ್ವಾಮಿಗಳು ಮನೆ ಬರ್ತೀವಿ ಅಂದ್ಬಿಟ್ಟು ನಮ್ಗೆ ಹೆಂಗಾಗುತ್ತೋ ಆ ಥರ. ಸೊ ಇಮಿಡಿಯೇಟ್ಲಿ ಹೇಳಿದ್ರೆ ದೇ ವರ್ ಆಲ್ ರೆಡಿ. ಸೊ ಆಲ್ ದೋಸ್ ಪೀಪಲ್ಗೆ ಹ್ಯಾಡ್ ಕಮ್ ಆನ್ ಎ ಪರ್ಟಿಕ್ಯುಲರ್ ಸಂಡೇ. Sarabhai, Chief Minister of Kerala, Collector, all those people also were invited. After the usual puja, whatever was over, the bishop addressed the villagers. This is Sarabhai. This Tumba is not even heard 10 kilometers in Trivandrum. Nobody knows this Tumba. But this scientist will make Tumba an international port. Chief Minister is here. Whatever land you are giving now, plus 1 square foot more you will get. From each family, 1 person will be appointed by Sarabhai. I will give you 5 minutes. I give you promise, Chief Minister will give promise. Everything will be done in 6 months. If it is not done, then you need not give. So I want within 5 minutes, yes or no. So within 5 minutes, all those Christians said, Amen, we agree, we all will vacate. So all those people were evacuated and they were given rehabilitated. Why I am telling you all this was, ISRO was born in the Tumba, a fishing hamlet. As a matter of fact, I will show you the photograph. ISRO, because the building it started in a church building. The church building from where the ISRO started. ಯಾಕಿದು ಹೇಳಕ್ಕೆ ಬಂದೆ, ಯಾಕೆಂದರೆ ವಿಡಿಯೋಗೆ ಹೋಗ್ತೀನಿ ನೆಕ್ಸ್ಟ್ ನಾವು. So why I am telling you this is, if somebody asks a question, where this ISRO was born, what is the growth of ISRO? ISRO was born in a church. ಎಲ್ಲಿ ಹುಟ್ಟಿದ್ದದು? ಅದು ಒಂದು ಬೆಸ್ತರ ಬಸ್ತಿಯಿಂದ ಮಂಗಳದ ಅಂಗಳದ ತನಕ. ಅಂದರೆ ಇಟ್ ವಾಸ್ ಬಾರ್ನ್ ಇನ್ ಎ ಫಿಶಿಂಗ್ ಹ್ಯಾಮ್ಲೆಟ್ and where it has gone? Up to red planet. So our growth is from a fishing hamlet to red planet. ಕನ್ನಡದಲ್ಲಿ ಹೇಳಬೇಕು ಅಂದರೆ ಬೆಸ್ತರ ಬಸ್ತಿಯಿಂದ ಮಂಗಳದ ಅಂಗಳದ ತನಕ. That is the growth of ISRO. You got it? So these are the various things. Now coming back to some of the centers which I am going to just touch up. ರಾಕೆಟ್ ಕಂಪ್ಲೀಟ್ ನಾವು ಮಾಡೋದು ಟ್ರಿವಾಂಡ್ರಮ್ನಲ್ಲಿ ಡಿಸೈನ್ ಮಾಡೋದು. ಅಲ್ಲಿ there are about 4,000 employees are there. ಎಲ್ಲ ಡಿಫ್ರೆಂಟ್ ಲೆವೆಲ್ ಎಲ್ಲ I told you electronics, mechanical, ಎಲ್ಲ structural engineer. So different, there are more than 300 types of engineers are there. One engineer I just want to tell you, just to see your feeling how it will be. ನಮ್ಮ ರಾಕೆಟ್ ತೋರಿಸ್ತೀನಿ ನಿಮ್ಮ ಮುಂದಕ್ಕೆ. ಇಟ್ಸ್ ಎ 4-stage ರಾಕೆಟ್ PSLV. ಅದು ಒಂದೊಂದು ಸ್ಟೇಜ್ ಕಂಪ್ಲೀಟ್ ಆಗಲಿ ದ ಸ್ಟೇಜ್ ಹ್ಯಾಸ್ ಟು ಗೆಟ್ ಸಪ್ರೇಟೆಡ್ ಆ್ಯಂಡ್ ಇನ್ಸ್ಟಂಟೇನಿಯಸ್ಲಿ ದ ನೆಕ್ಸ್ಟ್ ಸ್ಟೇಜ್ ಹ್ಯಾಸ್ ಟು ಗೆಟ್ ಇಗ್ನೈಟೆಡ್. ಸೊ ಇಟ್ ಹ್ಯಾಸ್ ಟು ಹ್ಯಾವ್ ಎ ಕಂಟಿನ್ಯೂಸ್ ಫ್ಲೋ. ಅದು ಸಪ್ರೇಷನ್ ಹೇಗಾಗುತ್ತೆ ಅದನ್ನು ಒಂದು ಮಾತ್ರ ನಿಮ್ಗೆ ಹೇಳ್ತೀನಿ, ಯಾಕೆಂದರೆ ಬಾಕಿದು ಹೇಳೋಕ್ಕೆ ಟೈಮ್ ಇಲ್ಲ, ಯಾಕೆಂದರೆ ಮೋಸ್ಟ್ ಇಂಟ್ರೆಸ್ಟಿಂಗ್ ಇಟ್ ಈಸ್. ಇದು ಹೇಗೆ ಆಗುತ್ತೆ ಅಂದರೆ ನಮ್ಮ ರಾಕೆಟ್ನ ಸುತ್ತಳೆ ಬರೋದು PSLVದು 10 ಅಡಿ ಡಯಾಮೀಟರ್. ಅದರಲ್ಲಿ ಆಲ್ಮೋಸ್ಟ್ ನನ್ನ ಕೈ ಇಷ್ಟುದ್ದದ್ದು ನಟ್ ಆ್ಯಂಡ್ ಬೋಲ್ಟ್ ಇರುತ್ತೆ. ಅದೊಂದು 120 ನಟ್ ಆ್ಯಂಡ್ ಬೋಲ್ಟ್ ಅದನ್ನು ಹಾಕಿ ಒಂದು ಸ್ಟೇಜ್ಗೂ ಕಪಲ್ ಮಾಡಿರ್ತಾರೆ. ನಿಮಗೆಲ್ಲ ನಟ್ ಆ್ಯಂಡ್ ಬೋಲ್ಟ್ ಗೊತ್ತೇ ಇದೆ. ತಲೆ ಭಾಗ ಹೆಡ್ ಅದು ಬೋಲ್ಟ್, ಇದು ಥ್ರೆಡ್ಡಿಂಗ್ ಇರೋ ಜಾಗ, ಕೆಳಗಡೆ ನಟ್ ಇರುತ್ತೆ. ಇದು ನಟ್ ಆ್ಯಂಡ್ ಬೋಲ್ಟ್, ಅದು ಗೊತ್ತಲ್ಲ. ತಲೆ ಭಾಗ ಥ್ರೆಡ್ಡಿಂಗ್ ಪೋರ್ಷನ್, ಕೆಳಗಡೆ ನಟ್. ಇದು ಸಿಂಪಲ್ ನಟ್ ಆ್ಯಂಡ್ ಬೋಲ್ಟ್. ಇದು ಮೆಕ್ಯಾನಿಕಲ್. ಇದು ನಾಟ್ ಆರ್ಡಿನರಿ ಮೆಕ್ಯಾನಿಕಲ್. ಇದಕ್ಕೆ ನಾವು ಪೈರೋ ಸಿಸ್ಟಮ್ ಅಂತ ಹೇಳ್ತೀವಿ. ಪೈರೋ ಟೆಕ್ನಿಕ್ ಅಂದರೆ ಎ ಸಿಸ್ಟಮ್ ವಿಚ್ ಈಸ್ ಎಕ್ಸ್ಪ್ಲೋಸಿವ್. ಅದು ಹೇಗಾಗುತ್ತೆ, ಈ ತಲೆ ಭಾಗ ಹೆಡ್ ಇದೆಯಲ್ಲ ಬೋಲ್ಟ್ನಲ್ಲಿ, ಅದ್ರ ಒಳಗಡೆಗೆ ಟಂಗ್ಸ್ಟನ್ ಫಿಲಮೆಂಟ್ ಇರುತ್ತೆ. ಟಂಗ್ಸ್ಟನ್ ಬಲ್ಬ್ ನಿಮ್ಗೆಲ್ಲ ಗೊತ್ತಲ್ಲ, ಟಂಗ್ಸ್ಟನ್ ಫಿಲಮೆಂಟ್ ಇರುತ್ತೆ. ಆಲ್ಸೋ ಇನ್ಸೈಡ್ ಇಟ್ ಇಸ್ ಫಿಲ್ಡ್ ವಿತ್ ಕೆಮಿಕಲ್ ಅದರಲ್ಲಿ. ಸೊ ದಿಸ್ ಟಂಗ್ಸ್ಟನ್ ಫಿಲಮೆಂಟ್ ಗಿವನ್ ಥ್ರೂ ಎ ಹೆವಿ ಬ್ಯಾಟ್ರಿ, ಹೆವಿ ಕರೆಂಟ್ ಕೊಡುವಂಥ ಬ್ಯಾಟ್ರಿ. through a switch. The switch will be off condition given to a battery. The switch is controlled by the electronic on-board computer, OBC ಅಂತ ಹೇಳ್ತೀವಿ, on-board computer. ಆ ಪರ್ಟಿಕ್ಯುಲರ್ ಹೈಟ್ ರಾಕೆಟ್ ಹೋದ ಕೂಡಲೇ ಆ ಆನ್-ಬೋರ್ಡ್ ಕಂಪ್ಯೂಟರ್ನ ಒಂದು ಕಮಾಂಡ್ ಹೋಗುತ್ತೆ. ಆ ಕಮಾಂಡಿಂದ ದಿ ಸ್ವಿಚ್ ವಿಚ್ ಈಸ್ ಓಪನ್ ದಟ್ ಬಿಕಮ್ ಕ್ಲೋಸ್, ದ ಸ್ವಿಚ್ ಬಿಕಮ್ಸ್ ಆನ್. ದಿ ಮೊಮೆಂಟ್ ದಿ ಸ್ವಿಚ್ ಇಸ್ ಆನ್, heavy current from the battery flows through this tungsten filament. Heavy current ಹೋದರೆ ಏನಾಗುತ್ತೆ ಟಂಗ್ಸ್ಟನ್ ಫಿಲಮೆಂಟ್ಗೆ, ಇಟ್ ವಿಲ್ ಬ್ಲೋ, ಇಟ್ ವಿಲ್ ಬ್ಲೋ ಸ್ಪಾರ್ಕ್. ಅಲ್ಲಿ ಕೆಮಿಕಲ್ ಇರುತ್ತೆ. ಆ ಕೆಮಿಕಲ್ ಆದ ಕೂಡಲೇ ಅದು ಎಕ್ಸ್ಪ್ಲೋಡ್ ಆಗಿ ಹೆಡ್ ಗೆಟ್ ಚಾಪ್ಡ್ ಆಫ್. When all 120 bolts head get chopped off, the stage will fall down. See how difficult this is. Even if 1 or 2 bolts are not separated, rocket instead of this way, it will take this way, because 1 or 2 bolts are not separated. All 120, then only it will fall this way. Now, the pyro engineer who made the pyro system, is he a mechanical engineer? Because nut and bolt. No. He cannot be mechanical. There is battery inside. Battery is there. So he must be an electrical engineer. There is tungsten filament. No. He cannot be an electrical engineer. He must be a chemical engineer, because there is chemical explosives there inside. Now tell me, what sort of an engineer he is? He is an electromechanical chemical engineer. Tell me, which college will teach you this? Can you see, ಯಾವುದಾದ್ರು ಒಂದು ಮಿಸ್ಟೇಕ್ ಆದರೂ ಕೂಡ whole thing will get problem into. So it is so complicated. These are the various types of engineers are there. So there is a special material, like I told you about Kalpana Chawla heat shield. There are so many such issues are there. So for the want of time, I have to cut short. We will go for the video. Okay. Can you reduce this slightly light? Is it possible? You can see from behind, or you want light to be reduced? ಆಗಲ್ವಾ? ಸ್ವಲ್ಪ ಲೈಟ್ ಕಮ್ಮಿ ಮಾಡಿ. ಬರುತ್ತಲ್ವ? ನಾನು ಹೇಳ್ತೀನಿ. ಓಕೆ. ಸ್ವಲ್ಪ ಲೈಟ್ ಕಮ್ಮಿ ಮಾಡಲಿ. ಅದು ಓಕೆ. ಲೆಟ್ ಅಸ್ ಸ್ಟಾರ್ಟ್. ದಿಸ್ ಈಸ್, ಐ ಡಿ ನಾಟ್ ಟೆಲ್ ಯು, Dr. Vikram Sarabhai. He is the father of our Indian space research. Next one. This is the church building where ISRO was born. Like I told you earlier, so this is the church building at Tumba. So where you can say ISRO was born there. Next one. Earlier days, absolutely there was no help, there was no vehicle. We had to carry a part of a rocket on a beautiful vehicle called cycle. That's all the facility what we had. Next one. You can see 2 scientists. The right side scientist is Mr. Satya. He is from Bengaluru only. He is also your neighbor. He belongs to your close, just about 2 kilometers from your house. So this is Mr. Satya. So in Trivandrum, you have to walk almost around 4 kilometers. Trivandrum weather, not like your Bangalore weather. Of course, Bangalore weather also is bad now. So we have to carry the part of a rocket almost 4 kilometers in such a sultry weather. Next one. Can you zoom it? This is the satellite. When we have to take it, before loading it to an aircraft or taking it to French Guiana, because at that time we did not have a rocket, so we were depending on French Guiana, a Ariane rocket, to launch our communication satellite. So we used another beautiful vehicle called Yethin Gadi. So this is the type of support what we had in the earlier days, just to show you how we are born from where we had come up. Next one. Can you zoom it? This is a very, very rare photograph. Somehow I am lucky to show you youngsters what a great photograph it is. There are two scientists working without even a shirt on. The person on the right side is my guru, Abdul Kalam. Whoever has thought the small little fragile fellow will become President of India, can anybody else imagine? Imagine. It's a great person. You can see working with a foreign payload. Next one. Dr. Sarabhai with the first rocket what Kalam has made. Unfortunately, Kalam himself is not there in this. This is the Rohini rocket, RH-75. 75 millimeter is the diameter of the rocket. This is RH-75, what they call it as. And other scientists are there just before the launch. This will go to up to 40 kilometers. Next one. So this is the Centaur rocket from the French people. So we were using some sort of a give and take. So they also used to come and work with us. We also started learning. So we started because Sarabhai made it international port, Tumba. So more and more foreigners started coming. We also started learning. So this you can see a Centaur rocket. Next one. Because of internationally so much famous it became, Tumba. So at that time Prime Minister Srimati Indira Gandhi was there. You can see black Sherwani, that is Dr. Sarabhai. Next to him is Kerala Chief Minister Mr. Nambudripad. So they were all there when the Tumba, called as TERLS, T-E-R-L-S, Tumba Equatorial Rocket Launching Station. So that are dedicated to United Nations. Next one. So the blue shirt, unfortunately Dr. Sarabhai passed away, and in his place Satish Dhawan, who was the director of here of Indian Institute of Science, he has taken over as ISRO chairman. So the other side is Dr. Srinivasan, an aeronautical engineer, and this is Abdul Kalam, whom you all know. Next one. Can you zoom it? So when the SLV, Abdul Kalam was the project director. Behind him is Satish Dhawan, and other dignitaries were there. I hope you all can recognize Abdul Kalam. Only thing is, after he became president, he changed his hairstyle, that's all. Next one. So this is the first SLV. Actually, first SLV was a failure. It did not go up to 80 kilometers. It failed. The most interesting part here was, immediately Satish Dhawan, who was the chairman, he told Kalam, you don't worry, I will go and talk to the press. He went and talked to the press. Subsequently, within the next 6 months, we had next SLV second launch. That was 100% successful. Immediately Satish Dhawan told Abdul Kalam, you go and address the press conference. The meaning in this is, when the failure was there, chairman said it is my responsibility. I failed. When success was there, I got nothing to do. They are the people those who have done. He will go and speak. So the moral of this is, the success is to the team. Failure is to me, because I am the man heading the entire thing. That is the type of culture what we have today. So you can see the success of, but this went up to only 80 kilometers with a 40 kilo satellite. No use. It is only a demonstration. India can do it. we can build our own. So, but just it is no application, no use. So for that what we did, next one, we put two other rockets on the sides called a ASLV, Augmented Satellite Launch Vehicle. With that goes up to 120 kilometers. It means we crossed that 120 kilometer barrier, which I told you in the very beginning, there is no gravity and all that. We had gone. So we had gone into the space. So India became self-sufficient in making our own rocket, our own fuel, our own tracking system, our own satellite. So of the 5 countries were there earlier, India became the 6th country to have all these 3 knowledges. Next one. So by the time we have PSLV, Abdul Kalam also was there, Satish Dhawan were there, and Madhavan Nair was the chairman ISRO. They were all there. Of course, I was also there, but my photo is not there. Next one. Here at SHAR, SHAR means Sriharikota Range. Here, we will not take a stage straight away for launching. So we want to make some ground test, how long it burns, how much of thrust it is giving, whether that nozzle is okay, whether it will withstand, all the parameters to be measured. So you can see the first stage of the rocket is getting tested, static test. Rocket will not be allowed to go, it will be tied up. So we will measure all the parameters. Only when everything is satisfied, then only it will go for launching. Next one. So at Mahendagiri, liquid propellant. So here, as a matter of fact, I am sorry that I should have shown earlier only, our rocket is total height. It comes to here I have a model, hope you can see from behind. This is the PSLV, this is a scaled down model, 1:100. So here you can see this is the first stage of the rocket. So here we use a solid propellant, we use chemical solid, and then 3 strap-on rocket, small rockets are there, but here it looks small because it's scaled down. Actually it is about 20 feet in length, each rocket. So 6 of them plus the main rocket. So this is the nozzle which I was talking about. So this is the first stage of the rocket. That goes to some particular height and that gets separated. And then comes the second stage. Now this becomes the second stage of the rocket. This is the liquid propellant. Here we use, anyway don't bother about that, just for continuation if you want to know, 40% of UD, that we call it as a N2O4. So and then 60% of hydrazine, that is combined together. So 40% of the N2O4, 60% of hydrazine. Don't bother, when you are a chemical engineer in the future, you will learn more about it. That will go to some stage, and second stage gets separated, then comes the third stage. So third stage again solid. So we use a solid, liquid, solid. This goes to some height, and then finally the final stage where the satellite is sitting inside, this is a solid propellant, liquid propellant, sorry. Liquid propellant will be here. Here the satellite is in a heat shield. So heat shield is, like I told you, it has to go through ionosphere. After once it crosses 120 kilometer, heat shield is not required because there is no more problem. So heat shield will be jettisoned, it will be thrown out because we don't want to carry unwanted things. So finally we take the satellite, we release it. So here you can see Mahendagiri, that is at Tamil Nadu border. So there we use the liquid engine. Next one. So this is at the throat, you can feel the temperature at the throat, at the nozzle, how much of temperature will be built. So the metallurgy comes into picture. Next one. You can see the satellite is sitting inside. We want to do testing before we go for actual launch. So we do several times separation. So we put net on either side. This is in the laboratory actually. So because the rocket is going at more than 11.2 kilometer per second escape velocity. If it goes slowly, so there will be a complete collision. So this has to be jettisoned out. How quickly it will be done, that will be checked. Next one. So that is after separation, earlier one of the before separation. So everything is okay, then we go for launching. Next one. So now we have come to Sriharikota. That is the bottommost stage. Here you can see the first stage. It will take in Sriharikota, the huge complex where different laboratories at 3 kilometers, 4 kilometers, 2 kilometers away, because we don't want to put all our, because strategically very difficult. So we don't any damage, anything happens, so it should not get affected. So each laboratory is far, far away. So now the first stage after testing, it will be taken to the launch pad. Next one. So first stage getting assembled. Now you can see almost middle segment one by one getting arranged. Next one. So 6 strap-on rockets one by one they are tested, they are being taken. Next one. After testing, that will be attached to the first stage. Next one. So you can see on the left side the first stage of the rocket is ready, and now next one please. Now first stage is ready, and the roll control thruster which gives the rocket a roll action, that also is getting ready. Next one. So you can see, so first stage at the vertical assembly building, the first stage is ready. This is actually PSLV's continuation 11th flight. As a matter of fact, this month end, somewhere 29th or 30th, date is going to be confirmed very shortly. We are going to have PSLV continuation 56 flights. This is the 11th flight. This is the one did Chandrayaan first mission. 56 flights, there is no problem at all. This is one of the best rocket in the world. NASA also has confirmed PSLV is a workhorse. Thereby, so many foreigners are coming to India to launch. So India has become, long ago, Professor U.R. Rao has told the government of India, in future I don't want money from government of India, I will give money to government of India. That much of confidence he had. So even today we are making PSLV is one of the biggest and most reliable rocket. Now further we had gone to GSLV and all that. So you can see this is the PSLV's continuation 11th flight. Next one. So once the testing is over, second stage is being taken to be connected to the first stage. Next one. We can see first stage and second stage. We can see the pyro engineers are there connecting first stage to second stage. Next one. So third stage is getting ready here now. And there itself is the fourth stage, where that is the brain of the rocket, that will getting ready. Here itself they will combine third and fourth together and they will take it to launch pad. Next one. So third and fourth stage is combined together, that is being moved to the vehicle. Next one. You can see to the main vehicle, third and fourth stage is getting assembled. Next one. Now this is the final stage, only satellite is not there. So that is the fuel tank. All the black boxes you see, they are the electronic packages. That is the one, that is the command on, that is what we call onboard computer, and then so all signal what is to be done, transmitter, everything will be done by that. Next one. So this satellite. So satellite you can see the rocket is only 10 feet, but the solar panel when it is completely opened and turned toward the sun, it will be 30 feet. So here we fold it and keep it. So automatically once it goes to space, we will open that. So you can see how do the testing. So deployment, folding. Next one. So when the satellite is ready, there is only a monitor box. Next one. So that will be attached to the main vehicle now. Next one. So once that final everything is ready, so all rocket people, satellite people, ground station, everybody says we are okay, we are satisfied. Then was ready for the launch. Next one. So the heat shield will be closed. Next one. So once the rocket is completely ready, final tests are over, the building, can you believe it? A 170 feet tall air conditioned steel building that will go 500 meters. Rocket alone will remain there. So steel building that will move 500 meters, because once the rocket takes off, so much of vibration and shock, whole building will collapse. We cannot spend money for each launch. So ISRO engineers, they have made a huge building, a steel building, air conditioned building that will go 500 meters behind. You can see the building has gone behind, rocket is ready for launch. Next one. Only I was there earlier with my mechanical engineer. Next one. So it's a nighttime photograph. Next one. Just to see that everything is normal, ready for takeoff. Next one. T0, half a second, 1 second. Next one. This is just to give a pictorial view how it is at T0 gets launched, and then how it goes. By the time it goes to 73 seconds, the first stage gets, strap-on motor gets separated. And by the time 90 seconds, 106 seconds, the first stage gets separated. And then at 157, it is just about 2 minutes, your heat shield gets separated. And then you can see finally the satellite injection 1017 seconds. 1017 seconds andre you can see less than 17 minutes. In 17 minutes, 70,000 operations will take place. All has to go 100%. Even if one there is a mistake, for us there is 99% is not correct. We want 100%. Then only the satellite will reach at the particular orbit. You can see Government of India wanted at 817 kilometers. The first launch we put at 820 kilometers within 17 minutes. This is the type of achievement. Why I am telling you all this? You youngsters, you should have that dedication. How much we have to, how close you have to see. Just you should not be satisfied with distinction. You must aim. That is the idea of telling this. Next one, please. Okay. Now you can stop. You can go for the video. Now you are going to see, because the time is running very fast, so I am going to show you the entire thing within just about 6 minutes video. So you can see a launch taking place. So you will not hear from me, you will straight away hear it. PSLV C6. So we have the various centers. At Trivandrum, like I told you, we make the rocket design. At Mahendigiri, that is the border of Kerala and Tamil Nadu, where we have the liquid engine. That all satellite will be made in Bangalore here, your satellite center. And all these things will be taken to Sriharikota. Sriharikota, that is Andhra border. There we do the launching. Once it is launched, the tracking will be done here only near Hasana. So we have master control facility. There we do the complete tracking. And also we have the tracking at various different places in the country. So, and also we have at the northeast frontier, that is the Assam. So we can have a border. So there also we have the tracking center. So we have, yeah, started. Yeah. Volume kudi. So, this is the mobile launch pad where the rocket will be assembled. Strap-on motors are getting assembled. Pyro engineers are working. This is the satellite, you can see the solar panel deployment. It opens up to 30 feet. The rocket is only 10 feet, so we keep it folded. Immediately switch on the floodlight instead of sun to see whether battery charging. You see the floodlights are switched on to demonstrate battery charging is okay. Shiva, the project director. Even girl students, if you study well, you can be project directors. This is the French satellite. We were launching not only for our country, we started getting customers from abroad. Heat shield closure. (150 feet tall vehicle inside the building. Now the building will move back 500 meters. Rocket alone will remain ready for launch. You see the building moving away. Nobody will be there near the launch pad. The range safety 8 kilometers away. There only we all will be seated. All data will be coming through the computers and online. This is the launch control center, 8 kilometers away.
Minus 55 seconds. Minus 50 seconds. Minus 45 seconds. Minus 40 seconds. Minus 35 seconds. Minus 30 seconds.
Onboard computer in flight mode.
Radar program activated. Minus 25 seconds. Minus 20 seconds. 15. Nine, 8, 7, 6, 5, 4, 3, 2, 1.
State separation. Heat shield separation. see, in 17 minutes, how many types of operation has to take place?
Chairman, Indian Space Research Organization, Mr. Madhav Nair, and all friends, and day and night, we are all working here. So I congratulate all of you for the excellent performance of PSLV 6 and the Cottersnap 1 and the Hamsat satellite, all in good performance. I was watching, so I was very proud of you. The country is proud of you. Wish you all the best. And I still remember in 1980 July, when I was in the other control center, then 40 kg we launched in the low Earth orbit. Today, we have launched after nearly 25 years, 4,000 kg, equivalent to 1.6 ton in the polar launch orbit. So my hearty congratulations for India is proud of you.
Thank you, sir. My dear colleagues, it's really a historic moment for all of us. In fact, the 9th launch of PSLV taking place from here, and we don't have an adjective to describe this mission. It is perfect, and all the subsystems have worked, so to say, well within the 1 sigma values as seen in the plot board. It's a fantastically accurate trajectory what we have got. And in addition, we have this vehicle surviving the environment for almost 2 weeks outside. Heavy rain, thunders, lightning, and all type of severe environment. In spite of that, it has performed very well. My hearty congratulations to
Okay.
all the team members for this excellent achievement.
Okay, can you switch on the light, please? So I do not know within this short time how much I have convinced you about very smart and do better work. With this only, today PSLV has proven a workhorse. Like I mentioned to you, international customers are coming to us for launching because we are the cheapest. Now it is only PSLV can carry up to 1.6 tons, that is 1600 kg satellite. Whereas a communication satellite may go beyond even up to 4 tons, that is 4000 kg. So we have to go for a bigger vehicle. We are having so many customers are coming, even student community, they are coming with small satellite, 200 kg, 250 kg, we are launching for them. So PSLV is required, no doubt. And now we have to go for a bigger one. So then we gone for GSLV, the geosynchronous satellite. Though we call geosynchronous, that can be used because this will take to around 300 kilometers. The satellite will put there. Then we take it for orbit raising. So we can carry a heavier load to a particular, then we can change the orbit. That's how we can use for even Chandrayaan mission, Mangalyaan mission, we can use GSLV. And also very shortly, might be within next 1 year or so, our Prime Minister is very keen by next, not the coming one, next Independence Day, India should send our own astronauts into the space. That is Gaganyaan. So it is already, work is on. So the technology is altogether different. You cannot just send a person there and forget about him. Poor fellow has to be brought back also. So bringing back is the most difficult one. Like I told you what happened to Kalpana Chawla. It is not only the prestige of the country. Technologically we have to prove and show India is capable of doing that. So the test is going on. Already near Chitradurga, we have done a reusable vehicle, a re-entry, because here you see, after the work is over, the stage falls into the sea. So again we are spending money to make a new rocket. So we are going for a reusable vehicle. That work is already on. So it means, like I mentioned to you earlier, the first stage we got chemical. Future we do not know. You are the bright scientists in the future. You may come out with nuclear energy. So once the rocket weight is reduced and more thrust is possible, we can increase the satellite weight. Now this, it is something like a scooter. So scooter itself is very heavy. Hardly it can carry one person. So if you make the scooter as light as possible, but for the same amount of fuel what you are spending, you can carry more load. So we have to come out with a new energy is required, new metals are required. So there is no end for the science. So the science is the one which can, whether it is agriculture, whether it is health or everywhere, it is very, very important. So with that, I am sorry I have taken too much of time. So it is such a short time. It is, I do not know how far I have convinced you. So God bless you all. Thank you. Jai Hind.
Sir, thank you very much for a very inspiring and interesting talk. I am sure many of the students present here would take up space science as their career. ಎಷ್ಟು ಜನ ಸ್ಪೇಸ್ ಸೈನ್ಸ್ ಓದ್ತೀರಾ? ಕೈ ಎತ್ತಿ ನೋಡೋಣ. ಸಿ ಅಷ್ಟೇನಾ? 5-6. Others would like to become biologists?
If somebody wants any questions, they can.
Oh, yes, sir. Any questions are there?
Any questions?
So, yeah, please.
How does the heat shield get separated?
See, like I told you, the stage separation, nut and bolt I told you, there it is only a question of horizontal separation. Whereas in the heat shield, since it is two half, it has to take vertical as well as horizontal. So here we use the same system what we have got. Here what we call it a zip card. Like a zip is there, you know. There's a zip pulled up and there is a pyro here. One that is a spring loaded, one that is done, that will break out. So the heat shield, vertical separation through zip card, and this one is through Merman band. So like a belt it will be held there, that will get released. So the horizontal separation, vertical separation. Good. Any other question? Yes, please. Speak louder, old man.
Whenever the rocket is moving into its particular stages, when those parts start falling into the sea and all that, wouldn't it affect the marine life? Is there any
I didn't
actions
get the
taken
question.
upon it?
Can you give me the question, please? Can you translate the question? What is it?
Basically, when the parts of the rocket keep falling off, so wouldn't it, she's asking whether it would affect the marine life.
Oh yes, that's a good question. Yeah, she is one of, right. Now, once it falls, a huge shape, let us say it's almost 1 ton, such a huge, when it hits there, anything it hits there, there's a small bounce is there, then it will sink. The moment it comes here, the fish is very smart. The moment something is there, they all will run away. But unfortunately, the fishermen at Andhra, Tamil Nadu, that Bay of Bengal area, they have confirmed with all this foreign material, rocket spent stay, sitting on the sea bed, on the bed here, the marine life has increased. They are enjoying more, some new metal has come there. So their marine life has, suppose some small amount is killed because of the heat, the marine life has increased more here. That get compensated. So there is no harm is taking place. We are very happy. Fishermen has also told us there is no harm here, no problem. But anyway, like I mentioned to you, one of the issues that also can be solved when we come up with a reusable vehicle. When we start using that, this also will not be there. Good question. Right. Any other question?
Any other question? So some of you are inspired by Sir's talk and would like to become space scientists. And I suppose others would like to become biologists because of Sir's talk. In fact, biologists are also required for space science. You know, they would like to colonize Mars. How to colonize Mars? They have to grow plants there and animals. How that is possible? It's only through biologists. So even if you are a biologist, you can enter space science. Even if you are a physicist or a chemist or a mathematician or an engineer, all of you are required for space science. I am sure many take-home messages you got from Sir's talk. I would like to thank Sir once again for a very interesting talk on behalf of KSTA and all of you present. Thank you very much, sir. And KSTA was started by a space scientist, Professor U.R. Rao.
Yeah.
He was the father of satellite technology in India. That is, second chairman was Dr. S.K. Shivkumar. He was the father of deep space network antenna in India. Have you, any of you have gone to Balal? Balal. You please visit Istrak, Balal. There we have 32-meter antenna through which we get information about Mangalayaan or Chandrayaan or other satellites through that antenna.
Very near to Dodda Aldamara.
Yeah.
Have to go that side.
Yeah.
So there you have a deep, big antenna is there.
So thank you.
Bailalu is
Yeah,
that.
Balal. So all of you go for lunch. After half an hour, please come. We'll be having one more talk. And also 3D shows will also be there.
Request all of you here to assemble at 2:30.
You know, in IISc, Indian Institute of Science, there is one department called MBU. There in that department, all faculty members are there. That means biology, then engineering, earth science, space science, what not. All branches of science faculty members are there in MBU. That is in IISc. Like that, see, up to MSc or engineering, there is what we call it as a specific program. After that, anybody can choose anything and he can go for any field of research. So this is what. And one more thing, I don't know whether you heard the name Satyendranath Bose. Maybe in the year 2012, you heard about the God particle. It is not the God particle, it is actually Higgs boson, but somehow the publisher has given the name God particle. That is how every person in the earth was able to understand what that mean is. Anyway, and in that, actually the standard atomic model was introduced by a team of scientists. They got the Nobel Prize in the year 2013, and in that, of course, the basic thing which was done by our own scientist Satyendranath Bose, but he is no more. That is why he could not share the Nobel Prize. So for getting the Nobel Prize, one should be alive, only then he will get the Nobel Prize. Anyway, this is with even our Indian contribution, especially in CERN, European research, nuclear research in Geneva, lot of our scientists are working and they are trying to understand the Big Bang theory. So it is only to understand the Big Bang theory, the work is going on there. Of course, you can also part of it. So let me now start with the basic experiments. I ask you to come here. I am not offering the chair, but I am doing some experiment on him. Just sit down, please. Get up straight away. No, you should not bend. Yes? Yes, okay, you can please take your seat back. Yes, anybody, can you tell me why we are not able to get up without bending ourselves? Why we cannot get up after sitting? Yes, center of gravity and not the center of mass. Center of mass remains the same, but the center of gravity changes. Only when the body is symmetric, uniform, then the center of mass and the center of gravity are coinciding. Otherwise, the center of mass remains the same. For example, for a body like this, it is uniform and the center of mass is at the center. And the center of gravity also coincides with this center of mass. But for some other thing, maybe something like this, if you take a pen or some other thing, then the center of mass may not coincide with the center of gravity. For example, if you take the center of gravity, the center of gravity may be inside the body or may be outside. That depends. Anyway, when you come to higher classes, you will understand whether it is inside the body always or even it could be outside. That is a different story. I will come back to it. And coming to another simple experiment, for example, let us say I will take the pen like this. I want to balance this pen. Is it possible to balance it? No, I am not able to balance it. You can take your own pen and try to balance it. You tell me whether you are able to balance the pen or pencil, not necessarily only the pen. You can try even with pencil also, but you will not be able to balance it. And I take a belt like this. I will just fix it. You see, now it is balanced. What may be the reason for balancing this pen after the belt is fixed to the pen? Can you tell me? It is again the center of gravity. So, the center of gravity is shifted. That is the same reason there also a boy who was not able to get up straight, only when, not only that boy, anybody for that matter will not be able to get up unless we bend ourselves. When we bend, the center of gravity shifts. Only when the center of gravity shifts, then we will be able to do something else. Same thing, you can try with any belt, not necessarily the belt which I am using here. Any belt you can try, and any pen, you will be able to balance it only with the help of something. Not necessarily the belt, anything you can use, but only thing is that should be able to withstand there. So, this is what we can understand the meaning of the center of gravity. And again I repeat, the center of mass may not coincide with the center of gravity always. Only in some cases where the bodies are symmetric in the sense on the left side as well as on the right side, if they are equal, and not only the sizes are equal and even the masses are also equal, only then the center of mass and the center of gravity will be at the same position. I do not know whether you have seen the longitudinal waves and transverse waves. ಅಂದರೆ ನಾವು ಕನ್ನಡದಲ್ಲಿ ಅದನ್ನು ಅಡ್ಡ ತರಂಗ ಮತ್ತು ಉದ್ದ ತರಂಗ ಅಂತ ಹೇಳ್ತೀವಿ. ಅಂದರೆ ಉದ್ದ ತರಂಗ ಅಂತ ಅಂದರೆ ಎನಿವೇ ಯಾವುದೇ ವೇವ್ ಬರಬೇಕಾದರೂ ವೇವ್, it is because of the vibration. Even when I am talking, the tongue is vibrating, and only because of the vibration of the tongue the sound is produced. And even in a musical instrument, whether you take harmonium, guitar, any instrument, only when the instrument is like if the string is vibrating, then the sound is produced. So, for example, the light wave which he was asking, the speed of light, can anyone tell me what is the speed of light? 3 into 10 raised to 8 meter per second. Very good. So, that is the speed of light, and of course, it is not possible to achieve the speed of light in any other medium other than some important media which I am not going to. Anyone who has already seen this? the transverse and this is what we call it as the slinky. And in this you can of course two boys can come here and you can play with this. Play with this in the sense, yes, you just hold it there at that end. Yeah, you can go to that end. That's why I asked for. Yeah, you can see that. Yes, yeah, you can just do like this. Yeah, you just push it also. And basically in this we have got two type of things. One is compression, ಅದನ್ನೇ ಕನ್ನಡದಲ್ಲಿ ಕಂಪನ ಅಂತೀವಿ. Another one is rarefaction. The compression and the rarefaction. Because of the compression in the sense, okay, you can just push it, you can see that at some position, ಸ್ವಲ್ಪ you can just see that both the longitudinal and the transverse waves are produced in a string like this, and this is one setup to understand the concept of the longitudinal and the transverse wave. Yes, you can please. Of course, even when we are using the fan, at some position we feel it is hot, and at some other position of course it is cool. What may be the reason? At one position it is hot and at another position it is cool. This is where when the compression takes place, that means when the fan is rotating, the air molecules which are around the fan will naturally push. When the air molecules are pushing, at some position the air molecules get compressed. When the air molecules get compressed, the temperature increases. And on the other hand, when the air molecules get separated, that means they are not compressed, and that is what we call it as the rarefaction. So when the air molecules get separated, the temperature decreases. That is where we see the cooling effect. That means if you sit at one position you feel hot and at another position you feel cool. This is only because of the compression and the rarefaction of the air molecules. Yeah, that is whatever we see around. You know, for example, in a paddy field, especially before ಅಂದರೆ ನಾವು ಗದ್ದೆ ನೋಡಿದಾಗ ಕಟಾವ್ಗೂ ಮುಂಚೆ ಆ ಭತ್ತದ ಇವ್ರು ಎಷ್ಟು ಜನಕ್ಕೆ ಭತ್ತ ಮರನೋ ಗಿಡನೋ ಅಂತ ಕೇಳಿದ್ರು ಹೇಳೋಕ್ಕಾಗುತ್ತೋ ಇಲ್ವೋ. ಅದು ಗಿಡ ಅಂತಂದರೆ ಚಿಕ್ಕ ಚಿಕ್ಕದು, ಅದು ಒಂದ್ರ ಮೇಲೆ ಒಂದು ಹೊತ್ಕೊಂಡಿರುತ್ತೆ. ಅಂದರೆ ಅಲ್ಲಿ ಕಂಪ್ರೆಷನ್ ಒಂದೊಂದು ಹೊತ್ಕೊಂಡಿದ್ರೆ ಅಲ್ಲಿ ಕಂಪ್ರೆಷನ್ ಅಂತೀವಿ, ಸ್ವಲ್ಪ ದೂರ ಇದ್ದಾಗ ರೇರಿಫ್ಯಾಕ್ಷನ್ ಅಂತ. ಅಂದರೆ ಗದ್ದೆ ಅವರು ಕೊಯ್ಲಿಗೂ ಮುಂಚೆ ಅಂದರೆ ಕಟಾವ್ಗೂ ಮುಂಚೆ ಕೂಡ ಆ ಥರ ಕಾಣಿಸುತ್ತೆ. ಹಾಗೆಯೇ ಈ ಅಡಿಕೆ ಮರಗಳು ಕೂಡ, ಅಡಿಕೆ ಮರ ಅಂತಂದರೆ ನೋಡಿದ್ದೀರಲ್ವಾ, ಅಡಿಕೆ ಅದು ಏನಾಗಿದೆ ತುಂಬ ತಿನ್ನಾಗಿರೋದ್ರಿಂದ ಗಾಳಿ ಬೀಸೋದೆಲ್ಲ ಬರುತ್ತೆ. ಅಂದರೆ ಒಂದು ಮರ ಇನ್ನೊಂದು ಮರ ಹೊತ್ಕೊಳ್ಳುತ್ತೆ. ಸೊ ಒಂದು ಮರ ಇನ್ನೊಂದು ಮರ ಹೊತ್ಕೊಳ್ಳುತ್ತೆ ಅಂದರೆ ಇನ್ನೊಂದು ಮರ ಬಿಡಿ ಆಗಲೇಬೇಕು. ಅಂದರೆ ಒಂದು ಕಡೆ ಕಂಪ್ರೆಷನ್ ಆದರೆ ಇನ್ನೊಂದು ಕಡೆ ರೇರಿಫ್ಯಾಕ್ಷನು. ಹಾಗೇನೆ ಟ್ರಾನ್ಸ್ವರ್ಸ್ ವೇವ್ಗೆ ಸಮುದ್ರದ ದಡದಲ್ಲಿ ಯಾರಾದರೂ ನೋಡಿ ಹೋಗಿದ್ರೆ ಒಂದು ಕಡೆಯಿಂದ ವೇವ್ ಆ ಕಡೆಯಿಂದ ಬರುತ್ತೆ, ಅಂದರೆ ಎಲ್ಲ ಗಾಳಿಗೆ ಬರುವಂಥದ್ದು, ಮತ್ತೆ ಬಂದು ದಡದಿಂದ ಮತ್ತೆ ವಾಪಸ್ ಹೋಗ್ತಾ ಇರುತ್ತೆ, ಆವಾಗ ಅದು ರೈಸ್ ಆಗುತ್ತೆ. ಅಂದರೆ ಈ ಟ್ರಾನ್ಸ್ವರ್ಸ್ ವೇವಲ್ಲಿ ನಾವು ಕ್ರೆಸ್ಟ್ ಆ್ಯಂಡ್ ಟ್ರಫ್ ಅಂತೀವಿ. ಲಾಂಜಿಟ್ಯೂಡಿನಲ್ ವೇವಲ್ಲಾದರೆ ಕಂಪ್ರೆಷನ್ ಆ್ಯಂಡ್ ರೇರಿಫ್ಯಾಕ್ಷನ್ ಅಂತೀವಿ. ಹಾಗೆಯೇ ಟ್ರಾನ್ಸ್ವರ್ಸ್ ವೇವಲ್ಲಾದರೆ ದಿ ಕ್ರೆಸ್ಟ್ ಆ್ಯಂಡ್ ಟ್ರಫ್. ಕ್ರೆಸ್ಟ್ ಅಂದರೆ ಮೇಲೆ ಕುಬ್ಬೋದು, ಟ್ರಫ್ ಅಂದರೆ ಕೆಳಗಡೆ ಹೋಗೋದು. ಹಾಗೆಯೇ ಏನೋ ಒಂದು ಸಣ್ಣ ಪಾಂಡ್ ಇದೆ ಅಂತ ಇಟ್ಕೊಳ್ಳಿ, ಆದರೆ ತುಂಬ ಹತ್ತಿರ ಹೋಗಬಾರ್ದು ನೀವು, ಯಾಕೆಂದ್ರೆ ಇನ್ನು ನೀವು ಮಕ್ಕಳಾಗಿರೋದ್ರಿಂದ. ಒಂದು ಸಣ್ಣದೊಂದು ಕಲ್ಲನ್ನು ತೆಗೆದು ಅಲ್ಲಿ ಹಾಕಿದ್ರೆ ಆಗ ವೇವ್ಸ್ ಬರೋದು ಗೊತ್ತಾಗುತ್ತೆ, ಅದು ಟ್ರಾನ್ಸ್ವರ್ಸ್ ವೇವ್ಸ್. ಅಂದರೆ ನಮ್ಮ ವಾಟರ್ ಮೇಲೆ, ನೀರಿನ ಮೇಲೆ ನಮಗೆ ಟ್ರಾನ್ಸ್ವರ್ಸ್ ವೇವ್ ಕಾಣಿಸುತ್ತೆ, ಅದರ ಒಳಗಡೆ ಲಾಂಜಿಟ್ಯೂಡಿನಲ್ ವೇವ್ಸು ಕೂಡ ಇರುತ್ತೆ. ಅಂದರೆ ಟ್ರಾನ್ಸ್ವರ್ಸ್ ವೇವ್ಸು ಮತ್ತು ಲಾಂಜಿಟ್ಯೂಡಿನಲ್ ವೇವ್ಸು ಸೈಮಲ್ಟೇನಿಯಸ್ ಆಗಿ ಬರುತ್ತೆ. ಆದರೆ ಇಲ್ಲಿ ಟ್ರಾನ್ಸ್ವರ್ಸ್ ವೇವ್ಸ್ ಕಾಂಪೊನೆಂಟ್ ಜಾಸ್ತಿ ಇರುತ್ತೆ ಲಾಂಜಿಟ್ಯೂಡಿನಲ್ ವೇವ್ಸ್ಗಿಂತ. ಹಾಗೆ ಈ ಅರ್ತ್ ಕ್ವೇಕ್ ಟೈಮಲ್ಲಿ ಲಾಂಜಿಟ್ಯೂಡಿನಲ್ ವೇವ್ಸನೇ, ಅದನ್ನೇ ಸೀಸ್ಮಿಕ್ ವೇವ್ಸ್ ಅಂತೀವಿ. ಆ ಸೀಸ್ಮಿಕ್ ವೇವ್ಸ್ ಅನ್ನೋದು ಕೂಡ ಲಾಂಜಿಟ್ಯೂಡಿನಲ್ ವೇವ್ಸು. ಇದನ್ನು ಯಾಕೆ ಇದನ್ನು ಅಂದರೆ ಆ ಎಲ್ಲ ಎಕ್ಸಾಂಪಲ್ಸು ಹೇಳೋದಕ್ಕೋಸ್ಕರನೇ ಇದೊಂದನ್ನು ತೋರಿಸಿದ್ದು. ಅಂದರೆ ಲಾಂಜಿಟ್ಯೂಡಿನಲ್ ವೇವು ಮತ್ತು ಟ್ರಾನ್ಸ್ವರ್ಸ್ ವೇವು ಒಂದೇ ಮೀಡಿಯಮಲ್ಲಿ ಒಂದೇ ಮೆಟೀರಿಯಲಿಂದನೂ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡ್ಬೋದು. ಆದರೆ ಒಂದು ಕಡೆ ಟ್ರಾನ್ಸ್ವರ್ಸ್ ವೇವ್ ಕಾಂಪೊನೆಂಟ್ ಜಾಸ್ತಿ ಇರುತ್ತೆ, ಇನ್ನೊಂದು ಕಡೆ ಲಾಂಜಿಟ್ಯೂಡಿನಲ್ ವೇವ್ ಜಾಸ್ತಿ ಇರುತ್ತೆ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ಈಗ ಯಾವುದೋ ಒಂದು ಸಾಂದ್ರತೆ ಅಂದರೆ ಡೆನ್ಸಿಟಿ ಅಂತೀವಿ. ಹೇಗೆ, ಹೌ ಡು ಯು ಫೈಂಡ್ ಔಟ್ ದಿ ಡೆನ್ಸಿಟಿ? ಕ್ಯಾನ್ ಯು ಟೆಲ್ ಮೀ? ಎಸ್, ಡೆನ್ಸಿಟಿ ಈಸ್ ಮಾಸ್ ಬೈ ವಾಲ್ಯೂಮ್. ಬರೀ ನಾನು ಸಿಂಬಲ್ಸ್ ಮಾತ್ರ ಬರೀತೀನಿ. m/v, ಮಾಸ್ ಬೈ ವಾಲ್ಯೂಮ್. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ರೆಗ್ಯುಲರ್ ಬಾಡಿ ಇದ್ದಾಗ, ವೆನ್ ವಿ ಹ್ಯಾವ್ ಎ ರೆಗ್ಯುಲರ್ ಬಾಡಿ ಲೈಕ್ ದಿಸ್, ವಿ ಕ್ಯಾನ್ ಫೈಂಡ್ ಔಟ್ ದಿ ಮಾಸ್. ಯಾವುದಾದ್ರೂ ಸ್ಪ್ರಿಂಗ್ ಬ್ಯಾಲೆನ್ಸ್ ಯೂಸ್ ಮಾಡ್ಬೋದು, ಡಿಜಿಟಲ್ ಬ್ಯಾಲೆನ್ಸ್ ಯೂಸ್ ಮಾಡ್ಬೋದು, ಎನಿ ಮಾಸ್. ನಾನು ಐ ಡಿಂಟ್ ಗಿಟ್ ದಿ ಬಿಕಾಸ್ ನೋ ಟೈಮ್ ಟು ಕೀಪ್ ಆನ್ ಮೆಜರಿಂಗ್ ಆ್ಯಂಡ್ ಫೈಂಡಿಂಗ್ ಔಟ್. And how do you find out the volume of a rectangular piece like this? Mass we can find out by using balance. Whether you go for a digital balance, nowadays we go for a digital balance rather than the mechanical balance like spring balance. ನೋಡಿದ್ದೀರಾ ಸ್ಪ್ರಿಂಗ್ ಬ್ಯಾಲೆನ್ಸು? ಆ ಸ್ಪ್ರಿಂಗ್ ಬ್ಯಾಲೆನ್ಸಲ್ಲಿ ಆದರೆ ನೇತು ಹಾಕಬೇಕು. ಆದರೆ ಡಿಜಿಟಲ್ ಬ್ಯಾಲೆನ್ಸ್ ಏನಿಲ್ಲ, ಅದರ ಮೇಲೆ ಇಟ್ಟರೆ ನಮಗೆ ಅದರ ನಂಬರ್ ಗೊತ್ತಾಗುತ್ತೆ. ಬಟ್ ಮೆಕ್ಯಾನಿಕಲ್ ಅದು ಅನಲಾಗ್ ಅಂತ ಕೂಡ ಹೇಳ್ತೀವಿ. ಆ ಸ್ಪ್ರಿಂಗ್ ಬ್ಯಾಲೆನ್ಸಲ್ಲಾದರೆ ಆ ಪಾಯಿಂಟರ್ ಎಲ್ಲಿ ಅಟ್ಯಾಕ್ ಆಗಿದೆ ಅಂತ ಅನ್ನೋದನ್ನ ನೋಡ್ಕೋಬೇಕು, ಅದು ನೋಡೋದು ಕಷ್ಟ ಆಗುತ್ತೆ. ಈಗ ಡಿಜಿಟಲ್ ಆದರೆ ಇಟ್ ಈಸ್ ವೆರಿ ಈಸಿ ಟು ನೋ. ಆಯಿತು. ಸೊ ವಾಲ್ಯೂಮನ್ನು ಹೇಗೆ ಪತ್ತೆ ಹಚ್ತೀರಾ? ಡೆನ್ಸಿಟಿ ಬೇಕು ಅಂದರೆ ವಿ ವಾಂಟ್ ಟು, ಲೆಟ್ ಅಸ್ ಎ ಮಾಸ್ ಗೊತ್ತಿದೆ, ವಾಲ್ಯೂಮ್ ಪತ್ತೆ ಹಚ್ಚಬೇಕು. ಹೌ ಟು ಫೈಂಡ್ ಔಟ್ ದಿ ವಾಲ್ಯೂಮ್? LBH, ವೆರಿ ಗುಡ್. ಲೆಂತ್ ಇಂಟು ಬ್ರೆಡ್ತ್ ಇಂಟು ಹೈಟ್. ಈಗ ಇದನ್ನೇ ಲೆಂತ್ ಅಂತ ಅಂದ್ಕೊಂಡು, ಇದನ್ನು ಬ್ರೆಡ್ತ್ ಅಂದ್ಕೊಂಡು, ಇದನ್ನು ಹೈಟ್ ಅಂತ ಕರಿಬೋದು. LBH ಫಾರ್ ಎ ರೆಕ್ಟಾಂಗ್ಯುಲರ್ ಪೀಸ್. ಅದೇ ನಮಗೆ ಏನಾದ್ರೂ ಕ್ಯೂಬ್ ಇದ್ದರೆ, ಘನ ಅಂತ ಹೇಳ್ತೀವಿ, ಕ್ಯೂಬ್ ಇದ್ದರೆ ಆವಾಗ L³ ಅಂತೀವಿ. ಅಂದರೆ ಲೆಂತು ಬ್ರೆಡ್ತು ಹೈಟು ಎಲ್ಲ ಈಕ್ವಲ್ ಆಗಿರುತ್ತೆ. ಅಂಥದನ್ನು ನಾವು ಕ್ಯೂಬ್ ಅಂತೀವಿ. L³ ಅಥವಾ B³ ಅಥವಾ H³ ಅಂತ ಕರಿಬೋದು. ಸೊ ಹಾಗಾಗಿ ಅದರ ಇದನ್ನು ಮಾಡ್ಬೋದು. ಲೆಟ್ ಅಸ್ ಸೇ ಐ ವಾಂಟ್ ಟು ಫೈಂಡ್ ಔಟ್ ದಿ ಮಾಸ್ ಆಫ್ ಸಮ್ ಇರ್ರೆಗ್ಯುಲರ್ ಬಾಡಿ. ಇರ್ರೆಗ್ಯುಲರ್ ಬಾಡಿ ಅಂದರೆ ಯಾವುದೋ ಒಂದು ಸ್ಟೋನ್ ಇದೆ ಅಥವಾ ಈ ಥರದ್ದು ಯಾವುದೋ ಇದೆ ಅಂತ ಇಟ್ಕೊಳ್ಳಿ. ಏನು ಮಾಡೋದು? ಹೌ ಟು ಫೈಂಡ್ ಔಟ್ ದಿ ಡೆನ್ಸಿಟಿ ಆಫ್ ದಿಸ್ ಮೆಟೀರಿಯಲ್? ಬಿಕಾಸ್ ವಿ ಆರ್ ನಾಟ್ ಏಬಲ್ ಟು ಫೈಂಡ್ ಔಟ್ ದಿ ಲೆಂತ್ ವಿ ಕ್ಯಾನ್ ಫೈಂಡ್ ಔಟ್, ಬಟ್ ಈವನ್ ಬ್ರೆಡ್ತ್ ವಿ ಕೆನಾಟ್ ಫೈಂಡ್ ಔಟ್ ಫಾರ್ ಎ ಮೆಟೀರಿಯಲ್ ಲೈಕ್ ದಿಸ್. ಆರ್ ಫಾರ್ ಒಂದು ಯಾವುದೋ ಒಂದು ಸ್ಟೋನ್ ತಗೋತೀರಾ, ಪೆಬಲ್ ಅಂತ ಕರಿತೀವಿ. We can't find out the density of that irregular material. How to find out? Display, Archimedes principle. Yes, for Archimedes principle, of course, we use a measuring jar. I just explain, otherwise ಇಲ್ಲಿ ನೀರೆಲ್ಲ ಚೆಲ್ಲುತ್ತೆ. ಅದಕ್ಕೋಸ್ಕರ measuring jar ತಗೋತೀವಿ. Of course, first we ಟೇಕ್ ವಾಟರ್, ಯಾವುದೋ ಒಂದು ಲೆವೆಲು, ಮೇ ಬಿ ಲೆಟ್ ಅಸ್ ಸೇ ಇಲ್ಲಿ ಒಂದು 40 cc ತಗೋಬೋದು ಅಂತ ಇಟ್ಕೊಳ್ಳಿ. ಫಾರ್ ಡೆನ್ಸಿಟಿ ಅಗೈನ್ ವಿ ಕ್ಯಾನ್ ಫೈಂಡ್ ಔಟ್ ಲೈಕ್ ದಿಸ್. ವಾಲ್ಯೂಮ್ V1 ಅಂತ ಕರ್ಕೊಳ್ತೀನಿ. V1 is equal to dash dash. Maybe I can put it as centimeter cube itself. ಏನು, ಸಪೋಸ್ ಐ ವಾಂಟ್ ಟು ಕನ್ವರ್ಟ್ ಫ್ರಮ್ ಸೆಂಟಿಮೀಟರ್ ಕ್ಯೂಬ್ ಟು ಮೀಟರ್ ಕ್ಯೂಬ್, ಹೌ ಡು ಐ ಡೂ ದಟ್? ಈಗ ಇದು ಸೆಂಟಿಮೀಟರ್ ಕ್ಯೂಬ್ ಅಂತ ಬರೆದಿದ್ದೀನಿ. ಆದರೆ SI ಯೂನಿಟ್ಸಲ್ಲಿ ನಿಮ್ಗೆ ಈಗಾಗಲೇ ಗೊತ್ತಾಗಿದೆ SI ಅಂದರೆ ಏನು ಅಂತ. ಏನು SI ಅಂದರೆ? ಇಂಟರ್ನ್ಯಾಷನಲ್ ಸಿಸ್ಟಮ್ ಆಫ್ ಯೂನಿಟ್ಸ್. ಆ ಇಂಟರ್ನ್ಯಾಷನಲ್ ಸಿಸ್ಟಮ್ ಆಫ್ ಯೂನಿಟ್ಸಲ್ಲಿ ನಾವು ಮಿಲಿಮೀಟರ್ನಲ್ಲಿ ಹೇಳಬೇಕು, ಇಲ್ಲ ಮೀಟರ್ನಲ್ಲಿ ಹೇಳಬೇಕು. ಈಗ ಸೆಂಟಿಮೀಟರ್ ಹೇಳ್ತಾ ಇದ್ದೀನಿ ಅಂದರೆ ಸೆಂಟಿಮೀಟರ್ ಕ್ಯೂಬ್ ಅಂತ ಅನ್ನೋ ಬದಲು ಅದನ್ನು ಮೀಟರ್ ಕ್ಯೂಬ್ಗೆ ಏನು ಇಂಟು 10⁻⁻6 ಆಗುತ್ತೆ. ಯಾತಕ್ಕೆ? ಬಿಕಾಸ್ 1 ಸೆಂಟಿಮೀಟ್ರಿಗೆ ಅಥವಾ 1 ಮೀಟ್ರಿಗೆ 100 ಸೆಂಟಿಮೀಟರ್ ಅಥವಾ 1 ಸೆಂಟಿಮೀಟರ್ ಈಕ್ವಲ್ಸ್ 10⁻² ಮೀಟರ್. ಹಾಗೆ ಕ್ಯೂಬ್ ತಗೊಂಡಾಗ 10⁻⁻⁶ ಮೀಟರ್ ಕ್ಯೂಬ್ ಆಗುತ್ತೆ. ಸೊ ವಾಲ್ಯೂಮ್ ಐ ಕ್ಯಾನ್ ಫೈಂಡ್ ಔಟ್, ಅಂದರೆ ಎಷ್ಟು ಲೀಟ್ರ್ ಇದೆ ಅಥವಾ ಎಷ್ಟು ಸಿ ಸಿ ಇದೆ, ಕ್ಯೂಬಿಕ್ ಸೆಂಟಿಮೀಟರ್ ಅಂತ. ಸಿ ಸಿ ಮೀನ್ಸ್ ಕ್ಯೂಬಿಕ್ ಸೆಂಟಿಮೀಟರ್, ಅದನ್ನೇ ನಾನು ಸೆಂಟಿಮೀಟರ್ ಕ್ಯೂಬ್ ಅಂತ ಬರೆದಿದ್ದೀನಿ. ಹಾಗೆ ಇಲ್ಲಿ ನಾನು ಎಷ್ಟು ಒಂದು 40 cc ತೊಗೊಂಡಿದ್ದೀನಿ, ವಾಟರ್ನ ತೊಗೊಂಡಿದ್ದೀನಿ ಅಂತ ಅಂದ್ಕೊಳ್ಳಿ, ನೀವು ಬೇಕಾದರೆ ಟ್ರೈ ಮಾಡ್ಬೋದು. ಆಫ್ಟರ್ವರ್ಡ್ಸ್ ಐ ವಿಲ್ ಪುಟ್ ದಟ್ ಮೆಟೀರಿಯಲ್ ಇರ್ರೆಗ್ಯುಲರ್ ಬಾಡಿ ಇನ್ ಟು ದಿಸ್. ಇರ್ರೆಗ್ಯುಲರ್ ಬಾಡಿನ ಇದ್ರೊಳಗಡೆ, ಅಂದರೆ ಇದ್ರೊಳಗಡೆ ಮುಳುಗೋ ಅಷ್ಟು ನೀರನ್ನು ತಗೋಬೇಕು, ಕಡಿಮೆ ತಗೊಂಡ್ರೆ ಗೊತ್ತಾಗಲ್ಲ. ಸೊ ಹೇಗೆ ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ, ವಾಲ್ಯೂಮ್ ಜಾಸ್ತಿ ಆಗುತ್ತೆ. ವಾಲ್ಯೂಮ್ ಜಾಸ್ತಿ ಆಗುತ್ತೆ ಅಂದರೆ ಅದನ್ನು ನಾವು V2 ಅಂತ ಕರ್ಕೋಬೋದು. Again in centimeter cube, or we can put it in meter cube. Then we can find out the mass of that irregular material. However it is irregular, the mass of that can be found out. So now we know the net volume. That volume is nothing but V2 minus V1. Mass we can find out, and I have already written down the formula, and that formula is D is equal to m by V. So we can find out the density of the irregular material. Suppose we have water up to this rim, then after putting the material inside, then water will come out. We can also measure how much water is come out, and instead of spreading water outside, we can take in the material, rather in the measuring jar itself. Instead of taking up to the rim, we can take up to 3/4 or half, whatever it is, but only condition is the material which you want to find out the density should be immersed in this volume. So suppose I take the pencil. So if I take the pencil, I don't know where I have kept. No, yeah, here I have. Suppose I rub it like this, you can easily move it. How you can easily move it? What may be the reason for that? It is what we call it as rolling friction. Friction andre ಘರ್ಷಣೆ ಅಂತ ಹೇಳ್ತೀವಿ ಕನ್ನಡದಲ್ಲಿ. So friction, that means this pencil, of course, if you want to move it, you can just rotate like this. So that is where ನಾವು ಮೂರು ಫ್ರಿಕ್ಷನ್ ಅನ್ನು ಹೇಳ್ತೀವಿ. ಒಂದು ಸ್ಟ್ಯಾಟಿಕ್ ಫ್ರಿಕ್ಷನ್ ಅಂತ, ಇನ್ನೊಂದು ಕೈನೆಟಿಕ್ ಫ್ರಿಕ್ಷನ್, ದ ಅದರ್ ಒನ್ ಈಸ್ ರೋಲಿಂಗ್ ಫ್ರಿಕ್ಷನ್. ಸ್ಟ್ಯಾಟಿಕ್ ಫ್ರಿಕ್ಷನ್ ಜಾಸ್ತಿ ಇರುತ್ತೆ ಕಂಪೇರ್ ಟು ಕೈನೆಟಿಕ್ ಫ್ರಿಕ್ಷನ್, ಹಾಗೆ ರೋಲಿಂಗ್ ಫ್ರಿಕ್ಷನ್ ತುಂಬ ಕಡಿಮೆ ಇರುತ್ತೆ. ಅದು ಒಂದು ನೀವು ಟ್ರೈ ಮಾಡ್ಬೋದು. ಆ್ಯಂಡ್ ನೌ ಐ ವಿಲ್ ಕಮ್ ಟು ದಿ ಎಕ್ಸ್ಪರಿಮೆಂಟ್ ಆಫ್ ಬರ್ನೌಲಿಸ್ ಪ್ರಿನ್ಸಿಪಲ್. ಬರ್ನೌಲಿಸ್ ಪ್ರಿನ್ಸಿಪಲ್ ಕೇಳಿದ್ದೀರಾ? ಆ ಅಪ್ಲಿಕೇಶನ್ ಅಂತೂ ತುಂಬ ಇದೆ. ಬರ್ನೌಲಿಸ್ ಪ್ರಿನ್ಸಿಪಲ್, ಒನ್ ಆಫ್ ಯು ಕ್ಯಾನ್ ಕಮ್, ಜಸ್ಟ್ ಕಮ್ ಹಿಯರ್. ಇದನ್ನಲ್ಲಿ ಇಟ್ಕೊಂಡು ಆ ಕಡೆ ತಿರ್ಕೊಂಡು ಚೆನ್ನಾಗಿ ಊದಬೇಕು. ಇದನ್ನು ಸ್ವಲ್ಪ ಯು ಡೋಂಟ್ ನೋ, ಯು ಹೋಲ್ಡ್ ಲೈಕ್ ದಿಸ್, ಟರ್ನ್ ದಟ್ ಸೈಡ್, ಯು ಹೋಲ್ಡ್ ದಿ ಬಾಲ್ ಲೈಕ್ ದಿಸ್ and blow air into it. You have to blow air into it and see what happens. But hold the ball like this initially, and you should not hold it permanently. Yes, you can blow air into that. Little up. No. Yeah, you hold like this first and leave you blow air. Yeah, with all your force you hold it. What is that? You could notice. Yes, the ball remain fixed there. So anybody else can try? You can just wipe it. Yes, could you try? Anybody wants? Yes, please. Yes, you can go there. Turn that side. First you touch it and then leave it after blowing air into it. ಇನ್ನು ಜಾಸ್ತಿ ಊದಬೇಕು. ಯು ಕ್ಯಾನ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ಕನ್ನಡ? ಓಕೆ ದೆನ್. ಊದಬೇಕು, ಚೆನ್ನಾಗಿ ಊದಬೇಕು ಅಲ್ಲಿ ಹಿಡ್ಕೊಂಡು. keep it up, ಒಂದು ಫಿಂಗರ್ನ ಇಟ್ಕೊಂಡಿರೋ, ಆಮೇಲೆ ಬಿಟ್ಬಿಡು. ಮೊದಲಲ್ಲ, ಊದ ಮೇಲೆ ಬಿಡಬೇಕು. ಎಸ್, ಎಷ್ಟು ಶಕ್ತಿ ಇದೆಯೋ ಅಷ್ಟು ಊದಬೇಕು. ಓಕೆ. ವಾಟ್ ಇಸ್ ದಿ ಪ್ರಿನ್ಸಿಪಲ್ ಬಿಹೈಂಡ್ ದಿಸ್? The principle behind this, of course, I am just showing only this funnel and the ball, but this principle is used everywhere, anywhere. For example, nowadays we are using for COVID, what is that called? Sanitizer. Yes, in the sanitizer what you see that you just push it down, then that solution will come out. Why? What may be the reason? Pumping. That is because of the pressure difference. That pressure difference we can write it as P2 minus P1 or P1 minus P2, anyway we can write. See, at the bottom of the sanitizer, the pressure difference, the pressure is at the atmospheric pressure. Even at the top surface, the pressure remains the same. But when once we just press it, either we will press it by our leg, so the provision is made either way, or let us say we press it by our finger at the top. Nowadays more by leg rather than the finger. Whatever it is, we have to press it at the top. When we press it at the top, the pressure decreases. Because of the decrease in pressure, the velocity increases, and therefore that liquid will come out in the form of fine droplets. So we can, or even if you go for a scented bottle, there also we just press it, then it will come out. Or even for some paint, even in paint also they do the same principle, just they press it, it will come out. So not only in this, even for the example of aeroplane, all of you, I think you have seen the picture of the aeroplane at least. So what happens there, initially the pressure below the wing and the pressure above the wing will be the same, but it has been made in such a way that the pressure here is more than the pressure on the top. And not only that, the wing has been made in such a way that the air, which we call it as the boundary layer, that means that air is just pushing like this. So when the air is just pushing above, then the air here, the pressure of the air is more, and as the pressure of the air in the below the wing is more, naturally the flight is able to go up or lifted. So there again we use the same principle. So what happens here is, when once we blow air, anyway initially the pressure below as well as the pressure above remain the same. No difference in pressure between below and above. But when once we blow air into it, then the pressure decreases and velocity increases. And that is what we write down the formula like this: P plus half rho V square is equal to a constant. That means here, as pressure decreases, velocity increases, either way. So if pressure decreases, the velocity increases, or if velocity decreases, the pressure increases. This is what we call it as the Bernoulli's theorem or Bernoulli's principle, and that Bernoulli's principle is used almost every day in our life, and that is again the basic physics. And that basic physics can be understood with a simple experiment like this. One more experiment I wanted to show, but again we want hot water and cold water. Just ask you a question. Let us say I have one beaker. Of course I have to get hot water and I have to go to the canteen to get it. That's why I just show you. Suppose we have two beakers. Let us say you can try at home. All these experiments you can just try at home. Let's say I take two beakers. In one beaker I take cold water, and in another beaker I take hot water. I just put 1 or 2 drops of ink in both the beakers. In which beaker the ink, the spreading of ink is more? In hot water. What may be the reason? Yes, because of the temperature. When the temperature is more, naturally the velocity, that is again we study from kinetic theory of gases. It is what we call it as the kinetic theory, and that kinetic theory is again studied, of course, not only in physics, and even in chemistry they study about the hot water and cold water. Now what I do, I take, of course, I fill this completely with water. This, you can see anyone, I am filling it up. Oh, sorry, I think. Water is filled in this completely, and even a little more I can put. So what I am doing now, I take, oh yes, I have some iron balls. Can anyone tell me how many balls can be put in this water? Yes, already I have filled it up. Any number of iron balls, how many number of iron balls can be put inside that? All the balls? What may be the reason? Not all the ball? Not all the balls, only up to some number, not all. Because I have got some 300, 400 here, even though my size is small. Yes, anyway, what may be the reason for that? Some more number of balls can be put it on that, even though it is completely filled. No. Water. That is the reason I am asking. Otherwise, we can put everything. Suppose I put one, no water is coming out, I have completely filled it. I can just say like this. Some already 10 I have put. Even now, it is not coming out. What may be the reason? I think already some 20, 30 are there. Like that you can go up to some, I have tried up to 200. The water will not come out. What may be the reason? Huh? Ions. Surface tension, you are near to that. Actually, we are not able to see the meniscus. That is what we call it as the meniscus. That means the water will be formed like this. We are not able to see that. This is what we call it as the meniscus. Water is here. Are you able to see this diagram? I am not writing neatly because of time, no doubt. So there will be a meniscus. That meniscus we can see only if you take a very narrow tube. That is what we call it as a very narrow tube, means it will be like this. Suppose you take that, we actually call it as the capillary tube. It will be like this, a very narrow tube. That means here you have only narrow opening. Let us say we put this in water, then water will rise inside, but not inside the tube. The water will rise here. That is what we understand by what is called cohesive force and adhesive force. Adhesive, not ADD, it is ADHI. ADHI, adhesive and cohesive force. So because of this, that between the glass and the water, of course, the force will take place, and therefore we will be able to See the difference? That means the water rises, but not in a bigger tube. Why? The adhesive force will not be dominant over the cohesive force. Suppose we have a bigger tube, and if you dip it in water, the water level will not rise, but a small meniscus can be noticed. But here the meniscus will be there, but we are not able to see the meniscus, and that even after putting some iron balls there, that meniscus is slightly coming up, and that is why the water will not spill out even if we put some 50, 100 iron balls. You can try at home if you have small iron balls like this, or even if you take little bigger balls, and with bigger balls about 30 to 40 we can put it, and this of course we can go up to 200. Now of course all of you have seen this. This is what we call it as an optical fiber. You have heard of this optical fiber, isn't it? And if this light is intensity of this light is more, we may not be able to see this, but still let me try. Yes, let me see. Yeah. Suppose I just pass the laser beam like this. What we understand that the light travels along a straight line, that we also call it as the rectilinear propagation of light. Of course, that rectilinear propagation of light was introduced by Newton, that we call it as the Newton's corpuscular theory of light. That was introduced in the year 1672. In fact, before the Newton corpuscular theory of light was introduced, it was Descartes. He introduced the concept, but he was not able to establish that, and it was only Newton who explained about this. That means light travels along a straight line. He also made another statement, or rather another theory. What is that? I think you only if the second year PUC students are there they may be able to give me the answer, but other students. According to Newton's corpuscular theory of light, the speed or the velocity of light, of course with respect to light or sound we can use the word velocity or speed, but when we come to mechanics we have to carefully use the word velocity or speed. Anyway, you will understand it later. But velocity of light is greater in denser medium than that of the rarer medium. That was given by Newton's corpuscular theory of light, but it was proved wrong. Huygens, he conducted the experiment from one mountain to another mountain about 80 kilometer or 50 miles. And based on that experiment he came to the conclusion, he proposed the theory that the velocity of light is greater in rarer medium than that of the denser medium. But it was Foucault, that was in the year 1850, conducted the experiment from one mountain to another mountain with a distance of 80 kilometer or 50 miles, and he came to the conclusion with the experiment that velocity of light is greater in rarer medium than that of the denser medium. For example, if you take the velocity of light in air or vacuum, it is 3 into 10 raised to 8, but in case if you find out the velocity of light in water, it comes to be about 2 point something. Anyway, yes, and you can see that can you see that even though it is bent, the light is visible at the corners. But in your home, if you have this fiber scope or optical fiber, you can also see various colors because it is rotating. Here I am not rotating it and I do not have a different color laser. So if you have a different color, then if you keep on rotating you would be able to see different lights. What may be the reason? How the light is bending here, that is what my question, in an optical fiber. Yes, it is based on total internal reflection. So, what is the total internal reflection? The total internal reflection ಅದನ್ನೇ ನಾವು ಕನ್ನಡದಲ್ಲಿ ಸಂಪೂರ್ಣ ಆಂತರಿಕ ಪ್ರತಿಫಲನ ಅಂತ ಕರಿತೀವಿ. ಪೂರ್ಣ ಆಂತರಿಕ ಸಂಪೂರ್ಣ ಪ್ರತಿಫಲನ, ಟೋಟಲ್ ಇಂಟರ್ನಲ್ ರಿಫ್ಲೆಕ್ಷನ್. Total internal reflection. What actually happens there? That is an optical fiber. Let us say it is bent like this, and then it is cladded like this. With the, of course, it is made either with glass or plastic, and the refractive index inside this is greater than the refractive index of the cladding. The refractive index, let us say here it is about 1.55. The refractive index of this fiber, the size of the fiber is very, very small, of the order of 10 raised to minus 6 meter. That is very, very small. Of course, there are several such fibers there. And this refractive index is maybe about 1.50 or even less. So, when the refractive index is less, let us say the light source is here, let us say this is the object, and when once the light is incident on this, it undergoes total internal reflection. That means it comes to all, and again the total internal reflection takes place here, then it goes to the other, then it will be like this, then it finally comes out, and we are able to see this. Suppose a person is here, he will be able to see. That is only because of the total internal reflection. And total internal reflection, you know that it takes place only when the light passes from denser to rarer medium. You know that when the light is passing from rarer to denser medium, andre kadame ಸಾಂದ್ರತೆಯಿಂದ ಹೆಚ್ಚು ಸಾಂದ್ರತೆ ಅಂತ. So, when the light passes from rarer to denser medium, it bends towards the normal. But as the light passes from denser to rarer medium, the light bends away from the normal. What happens when the light is in the direction of the normal? Now, it was explained, and a formula was also given by Snell. That is what we write it as sin I by sin r. Let us say the angle of incidence is 0. That means the light is in the direction of the normal. So, when the light is passing in the direction of the normal, the angle of incidence is 0. If the angle of incidence is 0, what would be the angle of refraction? That is also 0. Yes. So, when I is equal to 0, r is equal to 0, and sin 0 over sin 0. What is the value of sin 0? 0. What is the value of 0 by 0? Not defined. Yes, very good. So, Snell's law does not hold good. Then what may be the other way of defining the refractive index? Anyway, Snell's law does not hold good. We cannot say that there is no refractive index, or refractive index is not determinable. That is what from this law. For example, if you find out the refractive index of water, what is the refractive index of water? 1.33 or 4 by 3. That is the refractive index of water. How about the refractive index of glass? There are variety of glasses, but normally we think of only two types in our theory. One is crown glass, the other one is flint glass. Crown glass is of the order of 1.5, and flint glass is almost touching 1.6, 1.5758 like that. So, that is how the crown glass is different from that of the flint glass. How about the refractive index of diamond? Actually, it is 2.42, but we may write about 2.45. And especially when we go to purchase diamond, whether it is real diamond or artificial diamond, No artificial diamond will have the value of refractive index 2.45. Any artificial diamond will be less than even 2, not even 1.5, 1.6. That means in case if you want to purchase the diamond, real diamond, then you have to ask that person, shop owner, to give the refractive index of the diamond. So, and in front of you, he has to measure. Of course, there are now the devices to measure the refractive index directly, but normally in our physics laboratory we find out the refractive index by using the travelling microscope. Of course, we will later on see the travelling microscope, either the refractive index of water or the refractive index of the glass slab like this, we find out by using travelling microscope, and we find out it is 1.433 or 1.33 or 4 by 3. That is for water, and for glass it is about 1.5. And diamond we can't get it, and therefore we only know the theory and not in the experiment we have found out. Experimentally it has been found out, but normally we don't go for determining the refractive index of diamond in the laboratory. You know the reason why we are not finding out the refractive index of diamond. So, coming to now, again I take water in this. I think again if the light is there, I may not be able to show you this, but let us see whether you can, and if some, okay, I put some sawdust here, then it will be clearly visible. So, if I can you see anything? Can you see total internal reflection? Yeah, from wall to wall it is visible, and if it is little dark means we will be able to see very clearly. Because of the light we are not able to see it clearly. Yes, can you see? Yeah. How? The refractive index of that glass is more than the refractive index of water. The light is passing from water to glass, and the total internal reflection takes place like what I have explained in respect of this. And not only with that, you can try even with a test tube. Yes, you can also, but anyway, if you use red laser, you may not be able to get it so clearly like this. This is again so even with a test tube, let us say, yes, can you see? You can see that the total internal reflection takes place. Either you take a glass jar, yeah, that will go there, but you can see only here, inside, not outside. Yes. Is it visible there, this total internal reflection? And because of the light, I think it is not clearly visible. Salpa onchuru salpa off madi. Can you see? Yes, I think now it is good. Okay. So, the angle should be maintained, otherwise it is not possible to see that. So, if the angle is how much? Because there is a relation between the refractive index and the critical angle, only when that means we write that n sin c is equal to 1. n, this is the theory, n sin C is equal to 1, where C is called the critical angle. Only when the critical angle is greater than about 42 degree in respect of glass, then we would be able to see the total internal reflection, not otherwise. So, this is what you see here, and now I will go for some experiments on two plane mirrors. For example, if I have two plane mirrors, yes, any two, I am giving you two plane mirrors. I am sure that the other students who are sitting at the back will not be able to see this. Yes, you can hold like this, yeah, and I ask you to change the angle, and I think I have coin, some bright coin, I will place it on. So, how many coins you can see there? Coins in the sense images. Not? Yeah, hold like this correctly. Yeah, tell me how many images are visible. Maybe you can see from there. 4. Suppose you decrease the angle. Yeah, hold like this. Yes, how many are there? 5. Suppose you decrease further. And there is a relation, or what we call it as a formula for that. Suppose I write like this, n is equal to 360 by theta minus 1 if it is odd, and n is equal to just 360 by theta if it is, this is even number and this becomes odd. Suppose theta equals 90 degree. So, that is the formula. If theta is equal to 90 degree, yes, you can have, I think you have your pen and paper. You can tell me what would be the value of 360 by 90. 4. 4 minus 1, 3. So, if you put exactly 90 degree, then you will have 3 images. That means here I have the of course the, if you want we can put it like this. Yeah, here you can make the protractor like this. That means you take the protractor, go for xeroxing, and you have to increase the size. Suppose you put it like this, you can measure actually how much angle you can set, 90 degree, 60 degree, like that. Suppose I have 60 degree, how many images are there? You can verify the theory with the experiment. So, this is not simply we say that 360 by theta, that means 360 by 90 minus 1 is equal to 3. You have the theory here and you can conduct the experiment, and based on that experiment we would be able to say that how many images are formed. Yes, anybody wants to try, you can try. It is not simply listening and going away. You have to have some experimental skill or experimental background. Only when we have, why I am telling this, in our Karnataka we are concentrating more on theory rather than experiment. I don't know whether you heard of the Olympiads. We have even for 9th standard we have one competition like junior science. They go to national level and international level also. I tell you only in brief about our examination. IAPT, Indian Association of Physics, is conducting the examination, and finally HBCSE, Homi Bhabha Center for Science Education, that will take. That means initially if there are 10 students in any school, the center will be given, and now it has been made 20 because more number of centers are there. Earlier even there were 10 students, the center was given. Because of more number of schools coming forward to conduct this examination, it has now been made 20. So if we have 20 students in a school or a college, then the center will be given. Normally this examination will be conducted in the month of November. National Science, Junior Science, Astronomy A and Astronomy B, and for PU students both first year and second year, or anyone up to second year only, then that is what we call it as NSEP, National Standard Examination in Physics, National Standard Examination in Chemistry, National Standard Examination in Biology. But maths, it will be done separately, and even for the maths also, that is International Olympiad is there. So at the initial level, let there be any number of centers and any number of students can take, but next level, in the second level, all India level, only 200 students will be selected based on the experiment conducted at the primary level or initial stage. So for those 200 students, then examination will be conducted both in theory as well as in experiment. Yes, if you have done, you can go and sit. So if you have 200 students, then for those 200 students, of course the center will be changed. Only 35 students will be selected. If there is tie-up, then 36 will go for 36, like that. So 35 students. These 35 students will be given training in HBCSE, that is Homi Bhabha Science Center for Education in Bombay. And for those 35 students, both travelling allowance, food, everything, stay, everything will be taken care of by HBCSE, that is government only. And 15 days training will be given both in theory as well as in the experiment. So training will be given in the sense not the regular experiments. So some experiments the students can think of, or even the faculty will think of. So like that some experiments will be done and theory will also be done, and finally the examination will be given to those 35 or 36 students, and only 5 students will be selected, and those 5 students in physics, chemistry, biology will go for the International Physics Olympiad. So it will be done usually in different countries, Thailand or even America has not conducted so far, England, like that, Ireland. Many countries have already conducted, and sometimes it will also come in our newspaper about our International Physics Olympiad, Chemistry, Biology. So why I am telling you that, what we have found out that our Karnataka students are good in theory, no doubt. They are very excellent, but very poor in experiment. Very poor in the experiment means when we have asked them, even the least count of the slide calipers do not know for the students. That is the state of affair of our Karnataka students. If I ask what is the least count of the slide calipers, in other words called the vernier calipers, no idea for them. That means maybe we are not teaching properly. So if we teach them properly to the students, naturally they will be able to understand. If we don't teach them, or if we don't conduct the experiment, naturally no student will try to do the experiment rather than studying the theory. That is why I am just showing you some experiments and what is the principle behind each experiment. Suppose we do some experiment like what I told you about the Bernoulli's principle. It is not that we are conducting only here. It is used everywhere. So that is why we have to understand the basic principle through the experiments. So like for example, if we have, let us say I go for theta is equal to 0, then how many images will be obtained? Yes, anyone? Infinity, very good. So you have an idea. And I don't know, you must have seen in some temple or in some place, one mirror will be there on one side and another mirror will be there on the other side. And suppose we are in between, then we see that number of images. We are not able to count how many images are there, then we call it as infinity or infinite, and the symbol which we use for that is this one, infinity. Infinite number of images are seen if we have two plane mirrors parallel to each other. So if they are parallel to each other, the angle between them is 0, and 360 by 0, anything divided by 0 is infinity. How about 0 by anything? Let us say 0 by 1 is what? 0. Any number 0 divided by any number becomes 0, but any number divided by 0 is infinity. So that is why 360 by 0 is infinity. Minus 1 means when you are subtracting from infinity minus 1, it is nothing. That becomes infinity. Plane mirrors are parallel to each other. If they are parallel, the angle between them becomes 0, and if the angle is 0, the number of images obtained becomes infinity. So this is one thing which you can try at home. And you know about the long sight or the short sight. And especially, in fact, about 10 days back, I went to one place, village, Vasagavi near Maddur Taluk, near Maddur. About some 100 students were there. No student was wearing spectacles. In the sense, no short sight. But here in city area, many will be there, at least 20 to 30. Even here I can count many are there with short sight. I know about what do you mean by short sight. Can you tell me? You have short sight. You know that? You don't know. She has got short sight. What is your power? Now you are not muscle power, the eye power. What is that? How do you say that? I think madam can tell me what is her power. Minus. Yes, short sight means we are not able to see or we are not able to read an object more than 25 centimeter. That means the least distance of distinct vision for a normal eye is 25 centimeter. Suppose we are able to read the book comfortably at a distance of 25 centimeter, that means our eyes are normal. Suppose I am not able to read the book properly at a distance of 25 centimeter, and if I want to hold it close to my eyes, then definitely I come to the conclusion that I have short sight. On the other hand, again it is because of age. For me, I am not able to read the book or see the object clearly at a distance of 25 centimeter, but I can read it or see it clearly if it is more than 25 centimeter. If we can see more than 25 centimeter, that means long sight. Yes, what is the lens you are using? That also at least concave. Yes, for short sight we use concave lens. How does that concave lens look? It will be like this. This is concave lens. And convex lens is like this. For short sight we are using concave lens, and for long sight convex lens. For example, for me it is convex lens. The spectacle which I am using is convex. Usually after 40 years, not that everyone should have. Sometimes, you know, if a person is about 80 years or even more, he or she may not be using the spectacle. What do we understand from that? The reason for that is, initially when he was underage child, short sight must be there. The short sight is going to long sight, and that span may be 10 years, 15 years, like that. That means if a person is not using lens or spectacles for reading the book, means he or she must have short sight, and that short sight is tending to long sight, and therefore, let us say it was about 10 centimeter initially, and now it must have come to 25 centimeter, and therefore, he or she need not have to use the lens. Anyway, for short sight we use concave lens, and the power of the lens is diopter. And how do we say 1D? The power of the lens is 1D, 1 diopter. The power of the lens is 1 diopter if we have focal length 1 meter or 100 centimeter. And for a convex lens it is positive, and for a concave lens it is negative. For children, of course, even before some 20 or 15 years, it must be concave lens, and they will have negative power. So that is what we have. Anyway, in our India, we don't have much about other than this long sight and the short sight. But in other countries, we also notice some other defect. That is what we call it as astigmatism. For determining the astigmatism, a physics student, not necessarily an ophthalmologist, he or she can understand whether a student or anybody else will have an astigmatism. That means, let us say here I have written like this, all of equal intensity, 2, 2. And for a student or for any person, it does not matter whether student or not a student. Let us say this number 2, 2 appears to be bigger in size compared to other. Even though I have written same intensity, the 2, 2 may appear to be bigger in size compared to the other numbers. And then again I rotate it. Again this 4, 4 appears to be bigger in size compared to the other numbers. Even though it is, the intensity of this line is same as the intensity of the other lines, but it appears to be something different from others. If it appears like that, then we come to the conclusion that the person will have a defect, what is called astigmatism, ASTI, astigmatism G. So this is what we have. And now, of course, I just want to show you how through focal length of, yes, what is that concave mirror? I was only talking about the lenses, of course the mirrors. Coming to the mirrors, concave mirror means it will be like this, and convex mirror means a silvering on the convex side, then it becomes concave. Concave means ಅದನ್ನೇ ನಾವು ನಿಮ್ನ ದರ್ಪಣ ಅಂತ. ಸೊ ಅಲ್ಲಿ ತೋರಿಸಿದ್ದು ಅದು ಸಮತಲ ದರ್ಪಣ ಅಂದರೆ ಪ್ಲೇನ್ ಮಿರರ್ಸ್. ಇದು ನಿಮ್ನ ಇದು ಪೀನ ಮಸೂರ, ಇದು ನಿಮ್ನ ಮಸೂರ. ದಟ್ ಮೀನ್ಸ್ ಕಾನ್ಕೇವ್ ಮಿರರ್, ದಿಸ್ ಈಸ್ ಕಾನ್ವೆಕ್ಸ್ ಮಿರರ್. And you know, in a concave mirror the real image is obtained. It depends on the focal length. For example, here the focal length may be 10 centimeter. I have the concave mirror, convex mirror, and even the object. We don't know whether we can do the experiment. Anyway, I have brought the bulb ಬೇಕಾಗಿತ್ತು. If I want to do the experiment, I will anyway tell you that. Let us say here it is focal length. What do you mean by focal length? And before I go for the concave mirror or anyway convex, let us say I have the convex lens. How do I distinguish between the convex lens and the concave lens? After that, I will go for that. Mirrors. Suppose I have a convex lens. You are given the lens. How do you distinguish between the convex lens and the concave lens? So, convex lens means thicker at the center, thinner at the edges. If it is thicker at the center and thinner at the edges, then we say that it is a convex lens. I length without any instrument. I don't have to go for a lamp and then screen and then stand. Without anything, I should be able to find out the focal length of this convex lens. How can we find out? Anyone? Yes? Let us say you are given a convex lens. I am not giving you anything, a lamp, a screen or anything, stand. I am asking you to find out the focal length of this. Yes, anybody else? Not necessarily only he should answer. I don't know even power. If I know the focal length only, then I can find out the power. So, basic thing, the focal length itself is not known to me, but still I want to find out the focal length. Only after finding out the focal length I would be able to find out the power of the lens, because anyway the formula is P is equal to 1 over F. I did not write it on the board. P equals 1 over F. That is how the relation between the power and the focal length. I think this must have been told you even at the high school level. Let us say not here, we may have to go out, and let us say the sun shining is there, bright sun is there, and on one side I may have some piece of paper. You don't know that? So, I have a piece of paper here, and you do the experiment carefully. Hold the paper with the help of some stand or rather something, rather than holding by hand, because you know, when I say something, if you get a chance to do this experiment in the field, and if you hold the piece of paper directly from your hand, and your finger or anything else may burn. That is why I am repeating, put a piece of paper on some stick or something like that, and hold the lens like this. Maybe because the sun, depending on the position of the sun, you hold the lens and keep on adjusting it. At one position the paper gets burnt out. At that position the principal focus, that is principal focus, then that the distance between the lens and the position where the paper gets burnt, and that distance is focal length. So, this is the crude method. And other method is also, let us say we have some big building or some big tree, and we will have a piece of paper here. Here we are not getting any burn or something like that. We hold the screen. Screen means the piece of paper or some white book, cover page is white. Then I hold the lens like this. You would be able to see the image. What type of image is observed here? The image becomes inverted, diminished, and anyway the distance from this to this is focal length. It is real, diminished, inverted. So, these three properties you will notice: inverted, diminished and real. Why do we say it is the real image? Because we are able to get the image on the screen. So, if we can get the image on the screen, then that image is real. On the other hand, if we look at our face in a plane mirror, we do not get the real image, and that is only the virtual image. In fact, in a convex lens we get the real image, but in a concave lens we get the virtual image. Yes, can anyone tell me what type of lens? Oh, sorry, I should go to the mirror and then ask you the question. Anyway, let us say we want to find out the focal length of the concave lens. because we are not getting the real image, we are not able to measure it, but still we want to find out the focal length of the concave lens. How to find out? Can anyone tell me? Yes, that is convex lens. ಸರ್ ಇನ್ನು ಎಷ್ಟೊತ್ತು ತನಕ ತಗೋಬೋದು? ಹೌದಾ? ಓಕೆ, ಯಾಕೆಂದರೆ ಒಂದು ಮಾಡೆಲ್ ಇದೆ. ಲೆಟ್ ಮಿ ಸಿ ವೆದರ್ ಇಟ್ ವರ್ಕ್ಸ್. ಎ ಸಿ ಜನರೇಟರ್ ಆ್ಯಂಡ್ ಡಿ ಸಿ ಜನರೇಟರ್ ಐ ಹ್ಯಾವ್ ಬ್ರಾಟ್. ಇದು ಹೇಳಿಬಿಟ್ಟು ಆಫ್ಟರ್ವರ್ಡ್ಸ್ ಐ ವಿಲ್. ಹಾಂ, I can find out the focal length. How do you find out? Anyway, I forgot to get the lamp. Otherwise, I could have shown. Lamp ಬೇಕು. This is the screen. That means we normally put a bulb here, and that becomes the screen. And then we have a stand like this. We will put it like here, the stand. And then let us say we have a screen, and that of course bulb idre ಈಗಲೇ ತೋರಿಸ್ಬಿಡ್ಬೋದಾಗಿತ್ತು. I don't think anyway they have the bulb. ಅಲ್ಲ, ಇದಕ್ಕೆ ಇದು ಈ ಬಲ್ಬ್ ಅದು ಆಗುತ್ತೆ, ಅದನ್ನೇ ಬಿಡ್ಬೋದು, ಆಗ್ಬೋದು. ಸರ್ ಇದು ಬಿದ್ದೋಗ್ಬಿಟ್ರೆ ಕಷ್ಟ. Because let us say I keep the lens like this, and here we have ಲೇಸರ್ ಆದರೆ ಸರಿ ಹೋಗಲ್ಲ. ಇದನ್ನು ಟ್ರೈ ಮಾಡಿ, ಒಂದು ಸ್ವಲ್ಪ ಇದು ನೋಡಿ ಅಡ್ಜಸ್ಟ್ ಮಾಡಿ, ಅಲ್ಲಿ ತೋರಿಸ್ತೀನಿ ಅಲ್ಲಿ. ಸೊ ಫಾರ್ ಎ ಕಾನ್ವೆಕ್ಸ್ ಲೆನ್ಸ್ ವಿ ಯೂಸ್ ದಿ ಫಾರ್ಮುಲಾ ಲೈಕ್ ದಿಸ್. 1/f equals 1 minus 1/u plus 1/v, right? But for a mirror it is 1/f equals 1/u plus 1/v. ಬರ್ತಾ ಇದೆಯಾ? Yes, sir. Yes, that's what I think he is getting it. What we do with this experiment, we measure the distance from the, this is considered as the object. Can you see? You will see that bigger image. And on the other hand, suppose I put it like here, then you get the diminished image. ಹೊಡೆದೇ ಹೋಯ್ತಾ ಇದು? ಇರಲಿ ಬಿಡಿ, ಹೋಗುತ್ತೆ ಆಮೇಲೆ ತಗೋ. So here we get the diminished and almost the same size. Yes, I will explain that also. Yes, the formula is 1/f equals minus 1/u plus 1/v for a lens. And for a mirror, it is 1/f equals 1/u plus 1/v. Why? When we are measuring the distance, because in a mirror we call it as the pole. What is that? Center of, that is the pole of the mirror. Pole means kendra anta, and pole. And in the lens we call it as the optic center. ಅದನ್ನೆಲ್ಲ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡೋಕ್ಕೆ ಹೋಗೋದಿಲ್ಲ, because it takes time. So optic center, we measure the distance from the pole of the mirror to the object, or rather the image, sorry, ಎರಡನ್ನೂ measure ಮಾಡ್ತೀವಿ. And in a lens, let me first explain this. In a lens, because we have conducted the experiment and he has shown the image, let us say I am using this formula 1/f equals minus 1/u plus 1/v. But of course here the object is real, therefore we take it as positive. And if image is real, we take it as positive. If the image is virtual, when do we get the virtual image in respect of a convex lens? The virtual image is obtained when the distance is less than 10 centimeter. Let us say if the focal length of the lens is 10 centimeter, and if we place the lens less than 10 centimeter, then we get the virtual image. If we get the virtual image, then we are getting minus 1/v here. Otherwise, it is plus. And we use this formula, we find out, let me call that as f1. We are not able to find out the focal length of the concave lens by this method, and therefore what we do, we take both the concave lens and the convex lens and find out like this. Let us say this is the Yes. This is concave lens. I don't know whether you are able to see that. Thinner at the center, thicker at the center. In order to find out the focal length of this concave lens, what we do, we combine these two. That means we put a rubber band on this and then place it here. If anybody wants, you can try and put it on the stand like this and then find out the distance again here like this. I find out by a combination like this 1 over f equals 1 over u plus 1 over v. I know the value of f, or we can put it like this, f equals uv over u plus v. This is what you can do it. So, we know f1, we know f, then I will find out like this 1 over f equals 1 over f1 plus 1 over f2. I am putting the formula like this, but I know this value, I know this value. 1 over f minus 1 over f1 is equal to 1 over f2. So, simplify this, you get the focal length of the concave lens. This is one method, and you can also have a different method. That means you can keep some distance between the two and you can again find out. Anyway, that is rather this is better than that. So, this is what we do in respect of convex lens, rather concave lens, not concave. Convex lens we can find out easily. And coming to mirrors, because concave mirror I wrote the formula there, rather this. The concave mirror is, for example, this side where the mirror is silvered, we call it as silvered. This side is bent and this side is of course convex. That surface is bulging out, and this is convex mirror, and the other one is concave mirror. The concave mirror, here I have, this is concave mirror. You can see that here it is bulging in. If it is bulging out, it is convex mirror, and bulging in, it is concave mirror. Of course, in respect of a concave mirror, again you get the real image, except when the object is less than 10 centimeter. In the sense, if the focal length is 10 centimeter and if the object is kept at a distance less than 10 centimeter, you get the virtual image, and that virtual image is erect and enlarged. Same thing even with respect to the lens. My question next is, what type of mirror is used in vehicles? That we call it as a rear view mirror. Convex. Convex or concave? Convex, because we are getting only the virtual image and not the real image. Therefore, convex mirror is used. And coming to this, and of course, we have to do some experiment to show that refraction through, but let me just try here with the help of see how refraction takes place. In fact, we can do the experiment if you are getting the slab like this. That means first what you can do, you can find out the refraction like sin I by sin r. So, let us say you keep the slab on a sheet of paper, of course, you have to keep it on the table. Then just outline the frame of this, and then what you do, you take two pins, fix pin 1, pin 2 and draw a line, and then on the other side you just see the image of these two pins and fix the pins, and after removing that you see that the refraction takes place. Yes, you can do that. Now and I didn't tell you about the conservation of momentum. Suppose you take two balls, you can try that. Let us say I have one more thing is there, of course. And ಇಲ್ಲಿ ಇದು ನೀವು you can do that experiment at home because there are different experiments. ಇದು ನೋಡಿದ್ದೀರಾ ಏನದು? For example, you can do that experiment. I just show you what you can do. You can take a plate, put water on it, and then take the candle and light the candle, and then when the candle is burning, then put some glass bulb on it. What do you observe? Anybody who have already seen this diagram in the book? Huh? Yes. What did you observe? Off. Then water will move up. Why? What may be the reason? Huh? Yeah, the pressure, right. It is because of the pressure difference that will go up. And of course, I have something I have to go out and show you. Only if the sun shine is there, I will just show you. ಇದೊಂದು ತೋರಿಸೋಣ ಅಂದ್ಕೊಂಡಿದ್ದೆ, ಬಟ್ ಅದು ಸನ್ಲೈಟ್ ಬೇಕು. ಈಗೇನು ಮೋಡ ಇದೆ ಅನಿಸುತ್ತೆ ನೋಡಿದ್ರೆ. ಹೌದು, ಕ್ಲೌಡಿ ಇದೆ. ಆಫ್ ಕೋರ್ಸ್ ಇಟ್ ಈಸ್ ಅವೈಲಬಲ್ ಇನ್ SJP ರೋಡ್. SJP ರೋಡ್ ಅಂದರೆ ಬೆಂಗಳೂರಲ್ಲೇ, ಬೇರೆ ಎಲ್ಲೂ ಅಲ್ಲ. Let us say you have the solar cell like this. If I go out only, then I can conduct the experiment, not here. And you have a fan, small fan attached to this, and suppose you hold it. If you take solar cell and if the sun light is falling on it, you will see that the fan will rotate. That means we show that the solar energy is used, and that solar energy is what you call it as the light energy. The light energy can be converted into mechanical energy, because when the fan is rotating, it is mechanical energy. And at the same time, you can also have yes, one LED is there, and you can use LED. If you fix it here, you see that the LED will glow. That means the light energy again being converted into light energy. And then you have some sort of a speaker here. When the light is incident on this solar panel or solar cell, and you will hear the sound. That means solar energy can be converted into sound energy. So this is what you have basically. And before I close it, let me, all of you have seen AC generator, those who are in first PUC, because in 10th standard itself you have seen. This is of course there you have seen only the book. In the book, what is that? There will be those who are not able to see, better you come and see, so that it will be easy for you to understand how AC generator works. And here you know, these are the two magnets. One is north pole, the other one is south pole. And these two magnets may be permanent magnets or electromagnets. Of course, these two are permanent magnets only here. And here we have a coil. And in between that coil, we can also have one iron block. But I don't have iron block here. This we call it as armature. And here we have slip rings. Then this instrument gives you both the concept of AC as well as DC generator. AC generator means we have to use a galvanometer like this. Have you seen the galvanometer? Yes. This galvanometer, we call it as the pointer galvanometer. Let us say I will connect these two wires there, and if I keep rotating it, that means this is a rectangular coil. But this coil is not so rectangular like what we talk, but anyway, not necessary. if we want to go for the actual calculation of the induced EMF, we use the formula like E is equal to E naught sin omega t, and where omega is the angular frequency, t is at any instant of time. That means if we keep rotating it, you know there is a magnetic field, that means there will be a magnetic flux. When we keep rotating this coil, the magnetic flux changes. When there is a change in magnetic flux, an EMF is induced, and that induced EMF results in current, and therefore we observe the current in the galvanometer, in the sense the pointer shifts. That means in respect of an AC generator, you find that the needle moves on both sides. That means if we keep on rotating, let me ask you, what is the voltage in our India, the AC voltage, domestic supply voltage? 220. How about the frequency? Frequency means, what do you mean by frequency? Can anyone tell me? Frequency. What is the relation between the period and the frequency? What do you mean by period? Period is, that's what I told you in the beginning with respect to the remote sensing satellites and the geostationary satellite. Period means to and fro motion or one revolution. The period, and the frequency is how many revolutions are taken place in 1 second. That is frequency. Frequency is measured in hertz and period is measured in second. So T is equal to 1 by F. So that is what we have, the relation between the period and the frequency. That means if we keep on rotating it, there will be change in flux. Suppose I have like this, that means here the magnetic field is like this. Like this means, let us say this is north pole and this is south pole. The magnetic field is from north to south. It is, let us say this is in x direction and this is in y direction. So if it is exactly at right angles to each other, and cos 0, because we use the formula like cos, and then finally we change it to sine. Sine, you know, E is equal to E naught sin omega t. That means when it is coming to this sin omega t, when theta is equal to omega t, actually omega is equal to theta by t. Omega, the angular frequency, is equal to theta by t. It is similar to like S is equal to, V is equal to S by t. Velocity is defined as the distance by time. Same thing like that, angular velocity is theta by t, angular displacement by time. And there is a relation between the linear velocity, this we call it as the linear velocity. That means if a body moves from one place to another place, then we call it as linear velocity. On the other hand, if the body rotates, then we call it as the angular velocity. So if I write like this, S is equal to r theta, that is the relation between, suppose you have like this, let us say the body moves from this position to this position. If I call it as O, this I call it as A, this I call it as B, this we call it as arc, yes, and this is theta, this you call it as r. So we write the relation S is equal to r theta. Suppose I write it here, then we get V is equal to r omega. That is the relation between the linear velocity and the angular velocity, whatever it is. So theta is equal to omega into t. That is how we write E is equal to E naught sin omega t. So if theta is 90 degree, that means omega t is 90 degree, E becomes E naught, that is maximum. So it keeps on varying and it will be like this. So we use like this, this is what? In fact, it is varying like this. Anybody told me about the frequency of AC in India? Voltage is 220 volt, that you told me. but I think I didn't get the answer for frequency of, no. This you call it as E or I, EMF or current, and this one is time. This is the peak value, and which you call it as E naught. Same thing on the other side, it is minus E naught. It goes on like this. This we call it as frequency. This is the period. T is equal to 1 over F, and frequency of AC in India is 50 hertz. But in other countries, for example, America, it is 60 hertz, and voltage supplied to domestic, it is 110 volt, 110 and 60. How about our nearby country like Pakistan? Same as our Indian system. That means a frequency 50 hertz, domestic supply voltage 20 volt, and therefore the power supply can be supplied to Pakistan, or we can take from it there in case if there is a shortage. So this is what we have about AC generator. And then and one more thing, I just want to show this. Any piece of paper idea, idu chellutto eno? No, not that small thing. Maybe at the 8th standard itself, simple pendulum experiment is there. ಇದು ಇದ್ರೆ ಒಳ್ಳೆಯದು, ಇದು ಚೆಲ್ಲಿದ್ರೆ ಅಂತ. You know about the simple pendulum. How do you find out the period of the simple pendulum? Can you tell me? You have, but of course formula you have not studied it since. Bidi idille ತೋರಿಸ್ತೀನಿ ಏನು ಸಾಕು. We use the formula like this: T is equal to 2 pi into square root of L by G. This is the formula to find out the acceleration due to gravity. Can anyone tell me what is the acceleration due to gravity of the earth? 9.8. Of course, it is not constant all the days, or rather all the time. It varies from place to place and also from time to time. Time in the sense not that drastic change. It may be 9.79 something, 81, something like that. So anyway, this G is equal to, it is 4 pi squared into L by T square. So we use the simple pendulum to find out the acceleration due to gravity. Of course, there is a relation and a difference is there between small g and capital G. What is that capital G called? Capital G is gravitational constant, universal gravitational constant. It was established by Newton. And gravitational constant is constant forever, no change in that. Whereas the acceleration due to gravity keeps on changing. That is small g varies, and the value of g varies from equator to the poles. Yes, it is one experiment, and that we can find out. Here my question is, let us say I have, it is not a simple pendulum, we cannot call it as a simple pendulum, but here let us say only when we fix it, a paper ಸ್ವಲ್ಪ ಕೊಡಿ, ಇದನ್ನು ಅಲುಗಾಡಿಸಿದಾಗ ಚೇಂಜ್ ಆಗ್ಬೋದು. ಕೆಳಗಡೆ ಸ್ವಲ್ಪ ಕೆಳಗಡೆ ಹಾಕೋಣ. ಸೊ ವಾಟ್ ಐ ಹ್ಯಾವ್ ಡನ್, ಇಲ್ಲಿ ಏನು ಐ ಥಿಂಕ್ ಒಂದು ಹೋಲ್ ಮಾಡಿದ್ದೀನಿ, ಅದನ್ನು ಕ್ಲೋಸ್ ಮಾಡಿದ್ದೀನಿ. ಈಗ ಬಿಫೋರ್ ಐ suppose I rotate like this. I am doing very wrongly, of course. A physics student should not do like this, but just to explain. Let us say I find out the period when this bottle is completely filled. I may get some time, 2 seconds. On doing like this. Yes, it is coming out. Of course, it may not be, I may not be able to do it properly. So if I keep rotating like this, because the paper is also white, you will not be able to see. Anyway, when you fix it by ಕೈನಿಂದ ಹಿಡ್ಕೊಂಡಿದ್ರೆ ಅಷ್ಟೊಂದು ಸಿಸ್ಟಮ್ಯಾಟಿಕ್ ಆಗಿ ಬರಲ್ಲ. ಒಂದು ಸ್ಟ್ಯಾಂಡ್ಗೆ 60, if you just rotate like this, you will see circle, ellipse like this. Not only that, how about the period as the sand or powder is going out like this? That's what my experiment. ಈಗ ನೀರು ಹಾಕಿದರೆ ಬೇಗ ಹೊರಟೋಗುತ್ತೆ, ಅದಕ್ಕೆ ನೀರು ಹಾಕಲಿಲ್ಲ. ಇಲ್ಲಾಂದ್ರೆ ಇನ್ನೂ ಸ್ವಲ್ಪ ದೊಡ್ಡ ಹೋಲ್ ಮಾಡಬೇಕು, ಬರುತ್ತೆ, ಇಲ್ಲೆಲ್ಲ ಗಲೀಜಾಗುತ್ತೆ ಅಂತ ಸ್ವಲ್ಪ ಹಾಗೆ ಮಾಡಿದೆ. ಪ್ರಿನ್ಸಿಪಲ್ ಗೊತ್ತಾಗಬೇಕು ಹುಡುಗರುಗಳಿಗೆ. ದಟ್ ಇಸ್ ವಾಟ್ ಐ ವಾಂಟ್ ಟು ಎಕ್ಸ್ಪ್ಲೈನ್. ಸೊ ಇಫ್ ಐ make it to oscillate, then let us not worry about whether we get a circle or not. But my theory or my principle here is, what is the period when it is completely filled? And when we keep rotating it or oscillating it, the sand or the powder will go out uniformly. And when it is going out, what would be the period? Again I am coming back to center of gravity. ಈ ವಾಟರ್ ಏನಾದ್ರು ಹಾಕಿದರೆ ಬೇಗ ಹೊರಟೋಗುತ್ತೆ. ದಟ್ ಮೀನ್ಸ್ ವೆನ್ ದಿ ಪೌಡರ್ ಈಸ್ ಗೋಯಿಂಗ್ ಔಟ್, ಇನ್ನೊಂದು ಸ್ವಲ್ಪ ಹೋಲ್ ದೊಡ್ಡದು ಮಾಡಿದ್ರೆ ಈಗಲೇ ಹೊರಟೋಗುತ್ತೆ ಅದನ್ನು. ಸೊ ವೆನ್ ದಿ ಪೌಡರ್ ಈಸ್ ಗೋಯಿಂಗ್ ಔಟ್, ದ ಸೆಂಟರ್ ಆಫ್ gravity keeps on changing. As the center of gravity keeps on changing, naturally the length changes. As the length changes, the period changes. Let us say that it is completely removed. All that powder or sand has gone out and it is empty. What is the period after it is completely gone out or completely removed, and the period initially? When the sand or the powder is going out, the period keeps on increasing because the length of the simple pendulum increases, because the center of gravity keeps on decreasing, in the sense it is going down. Now when it is completely emptied, ಎಲ್ಲ ಫುಲ್ ಮುಗಿದೋಯ್ತು, what is the period compared to the initial one? The period remains the same after it is completely emptied. Why? Center of gravity comes back to its original position. So when it is completely filled, the center of gravity, like what you told me in the beginning itself, center of mass and center of gravity. Of course, if it is uniform, center of mass and center of gravity will remain the same. But the center of mass may change here, corresponding to that center of gravity also changes. So as the center of gravity changes, the period changes, and when it is completely emptied, again it comes back to its original position, and therefore the period when it is completely filled and the period when it is completely emptied will be the same. Therefore we get the same period. So this is a principle. Of course, we can do the experiment only if we fix it and make it to oscillate. It keeps doing like that. I will, you can try at home, otherwise it will spread like this. Sir, ಸಾಕಷ್ಟು ಏನು think we have some other things, may not be, because already it is time up. I will stop at this stage. If you have anything to ask, definitely you can ask me, and even other than what we have done also, in case if you want. This of course, because ನಾನು ತೋರಿಸ್ತೀನಿ, I have like this. One of you can come and try. See, this is what we have. ಮ್ಯಾಗ್ನೆಟ್ ಸ್ವಲ್ಪ ಹಳೆಯದಾಗಿದೆ, ಅದರಿಂದ ಅಷ್ಟೊಂದು ಯು ಕ್ಯಾನ್ ಸಿ ಹೀಗೆ ಬರ್ತಾ ಇದೆಯಲ್ಲ. ಓಕೆ, ದಟ್ಸ್ ವಾಟ್ ಯು ಕ್ಯಾನ್ ಸಿ. ಹೋಗಿ ನೀರು ಚೆಲ್ಲೋಯ್ತು. ಸೊ ಇಫ್ ವಿ rotate fast, you can see the deflection. That's what. It's only a demo model, but that demo model is similar to that of what we have got in AC generator. But in an AC generator, you know, turbine and steam is used in thermal and hydroelectric power project alli the water is falling from a very high position, and thereby the mechanical energy is converted into electrical energy, and that electrical energy can be used in different forms. This is what I think we will stop at this. So, anything
ನೀವು ಕ್ವಶನ್ಸ್ ಕೇಳಿದ್ರೆ ಅರ್ಥ ಆಗಿದೆ ಅಂತ.
ಇಲ್ಲದಿದ್ರೆ ಇಲ್ಲ, ಏನೋ ಸುಮ್ಮನೆ ನೋಡಿದ್ರೆ ಅಷ್ಟೇ.
ಎನಿ ಕ್ವಶನ್ಸ್? ಆಲ್ರೆಡಿ ಟೈರ್ಡಾ? ನಿಮ್ಮ ಕೈಲೇ ಮಾಡಿಸ್ಬೇಕಾಯ್ತಾ?
ಅವ್ರ ಕೈಲೇ ಮಾಡಿಸಿದ್ರೆ ಚೆನ್ನಾಗಿರ್ತಿತ್ತು. ಒಂದು ಮಿರರ್ದೊಂದು ಮಾಡಿದಾರಲ್ಲ ಅವರೇ.
So anyway, thank you very much, sir, for your interactive session. And as usual, tomorrow please we can start mathematics. No, fun with mathematics tomorrow, the whole day. So I think you will all like that session. And once again, thank you, sir.
Oh, thank you, sir. Thank you, and I wish you all the best.
So please, I request parents, some students give the feedback in the reception about this program, and request please go to the canteen and have some tea.
ಬೇಗ ಕ್ಲೋಸ್ ಮಾಡಲ್ವಾ? ಹೌದಾ? ಸ್ವಲ್ಪ ಗ್ಯಾಲ್ವನಾಮೀಟರ್, ಅದು ಗ್ಯಾಲ್ವನಾಮೀಟರ್ನ ಆಮ್ಮೀಟ್ರಾಗಿ ಕನ್ವರ್ಟ್ ಮಾಡ್ತೀವಿ. ಒಂದು ಶಂಟ್ ಯೂಸ್ ಮಾಡಿ, ಅಂದರೆ ಲೋ ರೆಸಿಸ್ಟೆನ್ಸ್. ಹೀಗೆ ಅದು ಇಲ್ಲ, ಈಗ ಹೇಳ್ತೀನಿ.
ನೀವು ಇಂಟ್ರೆಸ್ಟ್ ಇರೋರು ಇಲ್ಲಿ ಬಂದು ನೀವು ಮಾಡಿ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್.
ಗ್ಯಾಲ್ವನಾಮೀಟರ್ ಇದಾದರೆ ಇದಕ್ಕೆ ಒಂದು ಲೋ ರೆಸಿಸ್ಟೆನ್ಸ್ ವೈರನ್ನು ಕನೆಕ್ಟ್ ಮಾಡ್ತೀವಿ. ಇದು ಶಂಟ್ ಅಂತ. ಸೊ ಕರೆಂಟ್ ಇಲ್ಲಿ ಪಾಸ್ ಆಗ್ತಾ ಅಂದರೆ ವೆರಿ ಸ್ಮಾಲ್ ಕರೆಂಟ್ ವಿಲ್ ಪಾಸ್ ಥ್ರೂ ಗ್ಯಾಲ್ವನಾಮೀಟರ್ ವಿಚ್ ಪ್ರೊಡ್ಯೂಸಸ್ ದಿ ಡಿಫ್ಲೆಕ್ಷನ್. ಇದು ಗ್ಯಾಲ್ವನಾಮೀಟರ್